Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on how to solve word problems in trigonometry. Now, this is our first lesson in our chapter for applications of trigonometry, but I'm actually taking this section from a typical chapter of just trigonometry. So this is typically comes in like as the last section in a trigonometry chapter. But for my teaching, I decided to take it in and put it into this chapter because this is going to be a calculator-based chapter. And therefore, we're going to be using a calculator to solve the word problems. So I wanted to make sure that when we're using our calculator that we're going to be using it for all of the sections. So this is our first calculator-based section in our pre-calculus class. And these problems actually make sense because we are applying what we have learned for trigonometry. So in this section, we are going to learn how to set up word problems using angles of elevation, depression, as well as bearings. We're going to convert DMS, which is decimal minutes seconds, to decimal form. And we're going to learn how to use our trigonometric and inverse trigonometric functions to solve trigonometric equations. Now again, these are going to be equations that we are going to create based off of the word problems. So the way I like to introduce this kind of unit was just to, remember this is from our trigonometry unit. So typically we've already covered analytic trigonometry, and now we're kind of going back to some basics. But still, most students still should be comfortable with being able to solve for these because I believe actually even from geometry class, they were doing these types of problems. So if I want to find the missing measure of each triangle, let's just work on this first one. You can see here we have a side length. Now I have 45 degrees, it's a right triangle. I have 45 degrees and then I have two sides of a triangle. Now, in our trigonometry unit, we talked about the trigonometric functions, right? So we could, if we want to find the missing measure of a right triangle, we could use Pythagorean theorem or our trigonometric functions. Well, we could only use Pythagorean theorem if we have all three, like at least, two of the sides, and then we're trying to solve for one, an unknown. We don't know what this side length is, so we can't apply Pythagorean theorem. However, since we have an angle, we can use a trigonometric function depending on what that angle is, or depending on the sides based on that angle. So if I see from this angle here, 45 degrees, I have the opposite and the hypotenuse. So therefore I just want to think, which trigonometric function would I want to use? Well, in this case, if here's 45 degrees, you can use the sine, right? Because remember, the sine of some angle is equal to opposite over hypotenuse. So in this case, I'm just going to write a trigonometric equation. I'm going to say sine of 45 degrees equals x over 2. All right. Now, if I want to solve for x, I'm just going to multiply by a 2 on both sides. And therefore, I get x equals 2 times this sine of 45 degrees. Now, to understand the sine of 45 degrees, remember, we can just go back to our unit circle, right? We could use our calculator, but in this case, I'm just trying to give something nice for the students. And remember, based on the unit circle, 45 degrees, that's going to be the y-coordinate, which was square root of 2 over 2. So therefore, this would be 2 times the square root of 2 over 2. The 2's would now divide out, and therefore x equals the square root of 2. All right, so quick thing. When we're trying to find the side length here, you can see how we're using our trigonometric function of our angle. Now in this next case, we're trying to actually find the angle. So you can see here x, now this variable here, is actually written as an angle. But again, I have two sides of my triangle. So Pythagorean theorem didn't help us with angles of a triangle. But again, I'm going to want to revert back to my trigonometric function. So now if I was going to write the same thing, because I have opposite and hypotenuse, right? So now I'm going to say the sine of x equals 3 over 6. So I can simplify that, so let's go and do that real quick. Sine of x equals 1/2. Now, we could go ahead and solve this just by understanding the sine of what angle equals 1/2, but we need to kind of remember two things. First of all, last chapter we talked about finding all of the solutions, right? The sine of x equals 1/2 infinite many times, right? If you're going to look at this graph here, like there, if this is 1, then you can see that this graph crosses 1/2 infinite many times. Well, we know that in a triangle, there's not infinite many answers, right? So we need to understand the context of this problem. So last chapter in analytic trigonometry, we were saying, find all the solutions. And you would say, oh, well, sine of infinite many angles is going to equal 1/2, right? And then you can cross it here, and you cross it there, and so on and so forth. But that doesn't make sense in the context of this problem. So if you remember in our trigonometry unit, the last thing that we taught was inverse trig functions. And remember, inverse trig functions, they couldn't have more than one solution because then they wouldn't be a function, right? When you're doing inverse trig functions, you can only have one answer, right? Because it's a function, right? You plug something in, you're going to get one thing out. So we can't use what we did last chapter as far as solving this. Now we can still think of the unit circle in this case, like the sine of what angle equals 1/2. So let's just kind of do the unit circle here real quick. And think about, like, when is sine of x equal to 1/2? So we have this angle and that angle. Now, we could use radians, but since we're going to be doing triangles, we really are going to convert here just to focusing on using degrees. So you can see that there's two answers, right? I have sine of x equals, that's going to be 30 degrees, and this one would be 150 degrees. Well, 150 degrees doesn't make any sense, right? Because if this was 150 degrees and that's 90, remember all the angles in a triangle only add up to 180. So this cannot be 50 and that be 90. Therefore, you can see how that makes sense. Now, the way that actually we want to do it, so you could use some kind of like common sense there. But again, in reality, what we're doing is what we did in our trigonometry chapter. If I want to undo sine, I have to take the sine inverse. So my answer, x, is sine inverse of 1/2. Right? So really what we're asking you to do is evaluate the sine inverse of 1/2. And this is important for this chapter because that's what we're going to be typing into our calculator, is the sine inverse of 1/2. Now, again, we know what the sine inverse of 1/2 is. But again, like, what if my question was the sine, what if I had, so I gave to my students, I'm like, all right, so you guys could figure that one out on your own, but what if it was 1/5? We're not familiar with that, right? So if you're, like, we don't recognize that as far as a y-coordinate on our unit circle, so therefore you have to take the sine inverse of 1/2. And the rule of kind of thumb that I have with my students is when you want to find the angle, you're going to be applying the sine inverse. And when you want to be able to find the side length, you're going to be using your sine, or your trigonometric function versus the inverse trigonometric function. So anyways, my answer here is going to be 30 degrees. Okay, so we'll get some practice with that. It's just kind of an important thing to understand what you're solving for. Well, solving for x. Well, remember, the trigonometric function says sine of x. So we need to undo that sine, so therefore that's why we're going to be applying the sine inverse. All right, so just a quick little review. Again, this is after covering analytic trigonometry. So sometimes students kind of forget like where everything came from or what we've previously done in our previous chapters. So the main functions we're going to be working on is just going to be our three main functions, the sine, cosine, and tangent. We're also going to be using a lot of going back to our triangles. So again, just remember when we're dealing with a right triangle, our trig functions only work for right triangles. And they're all going to be based on where your angle is. So if here's your angle theta, here's your adjacent, here's the opposite side, and here is the hypotenuse, right? But again, it's all dependent on where the side lengths are. Okay, because if I did the exact same thing here, same right triangle, but if I put theta here, well, now this is the adjacent side, this is the opposite, and then we have the hypotenuse. Okay, so just make sure you're aware of where everything is landing based on where that angle is. The other thing is just a review of the inverse trig functions. And remember, inverse trig functions, they're functions, right? So they have a restriction on them, or the domain of the function of the original function is restricted. So therefore, our inverses can be functions. So if I did the exact same notes that we've already covered. The only difference is that I changed the restrictions to degrees. And just so you can kind of remember, well, this is something that's going to come up a little bit later in this chapter, but it's just kind of good to note right now that remember that cosine is restricted between 0 and 180. Inverse sine is restricted from -90 to 90, and tangent, again, is going to be restricted from -90 to 90. So again, you can see why that 150 degrees wouldn't work, right? Because does not fall within the restrictions of inverse sine. So again, this is something we'll continue to build upon in this unit. All right, so the next thing is going to be our degrees, minutes, and seconds. So degrees, minutes, and seconds is just a way for us to really break down our units for angles. So rather than using decimals, which we could use decimals, right? Which we do. We're going to be. It's a lot easier to be typing in decimals than it is going to be typing them in as far as minutes and seconds. However, the one thing I kind of related is obviously the degree minute seconds is very similar to the hours minute seconds, right? And I just tell students, think about like when somebody's running a marathon, and they run it, they give them the hours, the minutes, and the seconds. They don't tell them that they ran it in, 15.765, hours, right? So we give them in that hours, minutes, seconds. And that's the same thing that we'll do with the degrees, minutes, seconds. It's just a way to break down each of the units. So for every degree, right, there's 360 degrees in a circle. For every degree, that can be broken down into 60 minutes, which is 1/60th of a degree. And then each minute can be broken down into 60 seconds. So the way that's important to understand is, now again, I didn't write the units on here. So 1 degree, we have our degree symbol, right? Did I not do that? Oh, I guess that was in our last chapter. So we have 1 degree. That's going to be equal to 60 minutes. All right, and again, since there's 60 seconds in 60 minutes, we're going to multiply 60 times 60 to give us 3,600 seconds. All right, so there's 3,600 seconds in 1 degree. And again, if you get confused with the degrees, a lot of times I just tell students, just use hours. Just think of it as hours. It's the exact same really kind of math here. The one thing that we're going to be working on is actually converting them, because we're going to often get like word problems where our angle is going to be in degrees, minutes, and seconds, and not everybody's going to have a calculator where they can just type it in and then get a conversion. So what I'm going to do is I'm just going to show you a quick little method to be able to convert to them, so therefore you can solve the word problem. All right, so let's go ahead and practice that conversion. So in this one we have convert the following angles to decimal form, round to the nearest hundredth. Now the main important thing is when we're dealing with the negative doesn't really impact what the angle is, okay? Or I mean the conversion. So I'm just going to put the negative outside parentheses. Now I'm going to have 15 degrees. So the next one is 33 minutes. Well, obviously, if I had 60 minutes, I would have, an extra degree, right? But I don't have 60 minutes. I have 33 minutes. So that's roughly about half a degree, right? Because 30 minutes is half a degree. So we have 33. So I can kind of already know that my decimal is going to be 15.5, or like roughly, just kind of close. And I'm telling you this just so you can kind of understand, where your answer should lie. So what I'm going to do is I'm going to add not another degree, but 33 out of 60 of them, right? Because again, that decimal, as you can think about that decimal represents like 0.5 a degree. So 33/60ths is going to be what 33 minutes can be represented in degree form. And then I'm going to add that to, now I only have 10 seconds out of 3,600 make up a degree, right? So I'm going to write this as 10 over 3,600 degrees. So again, if I had 3,600 seconds, right, that would be a degree. So obviously we're not going to be able to add all those up. Now a lot of times I'm just going to be able to type these in the calculator. For right now, I'll kind of show you what these decimals show up as. So therefore you can just kind of see how I get my final answer. So I'm just going to have 15 degrees plus, and then you're just going to take 33 divided by 60. In this case, I get 0.55 plus, and then 10 divided by 3,600, and that's going to be a 0.0027. It looks like that is going to be repeating. Now, here's a good point where it comes into the rounding portion for this chapter as well as for the class. So there's a lot of different ways to go about this. The way that I kind of told my students, or actually this says round to the nearest hundredth. So what I'm going to do is I'm just going to add all those up. And actually you can see that by rounding it to the nearest hundredth, that's going to change that to a 3, right? So actually, I'll just round that. So now my final answer is going to be a negative 15.553 degrees. Okay. What I was saying though, if I don't mention how to round it, then this is going to be just my expectation in my class, rounding to the nearest hundredth. Or I also tell students that they can truncate it, meaning not round, but at least go to 3 decimal places. So therefore, we have negative 15.553 degrees. All right, moving on. So now I just have a couple other problems. Again, one of the ones I just wanted to kind of go with my students here that, so this one we have 59 degrees. And this one you can see that's 0.5, right? 33 out of 60. Well, actually, that's just right out there. So we have 59 plus 30/60. Now this is nice because if you see this, you already know that's 0.5, right? And then we have 100 divided by 3600, which is going to be 0.02. So again, 0.027. So now I can have 59.5328. So again, this is going to be rounding to the nearest hundredth. So therefore, that 7 would be round up, and therefore there would be a degree, 59.528. Now the next one, we only have a degree. We don't have a second. So again, that's fine, right? We don't need to worry about that. So that's going to be a -7 plus a 35/60. So then I just take 35 divided by 60, and I get 5.8333. So I have a -7.583 degrees. And that's repeating, so it's not going to round. And the last one, I don't have a degree, but I have 3,600 seconds, or 36 seconds. So I do 36 divided by 3,600, and that's going to be 0.01. So therefore, this is going to be 23.01 degrees. Actually, let me just write it out because that's what I've been doing for the rest of them. So we have 23 plus 36 over 3,600, which obviously you can see 36 over 3,600 would be that 0.01. So 23.01 degrees. All right, so that's basically how we're going to convert. A lot of times when I'm doing these in my problem, I will typically just type this into my calculator and then at least provide you guys the decimal answer. But it is just something that comes up, so I just want to make sure students can do it because I do kind of give them a shortcut if they are working with a TI calculator. But otherwise, students have different calculators, in this chapter. So I don't expect, I do want everybody to at least know how to do that. All right, the next one is the elevation and depression. So we're going to be coming across a lot of angles in these word problems. So we want to make sure we understand the difference between an angle of elevation and an angle of depression. And really the difference between an angle of elevation and an angle of depression is how they react to a horizontal line. So it's pretty obvious. Elevation, you can think of up, right? So if we have an angle of elevation from a horizontal, that is going to be up. So that's elevation. And then if we are going down from a horizontal, then that's going to be a depression, right? So it kind of makes, if you just kind of think of what those two words mean, it kind of makes sense as far as elevation's going up, depression's going down. Now, a lot of times where students get mixed up, though, is understanding where is the horizontal, or what does the horizontal represent. So a lot of times the horizontal is going to represent like ground level, or it could represent the water level. It could represent the a rope between two buildings that are the same height. It could represent the path of a plane, the path of a bird, the path of a helicopter. Anything that can be represented as a horizontal line, even if it's a physical line or actually an imaginary line or pathway. Typically, that's where our elevation is going to be either above or going to be below. But it's going to be some kind of horizontal line or something that's going to represent a horizontal line. And you'll see in these word problems, we'll be doing some of those paths with the angle of elevation or depression. And if it's not one of those angles, then typically it's going to be represented as a bearing. So a bearing is another angle that we're going to use that's very often used in navigation. So typically, if you remember, we talked about standard form. So, when we first did this chapter, we did everything in standard form. So we have, in standard form, remember, we always started on the initial positive x-axis, and we rotated clockwise to give us a positive angle, and we rotated, counterclockwise to give us a positive angle, and we rotated clockwise to give us a negative angle. And that is basically how we created our standard form. That's how we graphed our angles in standard form, and basically from there. However, for bearings, that's going to be dealing with our cardinal direction. So there's actually two ways that we're going to use bearings. But bearings are going to be, yeah, they're very often used for word problems, especially when we're dealing with navigation. So the difference with a bearing is you can kind of think, we still have our coordinate plane. Like we still have, you know, our x-axis and our y-axis. The only difference is now we're going to be kind of referring them to north, east, south, west, right? And the important thing is, you know, one way to represent a bearing is just going to be from due north. So if I said it travels at a bearing of, let's say, you know, 30 degrees, then that's going to be from due north clockwise. Now, the nice thing about bearings is they are always going to be positive. So if you remember in standard form, we had, you know, we had angles in degrees, we had angles in radians. They could be positive, they could be negative, they could be larger than 2 pi, you know, or larger than a revolution. It kind of got a little crazy. The nice thing about a bearing is they're always going to be positive, and they're always going to be within a revolution, between 0 and 360. So there's really no point for us to be giving us bearings, you know, that are larger than one rotation around. So this would be what we call a bearing of 30 degrees. Or we could also do a bearing, like if we had a bearing over here. Oh, actually, let's go over here. Or if we're going to do a bearing like this, we could say, all right, now that's going to be a bearing of, let's say, 300 degrees. Okay? So the nice thing about bearings is they're always positive. They're always going to be less than 360, but they also always go in the same direction. And they always start from due north. So instead of starting at the positive x angle, a bearing is going to start at due north, and it's going to rotate. I'm going this way, but you guys are now looking this way. It's going to rotate clockwise. So obviously you have, you know, 30 degrees, then we go to 90, you know, 180, 270, and then 360. So you can see that that's how that represents that's how those two angles would be represented. Now, again, that's when we're talking about a bearing of 30 degrees or 300 degrees. Sometimes this is not always the easiest way to identify the bearing, so there is another way that we write bearings, and that is, again, with our cardinal directions of north, east, south, west. So I want to present both of them to you because on multiple choice problems, they could be either one or the other. So we just want to make sure we understand both of them. Now, if I wanted to represent this angle as 30 degrees, I could also write this, actually, I could also write this as 30 degrees, north, 30 degrees, east, okay? So the nice thing about this way, this direction, is it's actually always going to keep angles acute. So I didn't do one, but let's just do this one. So what if I had like this angle here? Now if I was to write that as a bearing, let's just say this would be like 250 degrees. Well, that's kind of like maybe like a lot here, right? So another thing that we could write in this case is, let's pretend this angle from here to here, let's see, that's just going to be 70 degrees, right? So, and instead of writing that as like 180 plus 70, which would be 250, right? You could write it like this, 250 degrees. We could also just say south, 70 degrees, west. So when writing a bearing in this notation, basically we're either going to start with due north or start with due south. We're not going to start with due west or due east. We only start with due north and due south. And then we're just going to rotate to the east or to the west. And that's basically how we can go. And whatever that rotation is, that will give us our bearing. So I'll make sure that I do an example of both of them in this chapter. But that's basically the idea behind the differences between those two. All right, so let's just go ahead and practice. Go ahead and graphing one of these so you can kind of get an idea of sketching the following bearings. So in this case, I have 120 degrees. Oh, I already did 300. Guess that was on my mind. So again, you're going to start due north, and you say, all right, well, from here to here is 90, and from here to here is 180, right? So again, just to kind of give a rough estimate here, there would be my bearing 120 degrees. And again, remember, we have to start at due north. And actually, one thing I forgot to tell you. Whenever we're drawing a bearing, I always recommend to students to draw the northeast, southwest. Because once we get into more complicated problems, understanding where everything is going or this direction is going to be very helpful. So for the next one, 300 degrees. Now, I estimated this last one, in the example I was giving. So let's go ahead and actually kind of think about this? Well, if I'm going to start on north, all right, you always start due north. I know if I rotate all the way around, that's 360 degrees, right? From here to here is 90. So I have from here to here is 90, then 180, then 270 to 360. So I can tell that 300 degrees here is going to be somewhere in that direction, all right? So that'd be my bearing of 360 degrees. All right, so now you can see our two bearings. Again, it says north, 17 degrees west. So again, the first letter is telling us where to start, or where to kind of point our direction. So that's east, not west. So we have north, and then we're going to be 17 degrees for you guys west, this way, right? So we have north, and then 17 degrees west. All right, or this one, we're going to start on due south. So now I'm still going to label everything. Make sure you get those set, north, east, south, west. So we're going to south, and then 71 degrees east. And there you go. So you can kind of see how this is a little bit different. And again, these are two different forms, but it is important that one of these, ways you will possibly see. And again, basically it's best to just kind of keep it whatever. If you're given, your angles as bearings as these first two, and then you're asked to write the bearing, then you're going to want to keep that same format. Okay, so now let's go and talk about the tips for solving trigonometric word problems. So the first thing that we're going to do is just draw the picture. So that's what I tell all my students, when we're given a problem, just draw the picture. If anything else, just draw something. The next thing is we're going to identify the right triangle. Now, in this chapter, we know that we're only dealing with basic trigonometric functions, right? Sine, cosine, tangent, and the inverse sine, inverse cosine, inverse tangent. So we don't have to worry about crazy triangles. We just know we're going to have a right triangle. So from that picture, we want to make sure we can identify the right triangle as well as label its parts, meaning whatever lengths we have or distances, as well as whatever angles we have. Then for step 3 is we're going to define the variable. We don't want to just write h and just assume that people understand that that represents the height. So whenever we're using a variable, we're going to make sure that variable is defined either as a representation of a measurement or equal to some sort of equation. Then for question number 4, we're going to set up an equation to solve for the missing value, which is basically going to be our trigonometric equations. Then we are going to solve, and we're going to check your answer, does it make sense? And I can't tell you how many times this happens. People will go ahead and, the first equation to solve for, they just go ahead and solve, and then they just live there, and it doesn't answer the question. So always make sure you go back to the original question and make sure that the answer that you have actually answers the question, as well as makes sense, right? If you walk 5 miles and then walk 2 miles, your answer shouldn't be you walked 10,000 miles, right? Or you walked 0.01 mile. So just make sure when you're, when you're checking everything else, that it just makes sense in the context of the problem. All right, so let's get on with it. So the first one is just going to be talking about missing a length. So we have the angle of elevation from the ground to the building 100 meters away is 78 degrees. Find the height of the building. All right. The angle of elevation from the ground to the top of a building. Okay, so we have the ground, so I'm going to draw horizontal, right? Now again, you can see this angle of elevation, right? So again, we know from a horizontal, which is going to be the ground, is 78 degrees. Right? And we can see that that creates a nice little building, right? You can draw a building if you like to, put some windows, whatever you like to do. But again, if you recognize that building, then that's going to create a 90-degree angle. We're trying to find the height of the building, so I'm just going to label that h. And I'm going to say h equals the height of the building. Okay, so, and it says 100 meters away. All right, so again, now we just look at our trigonometric functions that we, trigonometric equations that we could use. So I have an angle, I have the opposite side and the adjacent side of that triangle, right? You can see this right triangle. So therefore, I can say the tangent of 78 degrees is equal to h over 100 meters. So therefore, h equals 100 meters times the tangent of 78 degrees. Now you can leave the meters out if you wanted to write that in there. Just make sure that you put those back in, because that's another common mistake. Like, it matters if it's 100 meters or 100 inches, right? So just make sure that if you are provided units, which for most of the time for word problems we will be, make sure that you have units in your answer. So, and then also when you're typing this into your calculator, if you're using a scientific calculator or a graphing calculator, make sure that it's in degree mode. So I'm going to do 100 times the tangent of 78, and that's going to give me 470. And now I did not say what to round, so therefore we're just going to round to our nearest hundredth. So we're going to say the height is going to equal 470.463 meters. And again, that makes sense in the context, right? 78 degrees is actually a pretty big angle. If it's already 100 meters away, 470 makes sense. All right, the next one. It says a Navy cruiser detects a submarine that is directly 3,500 feet away from the cruiser. The angle of depression from the cruiser on the top of the water to the submarine is 33 degrees and 45 minutes. How deep is the submarine? All right, so again, we have a ship. So again, we have water. We have a ship, right? We have a submarine. Okay, so it says there's an angle of depression. So we're going to say the water is our horizontal. We have an angle of depression from our Navy ship to the cruiser. The angle of depression from the cruiser on top water to the submarine is 33.45. Now remember, angle of depression is below the horizontal, where the angle of elevation, right, is above the horizontal. Here, the horizontal was the ground. Here, the horizontal is the water. Now again, this is 33.45 in 45 minutes. So let's go ahead and convert that real quick. So 45 divided by 60 is 0.75. So I'm just going to rewrite that as 33.75 degrees. Okay? And that's just going to make things a little bit easier for me. It says it's 3,500 feet directly away. So therefore, from here to here, they have that direct distance. Not a horizontal distance, but it's a direct distance. So that's going to be 3,500 feet. And then you go over and how deep is the submarine? So we're basically saying how deep is it? So deep. So D is going to equal the depth of the submarine. Okay. So again, we have our angle. Now based on this angle, again, you can see we're going to create a right triangle here. So we have the hypotenuse and we have the opposite side. So therefore, I'm going to use sine. So I'll just write out my trigonometric function. Sorry. I'll say the sine of 33.75 degrees is equal to my opposite side, which is D, over my hypotenuse, which is 3,500. Okay? And now I'll just multiply by 3,500 on both sides. And therefore D is equal to 3,500 times the sine. I'll just use parentheses here, don't really need it, but 0.75 degrees. All right, so let's go and type this into our calculator. 3,500 times the sine of 33.75. And I'm getting a distance here of 101,944.496 rounded. And again, remember that is in feet. And that makes sense, right? If it's that direct distance, if that depth is 3,500 feet, and the angle is 33, that makes sense that the depth would be about, 1,944 feet. So I would agree with that one. All right, the next one is the missing angle and distance. So you head out for a walk, due north for 5 miles. So if we think about this one, we're like, all right, well, if we're going due north, let's create a bearing here, right? Well, let's create our northeast, southwest. So we have north, east, south, west. All right, so we're going for a walk. Cool. 5 miles. So I'm just going to say, all right, there's 5 miles due north. Then you're going to turn east and walk for another 7.5 miles. So due east, going to be that way, right? And that's 7.5 miles. Now I'm not going to write miles. I'll just write that at the end. I just know that my unit is going to be miles. So let's just make sure I'll write miles so I remember. How far are you away and from where you started, and what bearing do you need to take to return home? All right, so if if I want to know, so here I am, right? So the question is, how far are you away from where you started? Well, if I want to draw a direct distance here, right, I need to figure out this length. Well, fortunately here, I have a right triangle. I recognize I can just use the Pythagorean theorem. So I'm going to call this D, and I'm going to say D equals the distance from home. Okay, so if we're going to find D here, I'll just do 5 squared plus 7.5 squared equals D squared. So therefore D is going to equal, as you would like to take the square root of these two. So I'll do, let's see, 5 squared plus 7.5 squared. That's not right. Jeez. I didn't use a decimal point. So I'm getting 81.25. And then if I take the square root of 81.25, I'm getting 9.014 rounded to the nearest thousandth. So 9.014 rounded to the nearest thousandth. And again, that's in miles. Okay? And again, since I have defined D, I don't need to write that in a full sentence. But you could always write your answer at the end as a full sentence. But that's why we want to go ahead and label it, so therefore we don't need to do that. All right, the next thing is find the bearing. Now this is where a lot of students get confused because they say, oh, well, let's go ahead and figure out what this angle is. And they just go about their day figuring out the angle. Now this angle theta, you could write an equation that tangent of theta equals 5 over 7.5, which is correct, right? Here's angle theta, here's the opposite side over the adjacent side. And then they say, all right, well, theta equals tangent inverse, that's good, you have to use the inverse, of 5 over 7.5. And they get very happy with themselves and they figure out that tangent inverse of 5 divided by 7.5, and they get 33.69. Now, in terms of our angles, which I don't think I mentioned, we're just going to round to the nearest whole degree, okay? So this angle ends up being 34 degrees. Okay, so I forgot to kind of mention that, but I mentioned in my classes that we're just going to round our angles to the nearest whole. So this becomes 34 degrees. Interesting, right? But again, so a lot of people say, oh, let's just take a bearing of 34 degrees. And this happened quite a bit. But again, think about this. If here you are, if you need to take a bearing, you need to create a northeast, southwest, right? So there's north, there's east, there's south. If you go on a bearing of 34 degrees, that's like right there, right? You're going to go farther and farther away from home. So you do not want to go on a bearing of 34 degrees. So we need to understand, we need to remember that bearings start at due north. This is 34 degrees. That is correct. But our bearing is going to start from due north and go from here to here. So how are we going to figure out that angle, right? That is our bearing. Now, a couple things we could do is we know that from here to here is 270 degrees. So I could take a 270 degrees and then subtract it from 34 degrees. So I have 270 minus 34 degrees. Well, that's going to be 236. So therefore I have a bearing of 236 degrees. Another way you could do this is you could also write this. You could also do 90 minus theta. Why 90 minus theta? Well, again, if you know what this angle is, right? This angle and that angle are complementary of each other. That means they add up to 90 degrees. So if you do 90 minus theta, right, which is going to be 56 degrees, then you could say a bearing of south 56 degrees west, right? South 56 degrees west, because 56 degrees plus 34 degrees is going to give us that angle theta. So we still need to find theta, that is correct. But theta is not going to be our answer. That's not going to be our bearing. We're either going to need to write it from due north or write it from due south 53 degrees west. I know it can kind of be confusing. I wanted just to provide both answers here because we didn't have any angles to go off of in this case, or any kind of bearing. So a lot of times, if we have a bearing, then we'll just use that same format as the bearing. But in this case, we don't have that. So therefore, both of those answers would be acceptable. All right, the next one. It says a missing angle. The sun casts a 51-foot shadow from a large oak tree. The tree is 39 feet tall. What is the angle of elevation? So again, we have an angle of elevation, right? So let's just draw. We have the sun. It's going to cast a shadow. So here's a tree. So sun casts a shadow. Okay, so now I kind of see what's going on. Now, a lot of times when I'm doing a problem like this, if it looks kind of difficult to like draw the triangle in there, I'm just going to redraw the triangle. Let's say, okay, I see my right triangle. Here's my right triangle. It's 39 feet by 51 feet, right? Because we don't measure a shadow by like that hypotenuse. We measure a shadow as far as its horizontal distance. And then it's asking us to find this angle of elevation. Well, again, the angle of elevation is going to be from a horizontal, which would represent the ground, right, going up to the sun. And that is what we are looking for. So we're looking for the angle of elevation. So theta is going to equal the angle of elevation. All right, so again, now I see, well, all right, so I created a picture. Now I drew my right triangle. Now I labeled everything. I defined my variable. Now I just want to see, well, again, what do I have? Well, I can create here a trigonometric expression, right? I can say the tangent of theta is equal to opposite over adjacent. Again, you don't need to use the units. You could, but I'm just going to leave them out. I'm just going to make sure, though, well, again, yeah, if you have feet, it doesn't really matter, because what happens with feet divided by feet? It goes to 1, right? So therefore, I have theta is equal to tangent inverse, right? Because, again, we have to solve for theta, right? So I have to undo tangent. So how do you undo tangent? You take tangent inverse. So tangent inverse of 39 over 51. Again, the feet divided out from each other. So therefore, I'm going to take the tangent inverse of 39 divided by 51. Tangent inverse. And I get 37.405. So theta is equal to 37.405 degrees. All right, 2 more examples to go. So this next one says, a small plane takes off from an airport traveling 100 miles per hour due west for 3 hours. Okay, now we gotta stop. So how long it was traveling does not tell us, right, how far it went. But we know it's going 100 miles per hour. So if it's going 100 miles per hour, so 100 miles per hour, and it traveled for 3 hours, therefore, you can say that it traveled for 300 miles, right? Kept this one rather simple because we'll get on to more complicated ones later. So it's going west. So again, let's just draw that. So we know we have a bearing again, right? So we're going to be dealing with bearings. Northeast, southwest. All right, so we're going west, and we're going to do that for 3 hours at 100 miles per hour, so that's going to be 300 miles, right? Before it changes course, heading due north for 4 hours. Okay, so now it changes course. So here's west. And now it's going to be heading due north. So now it goes up this way. So if it was going directly west, and we know it's never going to do actually a perfect 90-degree angle, you just got to have to play with us a little bit here. So that's going to be our 90-degree angle. And again, that goes for 4 hours, so therefore that's going to be 400. Now this one says, at that moment, how far is the plane from the airport? So again, here you are. How far are you from the airport? So that's going to be the hypotenuse. And at what bearing is the airplane from the airport? So here's the airport. Here's the airplane. If you remember, this is a little different. In this last one, when we took a walk, they're saying how far are you from where you are back to where you started. Now they're saying, what is the bearing, where's the bearing from where you started to where you now are, right? So we have to make sure we're answering the right question. We're going from here to here, not from here to here like in the last problem. So first of all, let's answer the distance problem. So let's say D equals the distance of the plane to to the airport. So the nice thing here is I recognize it doesn't matter, guys, if it's 3, 4, 5, 30, 40, 50, or 300, 400, 500. Those are Pythagorean triples. So again, if you could apply the Pythagorean theorem if you wanted to. But again, this answer is going to be, it's a Pythagorean identity, so this is going to be 500 miles. So now I can really focus my attention really on just identifying the bearing again. Now again, they're not giving us how our bearings were, so therefore I'm going to provide my answer in two different bearings. So the first answer is I still need to figure out this angle, theta, right? I can't answer my bearings if I don't have any angles going on. So I do have enough information though to find this angle, right? So here, this angle, I can say the tangent of theta is equal to 400 over 300. And again, we're not dealing with, like, we don't need to worry about the miles. So I'll say that's going to be tangent inverse of 400 over 300. All right, so let's do tangent inverse of 400 divided by 300, and that gives me 53 degrees. And again, I'm just going to round to the nearest whole here, so that's going to give me 53 degrees. Okay, so from here to here is 53 degrees. Now, if this is 53 degrees, what does it tell us about this angle, right? Because couldn't we do this to here, right? So what is that? Well, again, from here to here is 90 degrees. So I could say 90 degrees minus 53 degrees, right? Which is going to be 37 degrees. So I could say north 37 degrees west, right? You're going to go north 37 degrees west. Or our other bearing is we could just say, all right, why don't we start at due north and go all the way around? Now, all the way around, here's 90, 180, 270. So it's really 270 plus this 53 degrees. So, or we could say a bearing of, so we do 270, so that's going to be 200 and 270, so that's going to be 323 degrees. So this one is going to be 323 degrees, or we could say 37 degrees here, right? So either one of those bearings would be acceptable. All right, last problem that we covered in the class was find the angle for a changing angle. So in this case, we're going to have the angle of elevation from an observer to the bottom of an observation deck on top of a bridge located 200 feet away from the observer is 30 degrees. The angle of elevation from the observer to the top of the observation deck is 43 degrees, 50 minutes, and 36 seconds. What is the height of the observation deck? So basically, we have some observer, right? So we're going to draw a little stick person. And they're looking at a bridge. So, I don't know, here's the bridge. So you have an observation deck. I guess this is like a two-story one because it's like... So we have this first angle of elevation to the bottom of the observation deck. Now again, this is 200 feet away, right? Okay, to the bottom is 30 degrees. And then to the top of this deck here is going to be 43 degrees and 50 minutes and 36 seconds. So let's write that out in decimal form here. So let's do 43 plus 50 divided by 60 plus 36 divided by 3600. And I'm getting 43.843. So that's going to be 43.843 degrees. Okay. Now this is one of those examples where like right now this looks kind of complicated. Like where are my triangles? What am I doing, right? So in this case, what I'm going to do is I'm going to draw both triangles separately. So I'm going to draw the first triangle to the bottom. So here's 30 degrees, right? And this is 200. Now, this is going to be the height, but this is going to be the height to the bottom of the observation deck. So I'm going to call this H1. All right? Now let's draw the other triangle. Do a little bit bigger here. Oh, no. Doesn't it do that to me? Oh. This one has an angle of 43.843 degrees. All right, now this is the height to the top of the observation deck, right? So I'm going to call that H2. Now you could use them different ones if you want to. You just want to make sure that you understand that like H, these representations, because again, we're really only solving for H here, which is going to represent the height of the observation deck. So if here is H2 and here is H1, we want to find H, right? So H equals the height of the observation deck. So since what we're doing here is we can define this, then H is really just going to equal H2 minus H1. All right, so now we can define, so we've defined H, right? And we define H2 and H1 as being the difference of them is going to provide us with H. So now let's go ahead and see, well, can we solve for H1 and H2? Because if I can find H2 and H1, then I just subtract them to find the height, right? Well, fortunately, you can see here, yeah, this is again 200. So you can say, oh, so I have opposite over adjacent, opposite over adjacent. So I can say the tangent here, 30 degrees, is H1 over 200. And here, I can say the tangent of 43.843 degrees is equal to H2 over 200. So now, to solve for H1, all I'm going to do is just multiply 200 on both sides. I'll just write it out, might as well have room. So I have 200 feet times the tangent of 30 degrees. And here I have H2 equals 200 feet times the tangent of 43.843 degrees. Okay, so now let's just go ahead and figure that out, multiply them. So I have 200 times the tangent of 30. So that's going to be H1 equals 115.47 feet. And H2 equals 200 times the tangent of 43.843, 192. So 192.081 feet. Okay, and again, before we go and subtract them, does that make sense, right? Does it make sense for those two side lines where they are? Yes, H2 should be bigger than H1. Awesome. So therefore, I'm just going to subtract H. I'm just going to do 192. Now, I am writing down the rounded answers, but it is really important that when you are using a calculator to not use rounded answers here, but to use all the decimal places that you have here. So I'm just going to take this answer and I'm going to subtract it from the full answer that I have already stored in my calculator, just to make sure that there's not going to be any rounding answers. One thing we will work on later is going to show you how to store them, so therefore you're not using any rounding. And again, I have the default is rounding to nearest thousandth as our term. But again, we just want to make sure that we're always using as accurate of answers as possible. So 11 feet. So at least from the problem that I have here, or at least then we go and solve, and you can see here we have a height of 76.611 feet. So that was it, ladies and gentlemen. That basically covers, again, our solving word problems in right triangles. So I'd love to kind of hear from you if this was helpful. I know word problems is difficult, and a lot of students do not like this chapter just because they have to read. And some of these problems you can see, they cause multiple steps. But the main important thing, I remember when I was in high school, draw the picture. And again, the nice thing about today's lesson is that there's going to be a right triangle. So whenever you're drawing your picture, which sometimes it's hard, right, to try to figure out what's going on, but you want to draw that picture and just know that you need to create a right triangle. And then based on the measurements that you have, you can write a trigonometric equation. And then from there, you can identify the missing part. So I hope this was helpful. And I'd love to hear from you on any questions that you have or anything else that would be helpful to include in the lesson. So look forward to seeing you on the next video. And yeah, I look forward to seeing you on the next video. I don't know why I'll just keep on scrolling back up, but that's it. So I'll see you then. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on the law of sines. Now, this is the second lesson in our chapter for applications of trigonometry, and this is actually a lesson that I went through in my classroom that I'm going to work through now with you so you can hopefully better understand how to apply the law of sines. So what we're going to cover in this lesson is how to determine the missing sides of an oblique triangle when given angle side angle as well as angle angle side. We're going to talk about how to determine the types of triangles given oblique triangles, also known as the ambiguous case. We're going to solve the missing measures using the ambiguous case. And then lastly, we're going to end up with finding the area of an oblique triangle. Now, you might not be familiar with the vocabulary of an oblique triangle, so that's what we're going to kind of discuss here, or at least to kind of get started. But the way that I kind of started my lesson is I just wanted to give my students a triangle that kind of looks like an equilateral triangle, but then just have them understand, like, how would you write the height? So basically, if we have a triangle, if we want to write the height, we're going to draw a perpendicular line. Now, again, we don't know that this is a perpendicular bisector. We just know that we have a line representing the height that can be perpendicular. But from there, we actually have two right angles. And actually, let me go back to my red here. So by doing that, though, by creating a perpendicular line, we have two right triangles. So from there, what I can do is I can write a trigonometric ratio, right? I can say the sine of A is height over opposite, and therefore I can solve for H. I could also say over here in this triangle, the sine of C is opposite over hypotenuse. I'm seeing the H. H is height, not hypotenuse. So opposite over hypotenuse, and I could solve for H as well. So what we did is we recognized here that H is equal to C times sine of A, as well as A times sine of C. Well, since H is equal to two different expressions, I can set those expressions equal to each other. And that's exactly what I did here. So I started this with C times the sine of A equals A times the sine of C. Now, obviously, to try to say, well, I have C's and A's, why don't we put them together? So I divided C on both sides and I divided an A on both sides. And what I got was this proportion where sine of A divided by A is equal to the sine of C divided by C. And that is what we call our law of sines. Now, again, if we wanted to talk about B, that would also be proportional to these two ratios. All we need to do is just kind of rotate our triangle to its side and then find another height. But the important thing about the law of sines is this ratio of the sine of the angle to its corresponding side length is going to be proportional for all the angles and side lengths. So now that is going to be true for oblique triangles. It actually works for right triangles as well. But the reason why this is going to be helpful for us is because for right triangles, we have Pythagorean theorem as well as the trigonometric ratios, right? You can see that I could not use the trigonometric ratios until I created a perpendicular line. Then once I had a right angle, I could use my trigonometric ratios. So when we have an oblique triangle is basically just a triangle that does not contain a right angle. So there's two ways that we describe oblique triangles. We can describe them as an obtuse triangle. That means they have one right angle. Or we can call them an acute oblique triangle, meaning that they have all three acute angles. So we're going to use the law of sines to help us find the missing measures when we have oblique triangles. Again, absent of a right triangle or right angle. Now, the important thing to understand from the law of sines, though, is understanding the labeling of oblique triangles. So previously, when we looked at a right triangle, there's a couple different ways that we labeled right triangles, right? First of all, you have the famous a squared plus b squared equals c squared, right? Legs and hypotenuse. Then we went into trigonometric ratios, okay, where we basically were talking about given an angle theta, we're going to have the hypotenuse, the opposite, and the adjacent. So if you understood how to label right triangles this way, then you were good for right triangles. Now, oblique triangles, we get a little bit more exact, and meaning that we give our triangles, some labels or some letters like A, B, and C. And then the the side length that is opposing that angle or corresponding to that is going to be the lowercase angle. So if here's big A, that's going to be A. If this is big B, then this is going to be little b. And then the C's always get messed up because, you got to make sure you're doing a little c, not a big C, but that would be little c. Okay, so now again, not all triangles need to be written like A, B, and C. And obviously what you'll see through this lesson is I will be moving the angles around. But typically, unless I know that it's an obtuse oblique triangle, this is kind of like my go-to triangle, an acute triangle that looks like this, and label it that way. However, you'll see again, I will deviate from this because I do not want students to be caught up in, oh, A has to be here, or the triangle has to look like that, because that can be dangerous for students, because that will start getting them mixed up once we started getting into some problems. All right, so I started the lesson off with just kind of working through a angle side angle. All right, so basically here's the triangle that the students were, or here's the information the students were given. You can see how I created my triangle, right? So I had A, B, and C, just like kind of how I said I assume, that's what I start with. I don't have angle C, but I have side length C, which you can see is right in between the angles A and B. Now, the important thing when we're looking into the law of sines here is that we have to have a proportion. We have to have a ratio. And in this case, we don't have a ratio, right? You have to have an angle to its opposing side length, which we don't have here. So what I did was I could figure out C, right? If you have two angles, then you can figure out the third angle, right? The interior triangle angle sum theorem, right? All the angles of a triangle add up to 180. So what I did is I just quickly figured out what the value of C would be, which ended up being 37 degrees. And now I have a ratio. One thing I forgot to mention that I mentioned to my students, we have two proportions here, right? And again, this is equal for all three of these. Again, like you're only going to use obviously a proportion, a ratio equal to a ratio. You're not going to have all three of these set. But what's the difference between these? Why would I provide you with both of them? And the reason being is typically when we're solving for something, we do not want to be solving for something in the denominator. So when we want to solve for an angle, we're going to want to use this proportion because you can notice that our angles are inside of the numerator. However, if we're trying to find a side length, then we're going to want to use this proportion because the side lengths obviously are in the numerator. So a quick little tip that I did not cover when I was going over there. All right, so now I have a proportion, right? You can see that I have side length C and angle C. So you can see that ratio right here. And then I'm either going to solve for A or B. It doesn't matter. You just really kind of go with one. I show my work in here because for the next ones, I'm not going to show my work. I'm going to try to move through this a little bit quickly. But basically to solve for A, I just multiplied by the sine of 61 on both sides. And then this is what I basically plugged into my calculator. Now to do this chapter, you're going to want to make sure you have a scientific calculator or at least a graphing calculator. And since we're dealing with angles that are in degrees, you're going to want to make sure you're in degree mode. Now we're finding a side length. I told my students to round to the nearest thousandth, but obviously depending on the question, test, quiz, homework, that could always change. But if I don't mention how to round it, I said just to round it to the nearest thousandth. That might not be what your teacher wants or what you're used to. So you can just go ahead and adjust the answers as you need. But once I find this side length, well then I can just do the exact same proportion here to go ahead and solve for B. One thing I would recommend though is don't use B over sine of 82 equal to this new side length over sine of 61 because again, this is a rounded answer. You could use the exact answer, but again, it's never going to be exact. It's still always going to be an approximation. So it's always best to avoid using approximations in your calculator or to calculate answers when it is possible. So since I was provided or since I originally had this ratio 23 over sine of 37, you can see why I used that twice. All right. Okay, so let's go and do another problem here. Now in this case, wait a minute. That's not a angle side angle. Oh yeah, it is an angle side angle. Jeez. So in this case, everything's kind of written a little bit differently, right? And that's okay. So what I'm going to do is I'm going to still draw the same triangle, but I'm just going to put B here, and I'll put C here, and I'll put A over here. Okay? You don't need to do it that way, but you could do it that way. Now, I recognize that here I have 110 degrees and 30 minutes. Well, just remember, 30 minutes is like half a degree, right? Just like 30 minutes is half of an hour. So to figure out the decimal version, you're just going to take, well, I have 30 minutes out of 60, right? Because 60 minutes would give you 1 degree, just like 60 minutes gives you an hour. But you don't have 60, you have 30 of them. So 30 divided by 60, hopefully you recognize here, is going to be 110.5 degrees. All right, so I'm just going to use the decimal version here. So 110.5 degrees. And then C is going to be 41. And then we don't know A, but we know this is going to be 5 meters. Okay, so now we have a measurement, and that's okay. We're just going to want to make sure when we give our final answer, all of our side lengths we're going to want to make sure are in meters. So therefore, let's go and find A. So that'd be 180 degrees minus 110.5 minus 41 degrees. And therefore, that's going to give me 39. I'm just going to type into my calculator, so therefore I don't make a mistake, a silly mistake, and then get the whole problem wrong. So I'm getting 28.5, which 60, 70 looks good. So let's say that's going to be 28. Okay, so that's going to equal 28.5. Okay, so I'm just going to erase that and just say, all right, A equals 28.5. All right, so now I have a proportion. So therefore, what I'm going to do is just either solve for B or C. It doesn't really matter. What I told my students to do in class is basically provide me with the equation, and then you can provide the answer. So they have the triangle. They showed me the equation, and then they gave me the answer. That's in degrees. And then the next one is just providing the ratio. So let's do C here. So I do C over the sine of 41 degrees is equal to 5 meters over 28.5 degrees. Okay, so then to go ahead and solve this, all I'm going to do is multiply a sine of 41 on both sides. So therefore, on my calculator, I'm going to type in a 5 times the sine of 41. That's not what it. 5 times the sine of 41. And then I'm going to divide that by, the sine. I don't know why I didn't write that. Divide that by the sine of 28.5 degrees. So sine of 28.5. And that gives me a 6.87. So when I round that, let's see, round that to the nearest thousandth, that's actually going to be a 6.875. Okay. One thing also, just to kind of make sure that you're aware of, like a lot of times when students are typing these into the calculator, they're very prone to making a mistake. So always go back into your triangle and like make sure like the side length makes sense. Based on these triangles, like we should not get like, I don't know, maybe if I miss a decimal point, like 68 or 6,500 or, 0.2, those shouldn't be values based on the information we have for this triangle. So just make sure when you're calculating your answers, make sure everything kind of makes sense, because it's very easy to type something into a calculator incorrectly and then get the whole problem wrong. Right, so then the next ratio, let's use B. So I'll have B over the sine of 110.5 degrees is equal to, again, 5 meters over the sine of 28.5 degrees. All right, so now we're just going to do the same thing here. So I'm just going to do 5 times the sine of 110.5 and then divide that by the sine of 28.5. In this case, I get B is equal to 9.815. Okay, which makes sense. And again, that's going to be meters. And that's basically really all we need to do for those problems. So it's, if you don't have a ratio, when you're doing the law of sines, you got to make sure you have a ratio. If you don't have a ratio, look to see what you need to do to obtain a ratio. In this case, we just needed to subtract our other two angles from 180 to find our missing angle. There we could now find the ratio. Then the next example is actually if I actually was to give you a ratio. So in this case, we have A equals 46 degrees, C equals 61. So in this, and C equals 12. So when I kind of draw this, A, B, and C, you can see that I automatically already have a ratio. So therefore, I didn't need to do any extra work. And in this case, so I go ahead and, apply, set up my ratio, multiply it, I get A here. But now, once I find that, so I have that side length A, well, to figure out B, I have no information here, right? So therefore, what I need to do in this case is subtract my A and my C from 180 to give me 73 degrees. And now I can go ahead and use the law of sines to find my missing side length, B. So let's go ahead and do another example like this. And I guess I'm making sure that I'm doing all the ones. I guess I gave my students, I didn't even think about that I gave myself all the ones with degrees, minutes, and seconds. So, all right, let's go ahead and get through this one. So again, draw the triangle to understand what it should look like. So let's call this one B. Let's call this one C. And then we'll have little c here. So this is going to be 12 inches. All right, now this is going to be 16. So let's see, B is going to be 16 plus 25 over 60. So let's go and figure out what that is. 16 plus 25 over 60. And that is going to be 16.416. Now that's going to be repeating. So what I'm going to do is rather than just like round that to, 0.417, I'm actually going to store that as an answer. So I'm going to store that as, let's see, alpha B. So on your calculator, most calculators for scientific reading, they have a storing feature, and you can store them into the memory of the calculator. So I'm going to store this as alpha B because I don't want to round until the very, very end. Then I'll go ahead and calculate C. Now in this case, I'm going to have a 103 degrees plus 15 out of 60, here minutes, plus 30 out of 3,600 seconds. Right? Because there's 3,600 seconds in a degree, and therefore we only have 30 of them. So that is going to be the notation for degrees. So I'll do 103 plus 15 over 60 plus 30 divided by 3,600. And that is going to give me 103.2583. And it looks like, I don't know, that could be repeating as well. So what I'm going to do in that case is, again, store this answer. Okay, so when I'm storing something, what I'm going to do is I'm going to put brackets around that. Okay, so that's going to tell me it's now a stored answer. So I'm going to hit store alpha C. Okay, so now I have these two angles stored as alpha B and as alpha C. And I recognize here I have a ratio, right? So therefore, let's go ahead and find side length B. So therefore, I'll do B over the sine of alpha B. So I'm going to use those brackets to tell you that it was stored. And then 12 divided by the sine of C. And again, if you want to know where that stored answer is, you can just look at the stored answer and say, oh, that's what it's equal to. Or at least that's the rounded version. So in this case, I'll just do 12 times the sine of alpha B. And then I'll divide that by the sine of alpha C. 1,603. So alpha B, yep, alpha C. Okay, so in this case, I get B is equal to 3.48. That doesn't seem, sine of alpha B. Yeah, okay. All right, so 3.4, I'm sorry, that's going to be 3.484. All right. And therefore now I can find A. So A is going to be 180 degrees minus stored B minus stored C. So I'll do 180 degrees minus alpha B minus alpha C. And that's going to give me a 60.325. So it looks like that got rounded to 3 decimal places automatically, or at least got simplified to 3 decimal places. So therefore, I don't need to store that answer. 60.325. I'll just go ahead and write that in there. Obviously, if it kept on going or repeating decimal, then you'd want to store A as well. But in this case, I'm just going to have A. Oh, and this is in inches, isn't it? So A over the sine of 60.325. is equal to, and let's again use 12 over sine of C. So 12 over the sine of C. So in this case, I'll just do 12 times the sine of 60.325 divided by, that's a stored C, the sine of alpha C. And I get 10.71. All right, so A is going to equal 10.712 inches. So you can see it's not really, obviously this triangle is not really drawn to scale, obviously because we have a big obtuse angle, and you can see that this measurement is going to be a lot smaller than the other ones. But again, still you can kind of see these measurements would make, some sense if we were to kind of maybe rescale or redraw the triangle. All right, so now we kind of got our feet wet with the understanding the law of sines. Now let's kind of get into the word problems. So the word problems for law of sines was basically, again, what we want to do is draw the picture, set up the triangle. Now in this case, we're looking for the oblique triangle, and then we're going to look for the ratio. And if we don't have enough information for the ratio, we need to be able to see what can we do to create a ratio. So this word problem says 2 observers, 1.6 miles apart, see a hot air balloon between them in the air. So let's go ahead and immediately draw 2 observers. So we have observer and observer. And they see a balloon. So I'm just going to, there you go, draw balloon. Okay. Hot air balloon. Now it's in between them. Now it looks like we don't know if it's directly in between them. It does not say. All it says that there are angles of elevation of 36 degrees and 28 degrees. And I think that hopefully is a kind of a giveaway that if it was directly in between them, the angles of elevations would not be the same. So therefore, this is going to be 36 degrees. This is 28 degrees. And how far are they apart? Oh, it doesn't matter. Oh, they're 1.6 miles apart. So they're 1.6 miles apart, and we need to figure out the height. So again, we want to label what we are looking for. Okay, so we're looking for the height. Now, the problem is, based on this information, I need to create a ratio. I have no idea how long this is, no idea how long this is, and I have this length. So if I have this length, is there anything I can do to figure out this angle, right? Because I have to get a ratio. Well, thankfully, I already have 2 sides of my triangle, right? Or 2 angles, I'm sorry, of my triangle, 36 and 28. So I'm just going to go ahead and figure this to be 180 degrees minus 36 degrees minus 28 degrees. So I'll do 180 minus 36 minus 28. And that's going to give me 116. All right. So if that angle is 116 degrees, now I have a ratio. Now, again, that does not help me with the height, but it's important for me to understand the height is actually part of a right triangle. So let me draw one more triangle here. And let's just do this one. So if I have 36 degrees, I don't know what this length is. You do not want to make this assumption that it's halfway in between because they don't have the same angles of elevation. So that doesn't make sense. We don't know the height. That's what we're trying to find. Now, the only other side length is this. Now, this is the side length of an oblique triangle. Well, if I already have a ratio, I can find that other side using the law of sines. So what I'm going to do is I'm going to say, all right, 1.6, let's call this one A, and let's call this one B. That means this is going to be little b, right? So I can say 1.6 over the sine of 116 degrees is going to be equal to B over the sine of 28 degrees. Okay. So now you're just going to multiply, 1.6 times the sine of 28 and then divide that by the sine of 116. And when doing that, that's not right. 1.6 miles. Oh, what am I doing? That's not hundredths. That's 116. What am I doing? Yeah. That's 1.6. 1.6 over 100 sine 16 is equal to B over that. Oh, yeah, I guess that is right. That is right. That's fine. Okay, so B is equal to 0.8357. Now, or 6, yeah, because I'm going to round to the nearest thousandth. However, I'm going to round this. You can see this is multiple digits, so I'm going to store this as an answer, okay? So I'm going to now label this as a stored answer B because I don't want to round until the very end. So I'm going to hit store, and then I'm going to just take that as alpha B. But now, if you look at this triangle, you have sine of 36 degrees as opposite over hypotenuse, right? So you can say sine of 36 degrees is equal to H over stored answer B. So then all you got to do to find H is just going to be stored answer B times the sine of 36 degrees. So then I'm just going to type in the sine of 36, close the parenthesis, times alpha B. And in this case, I'm getting H is going to equal 0.491. And that's going to be in miles. right? It makes about sense. Like this is 1.6 and that's, 0.8. Then this height is obviously going to be a little bit shorter. So 0.49 makes sense. It's not like 5,000 or like 0.0003. So you can see here how we had to create our ratio, but then also just by solving the law of sines isn't our answer. Like we need to make sure we understand the height of the balloon, right? Which I should also define the variable, which I forgot to. H equals the height of the balloon. Okay, because I make sure I solved it, but I didn't define the variable. All right, next problem. The course of a boat starts as point A and starts at point A, and let's fix that. And proceeds in the direction of south 53 degrees east for some distance to point B. Then in the direction of south 39 degrees west to point C, where it lies 8 miles directly south of point A. What is the total distance of the boat traveled? All right, so whenever we have a word problem or we have a bearing, I always tell students to draw the compass heading. So we have this, it's going to be south 53 degrees east. So I'm just going to draw this compass heading. I do a nice one there. I did. Okay, so we have north, east, south, west. All right, so it's going to go south 53 degrees east for some distance to point B. So again, it starts at A. And then let's just go, I don't know, to here. And then let's call this B. Then it says, then it changes direction to south 39 degrees west to point C, which lies directly south of point A. Okay, so we're going to do another compass heading. So, again, northeast, southwest. And then point C, they said, is directly south of A. So we're going to call this C. And now you can see we have our triangle. All right. So let's kind of go through our angles. So we did south 53 degrees east. So there's that angle. And then this one is south 39 degrees west. Okay. And the only thing we know that the distance from point C to point A is going to be 8 miles. All right. So again, we have an issue because we do not have a ratio, right? We have one angle and we have one side length, but we don't have a ratio. Now, the important thing is whenever you have a compass heading, we know that those create parallel lines, right? North-south is parallel with north-south. So therefore, what I'm going to do in this case is I'm going to look at my parallel line relationships, right? Remember parallel lines in a transversal, alternate interior angles, corresponding angles, alternate exterior angles. All of those can come about. So if these two lines are parallel and I have 53 degrees here, well, alternating on the other side of this transversal makes that 53 degrees. Now, again, that's not inside the triangle, but I recognize that that could still be kind of helpful. Now, the other thing you could do is I can say, well, then if that's 39, then this is 39, right? And then, so yeah, you could use this as like complementary angles. Like if that's 39, then you know that this has to be 51 degrees, right? But you could also just say, well, if this is 39, this is 53, I can figure out what those angles are, right? I don't need to really do any more. So the nice thing is just knowing that you have these as alternate interior angles, you can now figure out that angle. And again, we need that angle because that's going to be opposing to our 8 miles. So let's see, we're just going to do 180 degrees minus 53 minus 39. So I'll just, again, type in my calculator here. Just because now I'm dependent on my calculator like all my students. Once we give them, we're like, oh yeah, there it is. So that's going to be 88 degrees. Okay. All right, so now I have a ratio. And again, we basically need to be able to solve for these two lengths. Now, we could call this little c and then call this one little a. Right? So let's go ahead and do that. Let's solve for C here first. So we'll do C over the sine of 39 degrees is equal to 8 over the sine of 88 degrees. And now we'll just go ahead and multiply by the sine of 39 on both sides. So I'll do 8 times the sine of 39 degrees, and then I'll divide that by the sine of 88. And that's going to give me 5.038. And again, remember that's in miles. And then we'll do A over the sine of 53 degrees is equal to 8 over the sine of 88. Okay, so we'll just multiply by the sine of 53 again. So that's going to be 8 times the sine of 53. And then divide that by the sine of 88. And therefore, A is equal to 6.393. And again, remember that's in miles. Okay, so there you go, ladies and gentlemen. That's basically the gist of the law of sines when we're dealing with a ratio, or at least a triangle that we can create a ratio. Now we're going to move into the lovely situation where we cannot confirm if we have all the information needed to identify what the triangle would be. And that is what we call the ambiguous case. So the ambiguous case is if we have two sides and a non-included angle are given, which is also called the side-side angle triangle. 3 situations can occur. So we can have no triangle exists, which is this one. We could have a right triangle exist, which would be that one. We could have 2 triangles exist, which is usually the confusing one. Or we could have the one triangle exist. So the first 2 examples, usually people, once we kind of work through this, they understand it. Really the difficult one, is it this one triangle case or this 2 triangle case? So what I do with my students is I had a conversation. I said, all right, guys, let's look at this document. And let's say, how does really the height of the triangle, how does that like relate here to the type of triangle that we have, right? If there's no triangle, how does the height of this proposal triangle like relate to it, right? Like here would be the height, right? How does the side length relate to the height? Same thing here. How does H relate to A? Or here, or here. And the point that we wanted to see was that when the opposing side, this A, was shorter than the height, no triangle existed. When H is equal to A, you can see that one right triangle exists. The one thing that we got to make this confusing difference here is when A is larger than H, which is not true for these two. So when A is larger than H, you either have 1 or you have 2 triangles. So what is the difference between these? Well, the difference is, in this case, you can see that A is larger than B. In this case, you can see that A is smaller than B. So what I did is I kind of summarized all of this into some cases. All right. And basically what we want to do when we're trying to identify the type of triangle we have for the ambiguous case is to find the height. Now you might recognize that formula for the height because that is exactly what we did at the beginning of class. H equals B times sine of A, right? If you create a nice little right triangle here. Now I did label the triangle differently than what is shown here. I did have B up here and C over here, but we're going to stick with this being angle B. So therefore that's little b. But if you're given this information here, you can identify that the height of this triangle is going to be the sine of A is opposite over hypotenuse. And when you solve for H, you get H equals B times sine of A. The way that I have this memorized is when you have, angle, side, side, right? Angle, side, side. Whatever angle you have that ratio with, your corresponding angle and the side, then that's going to be your corresponding angle. This would be your included corresponding side. This would be like your included side. So you're always going to take your included side times the sine of your angle. Now, I always hate writing like that, so I'm just going to write it because I know some people are still like, oh, side, side angle, side, side angle. Whatever your angle is, times that nearest side. But again, you can kind of see this relationship. Once you find the height, right, just relate it to A, okay? Now again, the letters is not what's important. What's important is understanding the side length, how it relates to that other side. And again, really the one where students really get confused here is when A is larger than H, because you need to determine is A bigger than B or less than B. And again, this is when A is acute. So if you have A is obtuse, it actually gets even easier. When A is obtuse, A has to be small. If A is smaller than or equal to B, then no triangle exists. And if A is larger than B, then one triangle is going to exist. So yeah, so that's just kind of important to understand. And again, like that makes sense. Like, I don't know why I didn't do this as a larger triangle, like an obtuse triangle. I should have redrawn that. So like if here's A, right? Here's B, or sorry, let's put that as B is over here. So therefore this is A and this would be little b, right? So you have angle, side, side. So if A is larger than B, then you can see one triangle exists. But if this ends up being shorter and this is an obtuse angle, like you're not going to have a triangle, right? If this was like shorter than B, no triangle will exist. Or even if it was exactly the same measure as B, there would be no triangle exist because therefore then it'd have to be a right triangle. And if this is obtuse, then it obviously can't be both. All right, so one of the types of problems we'll talk about is the ambiguous case, is how to determine if the measure is 1, 2, or no triangles. I will be a little bit more detailed in this case as far as identifying if it's a right triangle as well. So the main thing I like to do is just kind of draw the picture of the triangle. So I'll have C, so we'll have 75, this is going to be 10, and this is going to be 12. So then I like to find the height, which in this case is going to be 12 times the sine of 75 degrees. And let's see, that's going to be 12 times the sine of 75. That equals 11.6. Okay, so you can see that 10 is shorter than the height. So therefore, no triangle exists. This next one, you can see it's obtuse, so I don't need to worry about the oblique triangle happening, but I know that this is going to be 148 degrees right there. And therefore that's 8, and that's going to be 16 or 25. Again, if you remember, this triangle doesn't make sense how it's written, right? If this is your opposing side and that's smaller than that side, there's no way a triangle is going to exist. So again, this is another example of no triangle exists. On the next one, let's go and draw this here. So this one would be B. Therefore, this is 9.9, and this is 8.1. So let's go and figure out the height. So I know this is bigger than that one, so I know it's not going to be 2 triangles or 1 triangle, actually. Or actually, I'm sorry, we know it's not going to be 2 triangles, and it should be 1 triangle. Let's just go ahead and confirm. So let's go and figure out the height. So that's going to be 8.1 times the sine of 63 degrees. So 8.1 times the sine of 63, and that's going to equal 7.2. Okay, so again, since the opposite side here is larger than the height, we know a triangle exists, and since it's larger than the other side, you cannot create more than 1 triangle, so therefore that's going to be 1. The next example here, we have another acute angle. So let's go and draw this. Oh, I didn't do those. So here I'm going to have 12 degrees, okay? And then my opposing side is 28. And then this one is going to be 8. BB 8.1. Yeah. All right, so now I'm just going to do, so obviously it's going to be either be 1 or none. So let's go and figure out the height. So that's going to be, that's going to be 8 times the sine of 12 degrees. So I'll do 8 times the sine of 12 degrees. That's going to be 1.6, which is obviously bigger. However, that cannot rotate into both of them. So therefore, there's only going to be 1 case that's going to work in that one. This next one, we're going to want to relate this to our decimal form. So I'm going to do 23 plus 34 divided by 60. Oops. Plus 41 divided by 3,600. And that gives me 23.578. Now I'm going to go ahead and store this. Okay, just so I use an exact answer. So I'm going to say store as alpha A. And then my triangle is going to look here let's say, so that's going to be 2, and that's going to be 5, and this is going to be, 23 degrees roughly. So let's go and find our height. So h is equal to 5 times the sine of 23 degrees. So I'll do 5 times the sine of alpha a. Actually, let's use the stored a, so we know that we're using the stored answer. And when I do that, I get 1.99999, and I think that's going to be just a rounding error. You can see that that's actually exactly the same as equal to 2. So therefore, this is going to turn us into a right triangle. 3.2, C is 95 degrees, so let's go ahead and draw a right triangle here. All right, so there's going to be my C. This would be 10, and this is going to be 3.2. So again, once we know that this is a obtuse triangle and this side's gonna be larger than that side, we know it's going to be 1. Now I'm looking at this and I say, uh-oh, there's a mistake here. Now, obviously that's not gonna be my second case. This was supposed to be my 2 case, so I think I made a mistake. I need to change this up. If my height here is 7.2, I think this should not be larger because then we know it's gonna be 1 case. I think I wanted this to be 7.9. So if that's 7.9, and I'm sorry, I'm going to go back and change. I thought I'd worked all these out. Okay, but now you can see 7.9 is larger than my height, so therefore we know a triangle is going to exist, but it's smaller than my other side, so therefore this was supposed to be my 2-case solution. So sorry about that, but I'm going to go and change the answers there. Okay, then on to the last one, which is the ambiguous case, which I used to teach a lot, but it takes so long to be able to do it. And so what I did is I really didn't kind of go through an example. I wanted to provide at least one example so therefore students can see what I'm doing, but I don't really want to cover any more than that. So basically we have our side lengths, right? You create your triangle. The problem is when you figure out the height, it's 8.4. Now 8.4, the opposing side length is larger than 8.4, but it's shorter than the adjacent side, right? So therefore you don't know if 10 should look like that or like that. Right? So it has to be 2 of the 2 cases. You either have case 1 or you have case 2, the acute triangle or the obtuse triangle. There's not enough information for you to determine which one is which. So the first thing you do is just kind of go off of, let's just assume it's the acute triangle. So therefore you create your ratio. Now again, notice you're finding the angle B, right? So when you go ahead and create your proportion, you got to make sure you're going to want to put the angle, the sine of your angle B in the numerator, and you go ahead and solve for that. Then you're going to go and solve. You're going to use your inverse operation, and therefore you're going to get angle B right there, ends up being 57.409. Then you can subtract that from 180 or subtract your angle, 37, plus your B to be able to find your last angle, which is C. Notice I'm putting the brackets around everything because I'm storing everything in my calculator. So the other thing that's difficult about this is there's just a lot of storing. Okay, so once you find angle B, right, you already have angle A, and then you find angle B, so you're subtracting them from 180 to find angle C. And then again, you create your proportion to find side length C. Notice how I use the proportion where my side lengths are now in the numerator. Then we got to go and figure out case 2, which is the obtuse angle. Now again, we don't know if it's the acute, if it's case 1 or case 2, like we don't have enough information. So we got to look at what is the relationship between B and B2. Well, the relationship between B and B2 are they are supplementary angles, meaning they add up to 180. So that means I already found B. If I want to find B2, which would be the obtuse angle here, all I'm going to do is I'm going to take 180, subtract it from B, which again is still stored in my calculator. And that gives me an obtuse angle, right? Right there, 122 degrees. And then I ended up storing that as a different variable D. Now, again, you could replace that with B since you're already done with case 1. But just to keep things in case I wanted to go back to them, I stored it as a different variable D. That's why you can see B2 and D. You can see it's all defined here though. Well, now I have B2 and then I already had A. So then I can take those 2 answers, subtract them from 180. So I do 180 minus C minus B2, which is stored as D. And that gives me another acute angle, 20.4, which I stored as E. Then the last thing we need to do is find the third side, which is going to be C over sine of E equals 10 over sine of 37. And therefore your C is going to equal 5.795. Boom. Okay, so now let's actually go through an ambiguous case to be able to find the missing measures of both triangles. So the first thing we're going to want to do is actually draw the triangle to kind of see what it's going to look like. So we have, here is our angle B, and then this side length is going to be 7, and this is going to be 10.5. All right. Now, again, if we didn't know this was the ambiguous case, we could always check out the height. And to do that, I would just do 10.5 times the sine of 35 degrees plus 6 minutes divided by 60. And that's going to give me 6.037. I don't need to find the height, but what I can recognize here is that this side length is larger than the height, but it's smaller than this case. So again, to like kind of visualize this, we have this angle is defined, and we know that this side length is defined as well as this side is defined, but we don't have this angle defined, nor do we have these two angles defined. So that's why we don't have enough information. We don't know, is this an obtuse angle or an acute angle? Now, again, these are going to represent here C. So we could call this C1, and then we could call this angle C2, right? So therefore, this is going to be B. Now, again, last thing is notice how I created the triangle. I always create it with a angle side, side. All right. I always create the ambiguous case just like that. And then I just move around the letters as I need. Now, the first important thing is to just find case 1, just like we did before. So I'm just going to do case 1 right here. So it's usually easiest just to, pick your side and say, all right, let's just assume that this is an acute triangle, an acute oblique triangle, and therefore we can just solve from there. So what I'm going to do is we're going to find C1 here. And so what I'm going to do is say, all right, let's go ahead and find C. So I know I have, now again, we're going to looking for the angle, right? So I'm going to say the sine of C, sine of C1 over 10.5 is going to equal to the sine of 35. Now, again, what is 6 minutes out of 60? So 6 divided by 60, that's going to be 0.1, right? Yeah, 0.1. Okay. So I can just say that's 35.1 degrees over 7, right? That's 6 minutes over 60 is equal to 0.1. All right. So now what I'll do is I'll go ahead and solve for C1. So I'll just say multiply. So I'll do 10.5 times the sine of 35.1. And then I'm going to divide that by 7. Now, again, remember, when you're trying to find for the angle, you need to use inverse sine, right? Because it doesn't make sense here. Here's actually really important to talk about. So the sine of C1 is equal to 0.86 250787881. And the reason why I'm writing this down is because I want students to be able to understand, like, that's not the angle. That angle does not make sense. That's way too small of an angle. If you already have one angle, it's going to be 35 degrees. Like, yes, obviously it's possible, but it's very unlikely. And you need to understand, though, we haven't solved for C. We solved for the sine of C. So again, C1 is going to be the sine inverse. Now I have this in my calculator, so I'm just going to use the answer feature. So you look on your calculator, look for that A and S, and I'm just going to do sine inverse of the last answer. And that's going to give me a 59.5999. So let's say C1 is equal to 59.599343, which I'm going to store as equal to C. So I'm going to write that's equal to C, and I'm going to store that in my calculator because I don't want to round it until the very end. So I'm going to store this as alpha C. Okay. Now I have two angles, right? So if I already have C, which we're calling C1, I can be able to figure out what is my, what in this case is going to be my A1. So A1 is just going to be 180 degrees minus, A1 is going to be 180 degrees minus 35.1 degrees minus stored C. Okay, so then I'll just do 180 minus 35.1 minus my stored answer C. So I'll do alpha C. And that gives me 85.300 or 01, which is rounded. So I'm going to store that as alpha A. Now again, I already have, since I now have A and C, I already have C and B, I just need to find A. So now all I'm going to do is I'm going to say, all right, well then A over the sine of A, stored A, is going to equal 7 over the sine of 35.1. And then for now, I'm just going to do 7 times the sine of alpha A, which did I not save that? I didn't. Crap. Okay, so store that answer. So I'm going to store this as alpha A. I said it, but I actually didn't do it. So now that's stored as alpha A. And now, so I'll do 7 times the sine of alpha A. And then I'll divide that by the sine of 31.5. Okay, so therefore A gives me 13.352. Okay, so that is case number 1. Now, again, that is for C1. That is assuming it's a acute triangle. But what about if it's an obtuse triangle? So that'd be case 2. So then we need to understand is what is the relationship here between C2 and C1? Well, again, they're supplementary angles. So C2 is equal to 180 degrees minus C1. So all I'm going to do is do 180 minus C, which I calculated here, which I stored as alpha C. So that's going to be alpha C. Writing that in there, I'm going to get 120.4006. But again, I don't want to round this, right? I'm going to want to store this. So I'm going to store this as a new C. So I'm going to store this as alpha C. So I'm going to do store as alpha C. All right, so that's replacing my old C from the previous problem. But now I have 2 angles, therefore I can find a new angle, A, right? So A2 is now going to be 180 degrees minus my new C minus my B, which is going to be 35.1. Now again, remember, actually, yeah, we see that you can see that C2 is obtuse, right? Which we needed. We knew it had to be an obtuse angle. So then I'll do 180 minus alpha C. Did I store that? I did. So I'll do this as stored as alpha C minus 35.1. Now again, if my original A was this big and now it's getting this big, it should be smaller than 85.1 degrees. And I end up getting 24.45. So again, that is going to be smaller. So 24.499. And again, I'm just going to store that as alpha A. So I'll just store that as, so I'll do store as alpha A. All right. Now, again, we have 2 side lengths. I need to be able to figure out the other side length of A. So to be able to do that, all I'm simply going to do now is create one more ratio, and that's going to be with A. So I will have, let's see, where do I have anything with A? So I have angle A, so I'll have A over the side of my new A is equal to, let's do B with sine of B. So I'll do 7 over the sine of 35.1 degrees. Now all I'm going to do is take 7 times the sine of alpha A and then divide that by the sine of 35.1. And in this case, now I get A is going to equal a 5.08. And again, that should be smaller than my other A, right? Which is a 13, because A originally was this big. Now it got shrunk down to this big. So you can see how it go ahead and make sense. All right, last but not least here is we're going to talk about the area of a triangle. Now again, remember when you have a triangle, like, good old days, area equals base, height. So area equals 1/2 base times height. Well, what if you don't have a right triangle? Or what if you don't have it as a base, or you don't know the height? Like for instance, what if you have an oblique triangle? Well, again, if we think about this, we still need to figure out the base, right? But we've got to figure out the height. Now, if we know an angle, for instance, A, then we can say the height is going to be, remember, the height of a triangle, let's call this, here, I'm just going to call this C. And this would be B, and this would be A. Remember, I have all this room down here, and I'm not using this. So that's what we've previously learned, right? But if you have an oblique triangle, let's actually just redo this. So if you have an oblique triangle now, and let's call this A, let's call this B, and let's call this C. Well, if you need to find the height, right? What we talked about at the beginning of class today was that you can find a relationship of the height based on your opposing side lengths. So therefore, you can see that little c is the base of this triangle, and the height is going to be the included side times the sine of A. So you could say B times the sine of A is equal to height. So therefore the area is equal to 1/2 base, which in this case is C, times B sine of A. And again, if we keep on rotating our triangle, you can see how we would get different ratios for each one of those. So you can see here, that is my equation right there. The B and C are just flopped. But you could work on those for each and every one of them. So that's all we're going to do when finding the area. We're just going to find the area of these following two triangles. So in this case, we have our angle and we have our B and our C. So very good here. So that means all I'm going to do in this case is, let's just draw the triangle though, just to make sure we have everything. So here's A, that's 16, and that's 18. So we have area equals 1/2 B times C times the sine of A. And again, A is going to be 5 degrees and 100 seconds. So I can just type that in the calculator. I don't need to evaluate that. So I'll just do 1/2. So this is going to be times 18 times 16 times the sine of 35 degrees plus 5 over 60 plus 100 over 3600. Okay, so we do 0.5 times 18 times 16 times the sine of 35 plus 5 divided by 60 plus 100 divided by 3600. And I'll close the parenthesis there. And I am going to get an area of 82.824. Which seems relatively, depending on this height, because if I had the height, which would be, I don't even know what that sine is. So sine of 35, if you're doing 16, so that'd be 18 times the sine of 35 roughly. So it's giving you a height of 10, and then it's be 1/2. So yeah, seems like 180. Seems like that pretty much works. It seems in reason. Just remember, if you're using units, that's going to be your unit squared. For next example, I notice that I have two angles. Well, that's kind of an issue because I need to have I need to have two side lengths in one angle. So I'll draw my triangle. Here's 10 degrees. Let's call this big B. This will be little b. And let's call this big C. And therefore, I need to find little c. So the problem is I don't have enough information. However, I could kind of quickly, easily figure out what B would be. 180 degrees minus 10 minus 95 degrees. So I could do 180 minus 10 minus 95 degrees. That's going to give me 75 degrees. Now that I have this as 75 degrees, what I can do now is create a ratio. So now I can say that 3.2 over the sine of 75 is equal to, let's go ahead and find, doesn't really matter which one. You're either going to want to solve for C or for A. You just need two of them. So therefore, I'll just solve for A. So A over the sine of 10 degrees. So to do 3.2 times the sine of 10 degrees divided by the sine of 75 degrees. Whew. And that's going to give me A equals a 0.575. And then when I go ahead and plug that into my calculator, I have 1/2 times A times B, and then we'll do times the sine of C. So I'll just type all of that into my calculator. So I'll do 0.5 times that last answer, which was my A. So I'm not going to store that. I'm going to just use my last answer. And then times that times my B, which is 3.2. And then times that by the sine of C, which is 95 degrees. And I get 0.91. And therefore, based on that information, looks like that would relatively work. So there you go, ladies and gentlemen. That is the law of sines. You can see that we covered the area of oblique triangles. We talked about how to identify the ambiguous case, find all the missing measures, how to label 1, 2, or no triangle, as well as determine if it's a right triangle. Then we talked about obviously just understanding that ambiguous case, as well as looking into some word problems and finding the missing measures using angle, angle, side, as well as the angle, side, angle. So therefore, I hope you enjoyed, and I look forward to seeing you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on the law of cosines. Now, this is the third lesson in our chapter for applications of trigonometry. This is a lesson that I went over with my students that I am going to now go teach to you to develop the key and also to hopefully help you understand when and how to apply the law of cosines. So in this lesson, we're going to talk about finding the missing measures of an oblique triangle, the missing angles as well as sides, when given side, 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 as well as side, angle, side, as well as how to find the area of a triangle. Now, the way I started this lesson was I kind of went back to inverse trigonometry, and I gave these students these 4 problems. I said, all right, let's go ahead and, evaluate the inverse. And I was hoping that they went to use the unit circle, but now since this chapter, they have a calculator, a lot of students went ahead and just, plugged them into the calculator. But I'm going to use the unit circle, so therefore I'm going to use the exact measurements here. And you can always verify my measurements by using a calculator, which you will want to kind of follow along with me in this lesson with a graphing or a scientific calculator. All right, so again, remember the sine inverse is basically saying the sine of what angle equals 1/2. And if we remember in radian more, actually we're going to use everything in degrees. So we'll kind of go through in degrees here. So this was equal to, in degrees, that's going to be 30 degrees. And then when sine inverse for negative 1/2, we're going to think of negative 30 degrees. Now, again, remember, some people might think of, how do we, because we kind of went back already through a chapter on solving. Remember that the sine inverse function, right, is restricted on the first and the fourth quadrant, right? Because if you don't restrict it, sine is equal to 1/2 here and here. Right? But again, you can't have 2 answers when you're evaluating for the sine inverse of 1/2. There's only one answer, right? Because it's a function. So therefore, that's why we have it restricted between negative pi halves and pi halves, or negative 90 and 90 degrees. That's why the only answer is 30 degrees. You're not going to get this answer over here. Same thing for negative 30 degrees. You can see that it's going to be down there. That meets the restriction. This angle is outside of the restriction, which would end up being 210 degrees. Now we go ahead and go look at cosine. Now cosine has a different restriction, right? So the cosine inverse of 1/2, that's basically saying the cosine of what angle equals 1/2, but cosine is restricted between the first and the second quadrant. And when we look at that, we could say cosine is equal to 1/2. That's going to be this angle right here, which is going to equal 60 degrees. And then when we do cosine of negative 1/2, it's going to be over here. And again, these 2 angles, they also are angles where cosine is equal to 1/2 and cosine is equal to negative 1/2, but they don't meet the restriction. And again, that was such an important lesson that we talked about for inverse trigonometry, that there's only one answer, right? And your calculator is only going to give you one answer. And that angle obviously is going to be 120. Now, the point that I wanted to bring with the students is they were, typically were able to evaluate this rather quickly by the unit circle or with their calculator. But the point I wanted to drive home is, looking at these similarities, like a lot of students notice that the sine, whatever this angle is, if you have the negative version, you're going to have the negative angle. And then for here, when you have the negative value, you're just going to double it, right? So they recognize that doubling relationship and the positive and the negative. But I really wanted for students to understand and to dive deep why that's happening. Again, any angle that's positive up here, right, for sine inverse, when you take the negative value, yeah, it's just going to be reflected about the x-axis, right? Because it's either in the first or the fourth quadrant. And the cosine, you can see that here's the positive values for cosine. There's the negative values. So yeah, you're just going to be doubling those angles, in the first and the second quadrant. But what I really want students to come away from this is when you're doing sine inverse, you're only going to get an acute angle. Right? When you have a restriction between negative 90 and positive 90, you're never going to get an obtuse angle. You're only going to get an acute angle. And that was the problem with the ambiguous case. If you remember, when we were trying to find a missing angle, we were using sine inverse, which was only going to give us the negative angle. We were never going to get the positive angle. That's why we had that test with the height to find if there was an obtuse, if there was a two triangle case, right? Because if we just relied on sine inverse, if we relied on sine inverse, and that's not going to be enough information to determine if we're given the acute angle or if we're supposed to be given the obtuse angle. So the nice thing about today's lesson, or at least partially about today's lesson, is when we do cosine inverse, it's going to give us the acute or the obtuse angle, right? So whatever it is, it's going to give us that value, if it's 60 degrees or 120 degrees. And again, as long as the angle is between 0 and 180, it's going to be an angle inside of the triangle, right? So we don't have to worry about that ambiguous case for cosine inverse when using cosine inverse, because the restriction is between 0 and 180. So it will give us whatever the angle is. However, for sine, that doesn't give us the obtuse angle. It only gives us the acute version. So therefore, we have to do a little bit further test, and that's what was kind of difficult. So our goal today, and I spent a lot of time with students, is our goal today is to avoid that ambiguous case. And I'll give you what you're going to need. I'll explain to you how to avoid it. But I just wanted you guys to see the difference here between the cosine inverse and the sine inverse, and that really allows us to, I think, better understand our approach as we're going to work through these examples. So here's the law of cosines. I just kind of gave these to students. I didn't really work into the proof like I did for the law of sines. It's the same equation for the top and the bottom for the students. You know, the one thing to just kind of notice is typically when you want to solve for the side length, then you're going to use the top equation. And if you want to solve for the missing angle, you're going to use this bottom equation. But notice the bottom equation is really just the exact same equation as the top equation, just solve for cosine of A. It's also important to notice that these are solved for, or at least A is kind of semi-isolated, right? At least this one's A squared and this one's cosine of A. But obviously we're not always going to be solving for A. Sometimes it's going to be B or C. So whatever your angle is, or whatever your angle or your side length is, just swap it with what you have. So for instance, you know, I get this a lot with my students, you know, we'll need to solve for B squared. So I said, all right, wherever, just swap A and B. So now it's going to be A squared plus C squared minus 2 times A times C times cosine of B, right? So it doesn't matter what angle you're solving for. Oh, you want to solve for C? Okay. Then just swap the C and A. So C squared equals B squared plus A squared minus 2 times B times A times cosine of big C, right? So you can kind of see that relationship. I'm just swapping the variables. The other thing to always verify this, I always like to do, is, you know, for this first equation, the first side length and the angle are always the same, right? That's little b, big B, little c, big C, little a, big A. So that's one way I kind of check. And then these are the other two angles, and those are the other two, or the other two sides, and those are the other two sides. So once you kind of do it a couple times, you'll kind of get a little bit easier for you. And again, just to remember, we're going to label these. These are for oblique triangles. So we're just going to label opposite sides and their angles. All right, so let's go and get on with it with the side. All right, for the first example, it says find the missing measures of the triangle side using the law of cosines. Now, I don't really need to tell you to use the law of cosines, because once you draw this triangle, you realize there's no way for you to create a ratio because we're not given any angles. So what I'm going to do is I'm just going to draw an oblique triangle. I don't really know at this point if it's obtuse or acute. So I am just going to default that it's going to be acute. And I can always change it at the end if I see that it's going to be different. Okay, so there's going to be my triangle. And you can see I just have the side lengths. Now, the important thing is we need to say, all right, well, we can just find an angle. Like we have a formula, right, to find the missing angle. So should we just use A because that's what our formula is? Or should we be a little strategic? And that was the point of me spending that time at the beginning, is making sure you guys understood, like, we need to avoid the law of sines, or at least not avoid the law of sines. We need to avoid the ambiguous case. We want to make sure that when we're taking the sine inverse, that there's no option for us to have an acute and obtuse angle and not know which one is which. All right. So now the good news about this whole section is if you feel comfortable, or once you feel comfortable with the law of cosines, you can just continue using the law of cosines to find all the missing measures. So you don't actually have to transfer over to the law of sines. However, some students like to obviously solve things with the law of sines. It's a little bit quicker and a little bit less tedious of typing things into a calculator. So they sometimes aren't going to make as many mistakes as they would with the law of cosines. But the main thing is we have to avoid, or have to make sure we're aware of, is that ambiguous case. And so we want to make sure that we rule out the possibility of there being an obtuse angle or another angle larger than the one we're going to find. So what we're going to do then is we're going to find the largest angle of our triangle first. So when you have side, 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 always find the largest angle of your triangle first. And if you remember from geometry class, the largest angle is going to have the largest opposing side. So you can see here we have side length 6, or for C is going to be 6. That's the largest side. That means angle C is going to be the largest. So what's nice about that is when I find angle C, now again, the law of cosines is going to tell you exactly what C is. I don't need to worry about my other two angles being larger than C, right? Because remember, if you were to use sine inverse, it's only going to give you an acute angle. It doesn't give you a possible option for it to be obtuse. Well, if C is the largest angle, there's no way that my A and B can be obtuse because that's the largest angle in the triangle. And if there's going to be an obtuse angle, it's going to be C. So now all I'm going to do is I'm going to use this formula, but for C. And I'm just going to make sure that wherever I see an A, I'm going to swap it with the C for the whole formula. All right. So therefore I'll have, in this case, cosine of big C equals B squared minus A squared plus A squared minus C squared all over 2 times B times A. All right. And I just want to make sure that I did everything correctly. It's the opposing two side lengths minus A, same as that angle, divided by 2 times the other two side lengths. Perfect. And then it's plus minus, right? Okay, yeah, it's been a lull. Now we're just going to go ahead and plug things in, okay? And you are going to want to make sure you can follow along with the calculator. There is some big tips here that are going to come with how to type this into a calculator. For right now, I'm just going to show you how I'm just going to take this lengths and then plug them into the formula. So we'll have 5 squared plus 4 squared minus 6 squared. That's going to be all over 2 times 5 times 4. Okay. Now, it's very important that when you're typing this into the calculator, a lot of students want to just type everything in and just let the calculator do their magic, right? But you have to be very careful. If you want to type in 4 divided by 5 times 3, if you type it in as 4 divided by 5 times 3, then what your calculator is going to do is your calculator is going to do 4 divided by 5 and times 3. That's not what we want to happen, right? So what we want to do is we want to do 4 divided by parentheses 5 times 3. So it's very important when you're typing these problems into your calculator, especially if you're going to type everything in together, make sure you're using parentheses. So what my advice is for students is to do two things. You can either put the numerator and the denominator in an extra set of parentheses, which sometimes gets confusing. If you have a graphing calculator, it's a little bit easier than with like a scientific. Or you can just find the numerator, evaluate the numerator, evaluate the denominator, and then divide them out separately, okay? Now, obviously, we could probably do a lot of this in our head. These are not crazy numbers. But I'm just going to go ahead and type everything in. So this will be 5 squared plus 4 squared minus 6 squared, just because I want to make sure everybody gets the same values as I am. So 5 divided by 40, and then 5 divided by 40 is going to be 0.125. Now again, that is not the angle, right? So cosine of C is equal to 0.125, right? That's not what C is. The angle is not 0.125. The cosine inverse of 0.125 is going to be our angle. So now we can see the cosine inverse of 0.125. I can just type this in there now, and that's going to be 82.89. So I'm going to round this to 82.819 degrees. I'm going to round this to your nearest thousandth. I might have a rounding error at the end. Everything might not add perfectly up to 180, but that's because I'm going to be rounding them. But hopefully you guys can see in case, actually, I'm just going to leave everything truncated. But either way, so therefore we have our angle C, right? So cool. Now all we need to do is find another one of our angles. Now again, since we found the largest angle, I'm not worried about using the law of sines or the ambiguous case coming up. So all I'm simply going to do is I'm just going to pick either, A or B and just go ahead and solve. Now, one thing I do not want to do is use this rounded version of this angle that I gave. So what I'm going to do is I'm going to take my angle that I just found, and I'm going to use the storing feature on my calculator. So I'm going to hit STO store, and I'm going to save this as alpha C. Okay, so and then I'm going to label this on my work, so therefore I know that it's a stored answer. Now I'm going to use the law of sines to figure out what B is. So I will see, and again, we need to find the angle. So I'm going to use the sine of B over 5 equals the sine of stored C over 6. Okay, and then I can say the sine of B is going to be 5 times the sine of stored C divided by 6. All right, and that's going to give me some decimal 0.826, right? But again, I'm not going to use the rounded answer. I'm just going to go from here. I'm just going to do the sine inverse of that last answer. And B is going to equal 55.771. And then to go ahead and you can store that as alpha B. Then to find A, all I'm going to simply do is do 180 degrees minus B minus C. Okay, so I'm going to store that answer there. And then I'd just do 180 minus alpha B minus alpha C. And then in this case, A is going to equal 41.410 if you wanted to round it. And again, guys, I know I might have a rounding error from there, but that's okay. That's at least going to be my margin from my rounding errors. But at least you can see here now I've found A, my A, B, and my C. All right. So next example, you again see that we have a side, side, side. So we're just going to do the exact same thing. I'm going to draw the angles here. I recognize again, C is going to be my largest angle here. So let's go ahead and, so that'd be 60. B is going to be 51.7 and A is going to be a 22.5. Okay, so again, let's just go ahead and evaluate. I got a lot of extra room here. So I'll do cosine of big C equals A squared plus B squared minus C squared all over 2 times A times B. I don't know why. Why did I do the whole formula again? Whatever. So now this one, I'm just going to type in all together. So I'm going to use my parentheses on this one. So I'm just going to type this all at once. So I want you guys to kind of see how I'm typing this in. And I'm definitely going to be using parentheses, okay? A lot of parentheses. So I'm going to use brackets just to kind of differentiate my grouping symbols. And that's going to be over another bracket here, 2 times A times B, which is 51.7. Okay, so open parentheses. Then we'll do another parenthesis. Oops, parenthesis. 22.5 squared plus 51.7 squared minus 60. 60 quantity squared, close that parenthesis, divided by 2, divided by open parenthesis, 2 times 22.5, I don't really need those in parentheses, times 51.7, close parentheses. There we go. And then now I'm just going to do the sine inverse here of that answer. Not of that answer, I need cosine inverse. What am I doing? I'm crazy. Okay, so cosine inverse of that answer. And I get 100.422. So therefore I can say C, so cosine of big C equals, I got negative 0.18089. So therefore C is going to equal 100.422. And again, I'm going to store that as alpha C. So therefore I can use it later. Now, though, I can use, so I'll store this as C. Okay. Now though, I can go ahead and use my law of sines, law of cosines again. So again, it doesn't really matter. I already have an obtuse angle, so I'm not worried about there being another obtuse angle. I can just go about the law of sines. And that's the nice thing is, like, as long as you are aware that there's no way for you to get another obtuse angle, or there's not going to be an obtuse angle, then you can just go through the law of sines. So that either happens when you have an obtuse angle already, or when you know that you found already the largest angle in the triangle. So what am I looking for here? All right, so let's just go ahead and let's solve for B. So I have sine of B over 51.7 is equal to the sine of stored C over 60. So then I'll do the sine of B. And now what I'm going to do is I'm just going to take 51.7. I'm going to multiply that on both sides. So I'm going to multiply that by the sine of my stored answer C. And then I'm going to divide that by 60. So that equals, 0.847. And then I'm going to take the sine inverse of that. So I'll do sine inverse of that last answer. I'm not going to use the rounded answer I wrote in there. But when I do that, I get a 57.935 degrees. And then A, I'll just store that as alpha A. And then A is going to be, again, 180 minus my stored answer B minus my stored answer C. So I'll do 180 minus alpha B minus alpha C. Whoa, that's not right. 180 minus alpha B minus alpha C. Did I store? Oh, I stored that as A. Wait a minute. All right, let's check here. Let's see, alpha C. Got that one stored, alpha A. Oh, I did that as alpha A. Oops. Got to be careful with your angles. So I get 21.64. And the other thing to kind of like make sense of this as well, like your angle should make sense, right? And again, we can always check our angles. Now, again, I know I'm rounding, so my angles are not going to perfectly add up to 100, 180. But again, like that 21 and the 100.4, like that should work, right? That's almost 20, that's almost 58. That's almost 52. So you can see like, yes, those are going to add up to 180 or very, very close to it, right? We're going to have a little rounding error, but that's perfectly fine. So you can notice, like I noticed that my angle, I can't remember what I had, like 224. I'm like, well, that's wrong. So you got to be careful. I actually stored mine as the wrong angle that I said. So, or maybe I said it wrong. I don't know. But you just want to make sure you're careful with that. All right, so now let's kind of move on to the area. So the area of a triangle, like when we previously talked about the area of a triangle, and this was Heron's formula. Got to give credit where credit is due. So previously when we looked at the area of a triangle, we were looking at 1/2 base times height. Well, again, we need to know the height in terms of the, if you remember, we had to figure out the base, which was a side length. But in terms of the height, we figured out the height using with respect to one of the angles. Well, if we don't have any angles here, obviously we could use the law of cosines to go ahead and find an angle and then use that formula. But it's going to be a little bit quicker just to go ahead and use this formula. So the formula for area here is basically just going to be the S equals the sum of the sides divided by 2. And then you can basically just see it's going to be S times S minus A times S minus B times S minus C. And the nice thing about this formula is you can just plug everything in at once. So really the main thing you want to do first is find S. So that's going to be 4 plus 5 plus 6 divided by 2. And that's going to be 15/2. Since we have a calculator, that's going to be 7.5. So now the area equals the square root 7.5 times 7.5 minus 4. It doesn't matter the order that you go about. And again, one of the important things that to recognize from this is obviously if the side length is larger than S, then you can't have a triangle, right? Because what that would do is that would produce a negative answer, and you can't take the square root of a negative. The other way that you can also recognize when you wouldn't have a triangle is if S minus one of your side lengths is 0. Well, because then you obviously would be taking the square root of 0, and that means the area would be 0. So those are another ways. Sometimes you'll be asked, like, if the side lengths make the triangle. I think you should use the inequality, the side lengths, right? The sum of any two sides should always be greater than the third side. But again, you could also use Heron's formula to justify if a triangle exists given the angle measurements. All right, so now the nice thing about this is, again, I can just plug this exactly how it's written. I don't have to worry about my calculator doing a different order of operations. Or not an order, or at least following the order of operations, not as I'm intending them. So I'm just going to plug it exactly as how it's written, and I get an area equal to 9.922 rounded. And I don't have any units, but just remember, if you did have units like feet or inches, you'd want to use that unit squared. Okay, now let's go and get into the next one. Again, you can kind of see the same thing. I don't really need to draw a picture of this triangle. I just recognize this. I just need to figure out my S. So my S is going to be 22.5 plus 51.7 plus 60, all divided by 2. So 22.5 plus 51.7 plus 60 divided by 2 is 67.1. All right. So again, area. So that's 67.1 times 67.1 minus 22.5 times 67.1 minus 51.7 times 67.1 minus 60. So again, if you just want to check your work, let's just plug this in really quickly to make sure that we have the right answer. And again, really the main thing that students, they'll make their mistakes on is typing something in, dropping a parenthesis, forgetting a decimal point. So you just want to make sure, even though you can do this rather quickly, you just want to make sure you're careful with how you're typing everything in. And then I'm just going back through it, make sure I typed everything in right. And you can see, actually, I didn't, because I didn't put it under a square root. So I am crazy. So what I'm going to do, though, is I'm just going to evaluate that, and I'll just take the square root of that answer. There you go. And I'm getting area equals 572.029. And again, you guys can see, in this case, like, that makes sense, right? And the same thing for the other value. You can see that the area, like, works, okay? Like, it's not like 9,000 or like 0.9, So obviously when you have something like that, make sure your area would make sense relative, though, to those side lengths. All right, so the next set of problems we have is when we're going to have side, angle, side. Now, sometimes students will confuse these with looking at them to be angle, side, side, because they see the angle and they see the two sides. So that's why I always tell students to draw the triangle first. Now, if this was angle, side, side, I would always do the angle and then I'd do side, side. Well, in this case, we see this is 42 degrees. Well, I don't have any more angles, so let's call this B. Let's call this A. Well, B is 7 and A is 5. So you can see this isn't angle, side, like angle, side, side. This is side, angle, side, right? So draw the triangle, because a lot of times you're not going to know that it's side, angle, side, nor are you going to know to use the law of cosines. But obviously, once I draw the triangle, I realize I can't use the law of sines. I don't have a ratio, so I have to use the law of cosines. Now, the problem with using the law, or not really the problem with the law of cosines, but if you want to find a missing angle, if you remember from our formula, when I wanted to find a missing, let's go all the way back up. If I want to find an angle, I need to have all three side lengths, right? So I don't have all three side lengths. However, if you're looking for a missing side, like if you're missing for this, if you're looking for A, you need to have cosine of A, or you need to have angle A. So if you have angle A, then you can find A. And then all you need to know is B and C. So that's exactly what we have. We have an angle and we have the other two side lengths. So that means we can go ahead and find our opposing side length of our angle. So that's going to be A. All right. So what I'm going to do in this case is I'm just going to go back to the formula. So that's going to be A squared equals B squared plus C squared minus 2 times B times C times the cosine of A. All right. And now it really just kind of comes into plugging things in. So a squared is equal to 7 squared plus 7, wait a minute, 5, B and C. What am I doing? Did I write that down? Oh, I'm sorry. I'm trying to solve for C. I'm like losing my mind. So I'm not solving for A. I was like looking at that as A, but that's going to be C. So I'm trying to solve for C squared. So C squared equals, apologize, A squared plus B squared minus A times B times the cosine of C. Okay, so basically all I'm doing is I'm swapping the A and the C variable from our original formula. And again, just to look at this, that's going to be the opposing two side lengths, added squared add, minus 2 times A times C. Okay, and again, let me just go back and double check just to make sure I'm not doing anything crazy. Angle, the opposing two side lengths, minus 2 times B times C times cosine of A. Okay. So now it's just going to plug everything in. So I have C squared equals, so this would be 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of 42 degrees. Now, the nice thing about doing this is I can actually just type everything in as it's written. So I don't have to worry about like that division again. So this would be 5 squared plus 7 squared minus 2 times 5 times 7 times cosine of 42 degrees. And then I'm going to get C squared is equal to 21.979. And remember though, that's C squared, so you need to take the square root of that answer. So therefore C is equal to 4.688. Now, again, does that kind of make sense, right? 21 was kind of big for especially an angle at 42 degrees. So that one's kind of big. So, but 4 kind of makes sense, okay? Roughly that kind of looks all right for that triangle. Now, the next thing is, now what do we do? Should we go ahead and find now the B? Because we find B, or now we can go and use the law of sines because we have an angle. And that's where a lot of students will make the mistake. Or if they say, well, let's go and use the law of sines to find B because that's going to give us the largest angle. That's right. But remember, the law of sines only gives you the acute version of that largest side. So we do not want to use the law of sines because we're not sure if there's an acute angle or not. So what you're going to want to do is use the law of cosines here. So only time we really want to go to the using the law of sines is when we have that side, 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 and we've eliminated the largest angle of the triangle. And what I'll do is I'll show you why that can be a mistake. So let's go ahead and use the law of cosines to find cosine of B. So that's going to be A squared plus C squared minus B squared all over 2 times A times C. So cosine of B equals, so let's see here, it's going to be 5 squared plus, I don't have C squared. What am I doing? Oh, I do have C. I need to store this. So I'm going to store that answer. I forgot to do that because I don't want to use the rounded answer. So I'm going to store that as alpha C. Okay, so, and then it's going to be minus B squared. So that's going to be minus 7 squared. 2 times 5 times C. I'm sorry, times C, stored C. All right, so now on this one, I'm going to make sure I need to use my parentheses, right? So use some brackets here. All right, so I'll do 5 squared plus stored answer, C squared minus 7 squared divided by parentheses, 2 times 5 times alpha C. Okay, and in this case, I get a negative 0.04. So therefore, cosine of B equals a negative 0.043. And then again, you need to use cosine inverse. So B is going to equal the cosine inverse of that answer. And I'm going to get a 92.47 rounded degrees. Okay, so you can see that B is actually an obtuse angle. Now again, that would not happen if I did the law of sines. So let's just do it just for the sake of learning. How would you, like, what if you did do the law of sines instead? So if you did, you know, cosine of B over 7 is equal to the cosine of 42 degrees over stored answer C. B is going to equal, and watch this. So you do 7 times the cosine of 42 divided by stored answer C. That's not right. Hold on. 7 times cosine of 42 divided by stored answer C. Oh yeah, cosine. Oh, it's cosine. What am I doing? You're using the law of sines. I went to sine. I'm like, what is going on here? That's the sine of B over the sine of 42. Jeez, law of sines. So 7 times the sine of 42 divided by alpha C. And then if you did sine inverse of that answer, I get 87.5. Okay? Now again, like these are related to each other, right? But this is the acute version. B, again, sine inverse is only going to give you the acute version. So how do you go from this B to that B? Well, technically, if you do 180 minus B, you're going to get 92.47. The problem with this is you don't know if you're supposed to do that or not, right? You don't have enough information to confirm, is it the acute or is it the obtuse? However, if you use the law of cosines will tell you that is the angle. You don't have to guess and worry, I wonder if it's acute or if it's the obtuse version, right? So that's why we want to stick with the law of cosines. So now I have B and I have A, or I have C and I have B, so let's go and find A. So A is going to, I already found C, so remember I stored that. So now A is going to be, let's store this as angle B. Where was that angle? So I'll store that as alpha B, and then I'll do 180 minus 42 degrees minus alpha B. And by doing that, I have 180 minus 42 minus alpha B. So therefore, that's going to equal 45.53 degrees. And again, I'm just rounding this. So again, I could have a rounded answer there. But again, this is just very important not to go to this law of sines once you've done the law of cosines. Okay. So now let's just do one more example here. In this case, I have 43 degrees and 57 minutes. So what I'm going to want to do in this case is take my 43 degrees and then I'm going to add that to 57 over 60, right? Because if I have 57 minutes out of 60, that's going to give me a decimal, which is 0.95. So therefore, that's going to equal 43.95 degrees, all right? So I want to convert it to decimal form. And now let's just go ahead and sketch our graph here. So let's just call this A. So 43.95. That's supposed to be B, actually, because this is supposed to be side angle side. So let's call this one B. So that's 7.5. And this would be C. So that's going to be 8.5. All right. So again, you can see we're looking for A squared. So again, just kind of like what we did before, A squared equals B squared plus C squared minus 2 times B times C times the cosine of A. Now in this case, I'm just going to plug everything in, because we've already kind of covered everything. So I'm just going to say that's going to be the square root of 7.5 squared plus 8.5 squared minus 2 times 7.5 times 8.5 times the cosine of 43.95. Okay, so we can just type this all in together. So do the square root of 7.5 squared plus 8.5 squared minus 2 times 7.5 times 8.5 times the cosine of 43.95. And I'm getting A equals 6.05 9 rounded. And again, like that works, like that makes sense for that. I'm going to store that as alpha A. Now it's going to be very important that I need to solve for one of my missing angles. Again, I'm going to use, going to want to use the law of cosines. Do not do the law of sines. So in this case, I'm just going to go ahead and go to B. So cosine of B, because we haven't done that one yet, that will be A squared plus C squared minus B squared all over 2 times A times C. So therefore, the cosine of B is going to equal. So let's go ahead and actually type that out. So let's see, A squared. So that's going to be, where's A? Oh, that's going to be stored A squared plus C minus B squared. So that's going to be 7.5 all over 2 times stored A and then times C, which is 7.5. All right, so now let's go ahead and do that. Again, just make sure you're using your parentheses again. This is that number one mistake that students make there. So we have alpha A squared plus 8.5 squared. Now this one, actually, I'm just going to do everything kind of on its own. 7.5 squared. Okay, and then I'm going to divide that by the quantity, 2 times alpha A times 7.5. And then, so I'm getting cosine of beta is, or B, sorry, is 0.579. So therefore, B is equal to, kind of move over here. So I'm going to do cosine inverse of that last answer. And I get 54.552. That's a rounded answer, all right? So we already have A, so therefore C is going to equal B, which I'm going to store. So it's going to be 180 degrees minus 43.95 minus stored answer B. So I'll do 180 minus alpha B minus 43.95. And therefore, C is equal to 81.498 degrees. And again, I'm just going to do a kind of quick little spot check to make sure that they get me pretty close. Like I shouldn't have, obviously, something very larger than 180 or very close. Like obviously, I can have a rounding error based on at least my instructions here. But I should generally be very, very close to 180 degrees, which it looks like I am going to meet. So that's kind of the basics for using the law of sines. I'm sorry, the law of cosines when we have a side, side, side and a side angle side. Now what we want to do is kind of get into these word problems and see how we're going to address a word problem. So the first word problem we're going to work with is going to be with a bearing. So it says a ship leaves port at 1 p.m. and sails in the direction of north 38 degrees west. So I was very adamant with my students that whenever they see the bearing, again, if you remember from the law of sines, is to draw a compass heading. Okay, so it's going north 38 degrees west. All right, so I don't know how far it's going, but I'm just going to do that and say, all right, let's make that 38 degrees west. So we're going north, 38 degrees west at a rate of 20 miles per hour. Okay, cool. So that's going to be the rate 24 miles per hour, but I don't know for how long yet, so I'll just keep on reading. Then another ship leaves port. So again, obviously this is port at 1:30 p.m. and that sails in the direction of north 52 degrees west. So that's going to be a little bit farther. And again, I don't know how far these are going from each other, but I can see this is going a little bit slower at 19 miles per hour. Now it says at 2:30, how far apart are the two ships? So we're looking for basically how far apart they're going to be. So D equals, I'll just say the distance the ships are apart. Okay, so that's the distance that ships are apart. Now we got to find how long are those lengths, right? So we have 38 and we have what, 52? Okay. Let's try to draw that a little bit better. So here, I'll do this Put it right there. No. There we go. Kind of. Looks like that. Okay. So anyways, that's going to be 52. That's 38. Got it. Now, if we leave it the first one leaves at 1, and then we're asking for 230, then it's been traveling for 24 miles per hour for an hour and a half. Well, 1 hour it traveled 24 miles. So if it travels for a half, that's going to be 12 miles. So therefore, this is going to be 36 miles. And then over here, this left at 1:30, and we're clocking it at 2:30. So that's going to just be 1 hour. And if it's traveling at 19 miles per hour, that's going to be at 19 miles. Now, typically, sometimes I tell students to draw the triangle, draw the picture, and then you can go and solve. But sometimes it's just like, this is like kind of too much, right? I'm not really sure where, I want to make sure I can see the triangle and see exactly what I have. So a lot of times I just tell students to kind of just redraw the triangle. Like, forget about the picture. Like, keep the picture, right? Let's kind of keep this. But now let's just draw the triangle separately with its measurements. So I have something that looks like this. Now again, we need to figure out, like, that's the angle. Well, if this is 52 and that's 38, what is this angle? Well, again, that angle right there is going to be 52 degrees minus 38 degrees, right? And you can see that that's going to be 14. This length is 36. I'll drop the miles just to keep things simple, and that's 19. And then we're looking for D. So now you can see that we have side, angle, side, and we're looking for D. So now I just need to use the law of sines, and I'm going to be looking for D for the answer D. So again, using the formulas, now we don't have A, B's, and C's, and that's fine. So what we're just simply going to do is, hopefully you remember the relationship between those two sides. It's going to look something like this. D squared equals 19 squared plus 36 squared. So it's the two other sides squared minus 2 times 19 times 36 times the cosine of 14 degrees. Okay, so now all I'm simply going to do is just plug this in. So I'll have 19 squared plus 36 squared minus 2 times 19 times 36 times the cosine of 14 degrees. I don't remember that's what I got there. Cosine of... I don't remember that being the... Did I square those? Yeah, I did. Or my answer being... Oh, maybe that was it. Okay, yeah, that works. Okay, so it's been a while since I was going through this, and I was thinking, yeah, there we go. Okay, so that does make sense. So the point is, a lot of students will go ahead and get to this, and they say, oh, the answer is 329. And I said, all right, we got to make sure when you guys are doing word problems, make sure, again, if you remember, like one of the things we talked about at the beginning of the lesson is make sure it makes sense, right? This doesn't make any sense. If, one ship's going 36 miles and another ship's going 19 miles, does it make sense for them after an hour to be 329 miles apart from each other? No, because remember, it's D squared. So now if you take the square root of both sides, you're going to get D equals 18.156 miles. That makes a little bit more sense, right? If one travels 36 miles and the other one travels 19 miles in relatively the same direction, you can see that they're going to be 18 miles apart, and that makes sense. So just make sure that one, draw the picture, create the triangle, set up the equation using the law of cosines, check your answer, make sure it makes sense, and then make sure you apply the correct units. All right, the next example is, again, another bearing problem. But in this one, we're going to have a cruise ship travels at a bearing of 40 degrees. So it's a little bit different bearing. So I'm going to have a bearing 40 degrees. So I'm going to go ahead and draw that. Okay, so 40 degrees is going to be roughly something like this. All right, and then it's going to travel 40 degrees at 20 miles per hour for 3 hours. Now again, if it's going 20 miles per hour for 1 hour, that's 20 miles. So therefore I can say that's going to be at 60. Okay, then it's going to change course to a bearing of 120. So I'm going to bring this down a little bit. Not that one, this one. Okay, so again, it's changing course. So what that means is I need to create another compass heading. So now it's going from north, it's going to go 120. Well, from here to here is 90, right? So 120 is going to be like 30 degrees more. And it's going to, looks like it's going to go 20 miles per hour for 2 hours. So it's going to be 50. So it's going to be a little bit shorter than that. All right, and then we'll just say from there. Now it's saying find the distance the ship is from its original position. And also its bearing from its original position. Okay, so here is the distance, direct distance from its original position. We'll call D. So D equals distance from original position. All right, we have, so that's going to be 60. So that's 40 degrees. And then we know this is 120. Okay, so forget about the side lengths for a second. Let's just figure out the angles. So I don't know what this angle is. However, one thing we want to keep in mind is remembering, like when we have compass headings, we create parallel lines, right? North-south is parallel with north-south for both those compass headings. So what's important about that is when you have parallel lines, look for the transversal, because look for alternate interior angles, alternate exterior angles, corresponding angles, same side interior. So, you know, look for same side exterior are going to be complementary or supplementary. So look for those angle relationships. So therefore, if I know this is 40 degrees, then I know that's going to be 40 degrees. Also, I recognize that this is 120, then these are supplementary angles. That means this has to be 60 degrees, right? So again, actually, I'll put it in, so I'll put 50. I'll also put it in parentheses so I know it's not an angle. Okay, so now I have an angle, and you can see that I have, again, another 2 side lengths. So what I'll do here is I'm just going to kind of redraw this triangle. All right, and let's see, I have this angle is going to be 100 degrees. This is going to be 50, and this is going to be 60. So now you can see I can definitely go ahead and find this distance D. So in this case, I'm just going to go with the square root. I'm not going to make that mistake, you know, like a lot of students will make. And I will just go through, this is to be 60 squared plus 50 squared minus 2 times 60 times 50 times the cosine of 100 degrees. All right, so now I can just plug this all into my calculator. So I'll do 60 squared plus 50 squared minus 2 times 60 times 50 times the cosine of 100. Now, I could have put this under the square root. I forgot to. If you do forget to do the square root, you get 7,146, which again makes absolutely no sense, right? If you travel 50 miles, then you travel 60 miles, your distance back, the distance from its original position is not going to be 7,000 miles. So that's why we know we have to take the square root of that answer, and you're going to get 84.50, which makes sense. So therefore, my distance here now is going to be 84.51 miles. All right, so the next one is going to be finding the bearing. So the bearing, remember, is going to be from due north, right? We graphed all of these with the bearing from due north. So I need to be able to figure out this angle from here to here. Well, the only angle I can figure out now is this angle theta, right? And let's just call this, since we're going to use, let's just call this A. Okay. Well, to find A, I need to either, I could use my stored answer here of 84.51. You could use the law of cosines again. Or you can see that since we have a obtuse angle here, I'm not worried about looking for I'm not looking for an obtuse angle or anything larger. So I know my angle is going to be acute. So I can just go ahead and use the law of sine. So I'm going to store this as B, just so I can use this again. So I'm going to store as alpha B. And then now I have a ratio, right? So I can say, I need to find the angle. So I can say sine of A over 50 is equal to the sine of stored B over, I'm sorry, Yeah, sine of stored 100 over sine B. Jeez. B is not an angle. It's 100 degrees is an angle. So you could say sine of 100 degrees over stored B. Okay, so now I'll do 50 times the sine of 100 divided by stored B. And then I do the sine inverse of that angle. And I get 35.63. So A is going to equal 35.638 degrees. But again, that's not the bearing. That is angle A, right? So it's very important that we understand that from here to here was 40 degrees, right? So from here to here is 40 degrees, and then from there to there is 35.6 degrees. So therefore, we have a bearing of 40 degrees plus 35.638 degrees, which is equal to, 75.638 degrees. And again, that's just going to be rounded from there, but hopefully you can kind of see how finding that angle and how we just had to make sure we understood that bearing is going to be from due north. So there we go, ladies and gentlemen. That was 2 examples of how to use the law of cosines for side, 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 angle, side, word problems, as well as using Heron's formula. I hope this lesson has helped you out, and I look forward to helping you out on the next one. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to work on vectors on a plane. Now, this is going to be our 4th lesson in our chapter for applications of trigonometry. And what I'm going to do is I'm going to go over the exact same notes that I went over with my students and kind of work through the exact same examples so you can see what it is I wanted to teach my students for vectors on a plane. Now, this is our introduction lesson into vectors. So what we're going to learn in this lesson here is really what is a vector, how do we represent vectors, how do we determine the magnitude, the angle of vector, the unit vector, as well as how do we identify resultant vectors by using operations such as addition, subtraction, and scalar multiplication. So that's what we're going to kind of cover. The way that I started off this lesson was just kind of going back to some good old geometry with students and asking them to find the distance between 2 points. And a lot of students, kind of typical, kind of forgot what to do for finding the distance between 2 points. So let's just kind of cover that again. Remember, I think the main thing is, even if you do get stuck and you like totally forgot everything, remember you can always plot these points, right? Like here's A. And then here's B. So 1, 2, 3, 4, 1, 2, 3. So if you just plot the points, because a lot of students are like, what was the distance formula? Like I forgot it. And I'm like, you don't need the distance formula. Like if you look at this, guys, we can see that between any 2 points, all we got to do is create a vertical and a horizontal distance. Now you can create this distance to be negative, or you could create it to be positive, right? Because you're going to the left, so it could be negative and that could be positive. But again, using the Pythagorean theorem, that's going to be 3 squared plus negative 4 squared, or you can recognize that this is a Pythagorean identity. Now, the issue is when we want to write the answer, if you remember, we write the answer here as like AB is equal to 5. Or we could also write it as BA is equal to 5, right? It doesn't really matter if we're going from A to B or from B to A. The distance is still going to be 5. And again, all we're going to do to find that distance is I created a triangle using my horizontal and vertical distances, and then you could either use Pythagorean theorem, or you could use, notice that it's a Pythagorean triple. Now this next one doesn't look as nice, but again, I'm just going to plot the points before I judge it, right? So I'm going to go over 2, down -1, we'll call that C, and then we're going to go left 3, 1, 2, 3, up 5, 1, 2, 3, 4, 5. Okay, so there's going to be C, there's my D. Now in this case, again, we can follow those same steps here. We can create that vertical, as well as the horizontal, right? We're creating a right triangle. Now, again, all we need to do in this case is find these distances. And again, they don't need to be positive or negative, because in the same respect, I also could have gone negative down here and to the right 4. So that could have both been positive or negative, right? So I'm actually just going to erase the positive or negative because it doesn't matter when you are identifying this distance. And again, I'll kind of explain that as well once we get into using the distance formula. Now, the nice thing about plotting the points is you can easily you can easily count, right? We can easily just count these values and say, oh, this is going to be 1, 2, 3, 4, 5, 6, right? And this distance is 1, 2, 3, 4, 5. Right? So, I mean, it's not that bad just to kind of see those differences. But the thing I brought up to my students is, what if this was like the square root of 2, square root of 3, square root of 5? Like, what if you weren't going to really want to count by square roots? Or let's say they're fractions as well. Counting, or at least graphing them accurately, might not be a better way or a great way to find the length. So what we can do is really say, well, what is another way of like thinking about this? So the way that we can think about this is, this horizontal change, this is a change, right? In horizontal distance. We're going from C to D, or we're going from D to C. So either way, if we want to find the change from one distance to the other, what we're looking for is we're looking for the difference, right? What is the horizontal difference between D and C? Now, typically it doesn't matter which direction you go, but typically what we've done is said like x2 minus x1. And then for the horizontal distance between D, the vertical distance, I'm sorry, would be like y2 minus y1. And again, what is y2 and y1? Well, or what is x2 and x1? Well, those come from the coordinate points. So I'm just going to go from left to right because it doesn't matter which way you go. But you recognize that these are both coordinate points, x comma y and x comma y. Well, we obviously don't want to confuse which coordinate is x and which coordinate, is y. So what we're going to use is we're going to use subscripts to differentiate the two. So we're going to call this x2, y2. And this one, x1, y1. Okay, so that's how we differentiate between the points. And again, this is just how the formula is written. But again, if you want to like flip these around, it doesn't matter, right? It doesn't matter if it's -3, 4 or -4, 3. But either way, if we now apply this Pythagorean theorem here, you can say that d squared is equal to x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And really, instead of squaring the left-hand side, I could just rewrite this, take the square root of both sides, and just read it like that. And voila, ladies and gentlemen, we have the distance formula. So if I want to find the distance, I already did x2, x1, right? This one wasn't that bad. I was able just to count it, right? Now, again, just for the sake of teaching, though, I am going to, again, show you how this math works, just so you can confirm. Like, it was much easier just to count, but just for fun, let's do it. So let's do -3 minus 2. Quantity squared plus -3, 5 minus -1. And you can see, like, some of these people are going to make a lot of mistakes when they have these negative numbers. So -3 minus 2 is going to be a -5. And then 5 minus a -1, that's going to be a +6. Okay, so therefore we have a 25 plus 6, which, 36. Geez, what am I doing? 25 plus 36. And that's going to give us a square root of 61. Okay, so that would be the distance of that hypotenuse right there. So therefore we kind of got into this, and then we kind of talked about, really just discussion, like the distance doesn't really matter between AB and BA. But is there actually a difference between them? And yeah, there is a difference. Like typically for lines or line segments, we didn't really care if you're going from A to B or from B to A. But I think you guys would agree, like in a real life situation, it matters which one, where you start and where you end, right? There's a difference between if you go from A to B or if you go from B to A, not in terms of like the distance you traveled, but as far as like the direction that you are going, right? So therefore, to represent that direction is what we use with a vector. So a vector is a directed line segment. Notice it's a line segment. That means it has an endpoint at both ends with an initial point and a terminal point. So the initial point we can call P, but it's again just a point, and the terminal point Q. Now the notation for that vector would be in this form with the initial and terminal point would be like BQ, and then with this nice little kind of half arrow on there. Now when we're drawing a vector, okay, so let's just kind of go through the things. Like here, if you remember, that's a line segment. That is a ray, so that is a line segment. This is a ray. This is a line. And then this is a vector. So you can see how that endpoint, we have the initial and we have the end. So that is what we call a vector. That's how we represent this. So it looks very similar to the line, even though notation looks similar. But the the difference here is you can see that, you can see this arrow starting from here and like it's showing you we're going from here to there. Like that's what that arrow is representing, but it doesn't extend like a ray, right? It doesn't extend indefinitely. It kind of stops, but that is going to be our form from a vector. A lot of times we call this initial point also the tail, and then this the head. All right, so just like with any line segment or what we just distanced, the distance between 2 points, we have 2 points, right? We have the initial point and the terminal point. So that means we can find the magnitude. And thankfully for us, we just did the magnitude. The magnitude is just the length of the vector. So if we have an initial and a terminal point, you can see that the magnitude notation kind of looks like 2 vertical lines, kind of like double absolute value. It's not double absolute value. But that's going to be our notation that we'll use to represent the length of the vector, which we just call the magnitude. So again, depending on what type of information you're given, you can use this formula of finding the difference of the horizontal distance, finding the change in the vertical distance, squaring those, and then adding them together to take the square root. Or, if you're able to graph them, you could do it kind of the easier way, which we looked at as well. But fortunately, you guys can see this kind of looks kind of confusing just because there's just so much going on. So that's why a lot of times we don't really like to represent vectors in terms of its initial and our terminal point, but rather we like to look at component form. So what component form is, and I don't know why I didn't write this in, but yeah, so what component form is really, when we found the horizontal change in the horizontal change, as well as the vertical change, well, then we can just call those, like V1 is the change in the horizontal distance between the initial and the terminal point, and V2 is going to represent the vertical change in the vertical change in our 2 points. So the nice thing about component form is rather than having like 4 numbers or like, 4 points here, we can just represent V1, V2. So we call these the components of the vector, V1 and 2, where V1 is like the horizontal component and V2 is going to be the vertical component. The other thing I didn't mention about component form is component form always has the initial point at 0, 0. So let's go ahead and take a look at, let's go back to our original problem. Actually, let's just do a quick one. So let's say, well, I'll just kind of go for here. So my vector, well, I guess the one thing, we'll do an example of writing them in component form and you'll be able to see. But I guess my point that I want to go through with you is if I was going to say like 3, 5, that's a coordinate point, right? So that'd be 1, 2, 3. Let me get rid of that dot here. I'll just do an example. So 3, 5 is 1, 2, 3, 1, 2, 3, 4, 5. That is a point, okay? But if I'm going to write the component form of a vector 3, 5, what that tells us is the initial point is going to be at 0, 0, and then we're going to go to the terminal point is going to be 3, 5. So just remember, a lot of times when we're writing these vectors, what you're going to see, which I did not talk about that before. I didn't use that. My bad. So now you can see that we are going to use what we call slanted parentheses. So this is going to be our common form when we're dealing with component form. You're going to see what we'll call these slanted parentheses. So just notice the difference between them. So we have a coordinate point, which is 3, 5. And then when you have a component form, it was slanted parentheses, that's going to be from the origin 0, 0 to your coordinate point 3, 5, which will represent the terminal point. The nice thing about component form, since it reduces everything, it makes everything a little bit easier to calculate. Like for instance, instead of the magnitude, we already know the change in the horizontal and the change in the vertical. So now I can just square both of those components and then take the square root of them, right? So if you have V1 and V2, it's a lot easier to find the magnitude. And then also, if you're given an angle, right? Oh, actually, let me just kind of go through this. So let's kind of look at this again real quick. So if, here is my V1, V2. Let's say that's the vector. Then, that's your V1 and that's your V2, right? So, if here is your vector V1, V2. Let me just erase that and see. So again, the vector in component form is going to be going from 0, 0 up to your terminal points, v1, v2. But again, that's represent the whole direction. Well, again, your v1 and that's your v2. Those are your changes. So you can create the triangle and then find the denominator from there, which would be, not the denominator, the distance or the hypotenuse, which will represent your distance. And then also, we can also look at this as a direction, right? Sorry, not the direction. That should actually just be the angle of the vector. Got to change that. So the angle of the vector is, again, since we have this at the origin, we can look at this in terms of standard form. So again, we go back to our XY axis, right? And let's say we have our dot here. So V1 comma V2, that's going to represent our angle right there. So again, if we're looking for like, hey, what is this angle? Like how much is that of a rotation, right? Well, again, we can look at this as V1 and V2, right? Where you can see, obviously, oh, well, the opposite over the adjacent side of this triangle, right? Again. So now, again, you can see here that we would just use the, opposite over adjacent or the tangent function. Let me make sure this like kind of sticks out so you can kind of see. I don't want that to be confused with that line. Okay, so now let's kind of get into some examples where we can look at the magnitude and the direction of each vector. So in this first example, I just want to kind of show how the initial point and the terminal point is kind of similar to the component form, as well as how they're different. So the first thing I'm going to do, you don't necessarily need to do this, obviously, unless you're being told to do it, but I'm going to graph both of them. So if I need to graph r, that's going to be -3, -1. And then t is going to be 1, 2, 4. 1, 2, 3, 4. So that's going to be t, and that's going to be r. If I need to find component form, that's going to be r to t. I'm sorry, the vector. It's going to look something like that. Okay. Now again, I don't want to go ahead and find the magnitude from there. It's just a little bit of, kind of a lot of work. So what I'm going to do is to write this in component form. It's really actually the same amount of work to write it into component form. But all we're simply going to do is we're going to identify v1, which, remember, v1 is just going to be the change in x2 minus x1. Now, again, which one's x2, which one's x1? It really doesn't matter since they're going to be squared. But typically, your initial point is going to be your x1, y1, and your terminal point will be x2, y2. So x1, y1, x2, y2. All right, so v1 is going to be 2 minus -3. And my v2 is going to be 4 minus a -1. Okay, and in this case, you can see that we're going to get 5, 5. So that equals 5, and that equals 5. So now my vector, and again, a lot of times what I'll do is I'll just write this in like this. I'll just say vector v can be 2 minus a -3, comma, 4 minus a -1. And again, what we get here is 5, 5. Oh, I said find the angle and the direction. Ooh, crap. All right, so let's go and graph 5, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One more up. Okay, so what I want you to notice here is the vector from the initial and the terminal point. When I write the vector in component form, that means basically taking that vector and placing it at the origin, you can see that it has the exact same magnitude. It's also angled at the exact same direction, so the angle is going to be the same. But now that my initial point is at the origin, not only one, is it a lot easier to write and understand, right, than coordinate points, but it's also going to be a lot easier for me to identify the magnitude, right? Remember, the magnitude of v is just going to be the first component squared plus the second component squared. So that's going to be 5 squared plus 5 squared, which is 25 plus 25 is square root of 50. And again, in this chapter, we're not going to have to worry about simplifying our radicals or rationalizing the denominator. We can just leave our answer just like that. In terms of the angle of theta, in this case, you can see that we're in the first quadrant, so we just need to be able to figure out from here to here. Now, hopefully you recognize that if we were to simplify this, just a little FYI, let's play a little game. Let's see if you remember which triangle this would be simplified into 5 square root of 2. which triangle have we talked about where the two legs are exactly the same and the hypotenuse is the same as the leg multiplied by the square root of 2? Well, that's a 45, 45, 90 triangle. So my angle here is just 45 degrees. Could you also do the tangent inverse of 1? You could, right? So you could also say theta equals tangent inverse of opposite over adjacent, which is 1. And again, you're going to get 45 degrees. But I saved myself a little bit of time. The last thing I wanted to explain, which I didn't cover on the component form, is why I'm using v. So the reason why we're using the vector v here is because, a lot of times we can describe vectors as their initial and terminal points. But when we write them in component form, right, what we do is we can give them letters to represent the vector. So we could call them v, we could call them w, we could call them l, m, n. We're going to be using a lot of different variables to represent our vectors. It just makes it a lot easier. So I can say like vector v, and then the components that I am referring to for that vector. So if we have the initial and terminal points, we'll use those initial and terminal points, but you can see why component form, all I got to do is I can just give it a name here, and whereas v1 and v2 represent the components of that vector v. So in this case, you can see, again, I'm using v. I will switch it up as we get through the lesson. But in this case, I don't really need to worry about the magnitude because this is already in standard form, right? So let's go ahead and first graph this just so you guys can see what this vector is going to look like. So negative 1, 2, 3, 4, 5, 1, 2. All right, so there's vector. Let's call that v. Let's go ahead and find the magnitude. So again, using my magnitude notation, vector v is going to be equal, let's see, negative 5 squared plus negative 2 squared. Well, let's see here. Negative 5 squared is 25. Negative 2 squared is 4. So therefore, that's going to equal the negative square root of 29. Okay. As far as the angle goes, let's see here. I'm going to have tangent of theta equals a negative 2 over negative 5. So theta equals the tangent inverse of 2 over 5. All right. So now we're going to have to go and use our calculator, right? And what I'm going to do is I'm going to type this into my calculator. So I'll do tangent inverse of 2 divided by 5. And I get 21.8 degrees. Now that's a problem because that angle doesn't look like the angle that I need. I'll just round this to the nearest tenth. Because 21.8 degrees is over here. Right? Our vector is negative and negative. It's in the third quadrant. So how are we getting this angle, but we need to get down here? Well, again, this goes back to our understanding of restrictions. Tangent inverse, if you recall, is restricted between the first and the fourth quadrant, right? So when I'm looking for an angle, it's never going to give me this angle. Tangent inverse is only going to give you an angle in the first or in the fourth quadrant. So then what is 21.8? 21.8 is the reference angle. That's how big this angle is right here. Now again, remember the reference angle is just the positive acute angle here. So if that's 21.8 degrees, but I need to go from here to here, then what is my angle theta? Well, my angle theta is going to be 180 plus 21.8. So then to find my angle, all I'm going to do is do 180 plus 21.8 degrees, and that's going to give me a 279.2, I think. Let's check. Plus 21.8, 201. What was I thinking? 179. I guess I was like subtracting. Pretty silly me. Or and that'd be 78 anyways. 78.2. Anyways, this is going to be 201.8 degrees. Okay, going a little crazy. All right, so those are the two problems I kind of covered my students, and then I wanted them to kind of work through these examples. So let's just kind of work this here. You can see here that I have the U and the W. So again, just working on that same kind of idea of different names for our vectors. So let's go ahead and figure out our magnitude here. So magnitude of U is going to be 5 squared plus 12 squared. And hopefully you recognize that's, again, another Pythagorean triple. So that's going to be 13. This is in the first quadrant, so therefore I don't need to worry about using the reference angle here. So I'm just going to use theta equals tan inverse of 12 over 5. So tan inverse of 12 divided by 5. And that's going to be 67.38 degrees. Let's just round that to the nearest tenth. All right. Let's do the next one. Again, this one, let's see, magnitude of W, that's going to be negative square root of 3 quantity squared plus negative 1 quantity squared. So again, if you have a square root, like a negative square root times a negative square root, that's just going to give you 3. And then negative 1 squared is going to give you 1. So that gives me square root of 4, which is just equal to 2. Okay? And then if I was going to do the tangent in, so now I could say the tangent of theta equals negative 1 over negative square root of 3. So therefore, tangent equals tangent inverse of 1 over the square root of 3. Hopefully you recognize, though, without using your calculator, that this is the tangent of square root of 3 over 3, right? If you like rationalize the denominator and simplify that. And then hopefully you would also recognize that that is a coordinate point, that is the y coordinate over the x coordinate for pi over 6, so it would be 30 degrees, yet this angle is in my third quadrant again, right? So I believe this would be 210 degrees, but let's just go ahead and check our work. You don't need to refer to that. You could also just do tangent inverse of 1 divided by the square root of 3, and I get 30 degrees, okay? So again, just remember that your angle is down here. The reference angle is giving you that 30 degrees, so therefore you need to add it to 180 to give 210 degrees. All right, so for the next 2 points, now in this case, what we need to do is actually find the component form first. You don't need to, you could use the old formulas, but I think it's just easier when you have the initial and the terminal point, just to go ahead and find the component form. First thing is going from T to U, I'm sorry. So let's go ahead and call this, so TU in component form is going to be 4 minus 1, comma, negative 3 minus 0. And let's see, that's going to be 3, comma, negative 3. Yep. So therefore we can graph that, or we notice that that is again going to be in the fourth quadrant. So, all right, let's go and find the magnitude here. So the magnitude of TU is going to be 3 squared plus a negative 3 squared. And 3 squared is going to be 9 plus 9, so it's going to be 18, but we can just leave that as the square root of 18, which is perfectly fine. As far as the angle goes, again, hopefully you recognize that's going to be tangent inverse of, that's going to be tangent inverse of negative 1, right? It's just right over there. So that's going to be negative 3 over 3, which is equal to the tangent inverse of negative 1, which is equal to negative 45 degrees if you were to type that into your calculator. However, you could also write that in the positive version of 315 degrees. Now, it doesn't really matter if you want to use the positive or the negative. I tell students to typically when we're dealing with our problems, just keep it positive from there. But however, since my negative version is acute, sometimes people like to just go ahead and use the negative version, which is perfectly acceptable unless otherwise noted. For the next one, again, we're going to do the same thing. So let's go ahead and find the magnitude of this. So that's going to be x1 minus x1. And then this one's going to be 5 minus 0. All right, so that becomes a positive. So therefore, that's going to be 0, comma 5. So it's a negative 1, 0. Oh, why did I do second? So that's a 0, 5. Very good. Oh, you could have done the negative 15. Let's go. So that's going to be 0, 5, right? Yeah. Okay. So I'm like losing my brain here. There, the magnitude, that's not the magnitude. That's the component form of the vector. Sorry. Okay. The magnitude of Mn, that's going to be the square root of 0 squared plus 5 squared. which is just going to be the square root of 25, which is going to equal 5. And again, that makes sense, right? You have a vector with no horizontal component. It's just going up 5 units. Now, it's also important because if you think about that vector, you can think about this vector as really just going straight up. So what is that angle, right? Like, what is the angle that just goes straight up? 1, 2, 3, 4, 5. Well, that's going to be 90 degrees. However, if you want to use it, this would be tangent inverse of 5 over 0, which is the tangent inverse of 0, which is just going to also equal 0. I'm sorry, tangent inverse of 0, which would be 90 degrees. Sorry. Okay, and again, it makes sense. Tangent inverse of, no, sorry, wait a minute. Tangent inverse of 90 degrees is going to be 0. I wonder what I think I drank too much coffee. Tangent inverse of is going to equal 0, but that's not going to be 0 because we're looking at this vector. We know that's going to be 90 degrees. I'm sorry, that's right. That is actually undefined in this case. Yeah, that's undefined. What am I doing? I was wondering, I'm like, why is this crazy? Okay, so in this case, you can see that if you were to type this into your calculator, that's right, my apologies, this is going to be undefined. So that kind of comes to the question, well, how are we going to do this? Is there no vector? Well, no, there is a vector. It's going 0, 5, but we recognize it's straight up, right? So there is no slope. You can't divide by 0. And again, just by knowing what the vector looks like, that's why I said, that's why it's a lot of times it's just helpful to graph these vectors. You can see that even though it has an undefined slope, we know that the angle is going to be 90 degrees. All right. Then we worked on vector operations. So the vector operations we're going to cover in this class is going to be addition as well as subtraction, and then multiplying by a scalar k. So when we are adding vectors or applying a scalar, what we're going to use is what we call for at least adding and subtracting vectors, we're going to use what we call the tail to head method. So the way I like to just kind of show students with that is, I kind of gave them like a word problem, first of all. I said, if you were to, for instance, actually, let's go back. If you were going to walk 5 miles north, right? And this was a word problem we did like previously. You would look something like this, right? And we'd say 5. And then say, all right, then you're going to turn and walk 5 miles east. Well, you don't write your vector like this, right? And let's say walk 3 miles east. That doesn't make any sense. What we did is if you're walking 5 miles north, right? Then what we're going to do is we're going to put this vector at the end of the other vector, right? So what we're doing is we're taking the tail of one vector and adding it to the head of the other vector. So that's what we call the tail to head method. Okay, so when we're looking at graphing vectors or applying operations graphically, we're going to do that tail to head method. Just make sure you're taking one vector and put it at the end of the other vector. When you're applying the scalar, it's important that you understand that the scalar is being multiplied times both of those, times both components. So this represents u plus v. Okay, so you can take u and you can add v on either side, and then that is going to be what we call a resultant, our u plus v. Now, as far as the scalar goes, scalar could be multiplication, or it could it could be a stretch, or it could be a compression, right? But the main important thing to understand is when you are, expanding or compressing, you're not actually going to be changing our vector, right? You're just either stretching it or going to be compressing it. And it's really just kind of looks and just make sure you do it to both of those components. So let's just kind of go through, I think, just some examples I think would probably be easier than trying to look at some arbitrary vector. So what I did is I gave my students 4 vectors, and then I said, all right, let's just go ahead and practice applying the operations. Now, actually, that's the first one that I wanted to look at, actually. Let me actually go back to this, because there actually was one thing I was like, what do I need to actually change here? So one thing I wanted to talk about was addition, because addition kind of makes sense. Now, if I have my vector, and let's call this vector u. Well, if I was going to do, and again, remember, this would be like u1 and u2, right? Well, what if I have negative u? What would that look like? Well, again, what that's going to do is that's going to make u1 negative. So now my vector is going to the left, and it's going to make u2 negative, right? So now that vector is going in the exact opposite direction. Okay, so that's just important when you're dealing with the negative. And the reason why I bring this up is because when we are doing subtraction, it's pretty easy to understand addition. You can see you just take one vector and you add it to the other vector. Well, what about doing subtraction? Like, how do you subtract one vector to another? Well, the best thing I like to tell students to do is just rewrite the vector subtraction as addition. So that's the first thing I'm going to do here. Instead of thinking about this as subtraction, I'm just going to rewrite this as L plus a negative m. So now I can just treat that negative as like a -1, as like a scalar. So the first thing I'm going to want to do is identify, well, what is negative m? So if m is 2, 0, then negative m is -2, 0. Okay? So now let's go ahead and graph these. Because the algebraic part is really not that difficult. You just go ahead and apply the operations and you're good to go. But sometimes when you're looking into graphing them, understanding the negative can be difficult. Okay, so there's L. Then here, I'm going to have m, which is -2. Sorry, that's negative m. Okay? So what I need to do here is I'm just going to take the end of one vector and I'm going to add it. Should have just left this there. I don't know why I did that. I'm just going to take this vector and I'm going to approach it here at the end. So I'm just going to take this vector. Let me actually maybe do a different color. Maybe that'll help out. So all I'm going to do is now take m and put it here, up there, right? So again, I'm just taking the head or the tail of one vector and adding it to the head of the other vector. Therefore, when I connect my tail to my final head, that is going to represent my L minus m. Okay. Now, a lot of students say, well, could you have added L to the end of negative m? And yes, you could have. Right? That's what creates what we say like a parallelogram. You can see that you could also add L to the end of m. Or you could add negative m to the end of L. It doesn't really matter, right? Because like 3 plus 4 is the same as 4 plus 3. So it doesn't matter in that regard. That's why it's so important to change this to vector addition so you can easily do that. Now, as far as the operations go, you know, algebraically, all I'm simply doing is just taking my vector -1, 1, and then adding that to a -2, 0. Right? So if we look at this, all we're simply doing -1, 1, and therefore this is going to be plus, distribute that to a -2, 0. Now, I didn't really explain this or at least cover this really quickly. But again, notice that when you're doing addition, all you're doing is you're just adding the first two components of vector u and vector v, and then you're combining the second two components of vector u2 and v2, of the second components, I'm sorry. So here, all I'm going to do to find my addition, so L minus m is equal to -1 plus -2, which is -3, and then 1 plus 0, which is 1. And you can see, does that make sense? Like -3 up 1. And yeah, it works, right? So on the next one, again, we just need to understand what is happening to n. So I'm just going to cover this real quick, just so you can kind of see visually. And then, because the algebra is not really the big deal, I think the graphical part is actually the difficult part for a lot of students. So if n is 1, 2, -3, 1, 2, 3, there's n. Now, what if I do 2n? What is that going to do to the vector? Well, again, that's going to double 2. So now it's going to go over to 4. And it's going to double -3, which is now going to go to 1, 2, 3, 4, 5, 6. So you can see what's happening here is it's doubling that magnitude, right? It's like doubling how long that vector is. And then all I'm going to do is add that to vector p, which is 4, 2. So 1, 2, 3, 4, 1, 2. Okay. So again, you could do that vector either way. You could add p here, or you could take a 2n and add that there. It doesn't really matter how you want to do it. That's going to be our vector right there. That's going to be 2n plus p. Now, as far as the algebra goes, let's see if this like makes sense. So for this, we'll do 2 times 2, -3, plus 4, 4, 2. All right, so therefore I have 4 comma -6 plus 4, 2. Bad penmanship. And now we just combine our first two components, which is going to be 8 comma -2. And let's just check that out. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. So my graph is off a little bit, but hopefully you won't be too mad at me and you can kind of see that. Let's just kind of make it like that. So I'm not perfect on mine, but hopefully you can see that I'm pretty close. Oops. Okay, again, I'm not dealing with graph paper. But again, if you would, that's what you'd want to do. So here are just some of the problems that I gave my students just to kind of practice. I asked them to go and do it algebraically and then graphically. I think a lot of times, guys, it's just going to be easier just to do the algebra first and then to kind of come back and do them graphically. So therefore, this is going to be 1, 1. So really just do a vector. So like L, so -1, 1. And then I do a vector 2, or M. And you can see that that's going to give you up 1, 0. Right? Because if you were to plug that back into there, that's M, L, and that was M. Actually, you know what? I'm not going to do those two vectors. I'm just going to draw both those vectors, and then I'm going to draw the component. I'm not going to connect them. I'm just going to do that's M plus L, which would make sense if you were going to go ahead and do that. For P minus N, let's just go ahead and distribute this. So this is going to be 4, 2 plus -2, negative, oops, I'm sorry about that, plus a -2, -3. All right, so therefore this becomes a 4, 2, and this becomes a plus a -2, +3. Then I'm going to add those to give me a 2, 5. So we'll go ahead and graph P, so which is 1, 2, 3, 4, up 2. Let's go ahead and graph N, which is 2, -3, 1, 2, 1, 2, 3. And then you can see P minus N is going to take us 2, 2, 1, 2, 3, 4, 5. And again, you can see that how it kind of works into that difference of those two vectors. Because this is P. No, that's not right. That's P, 4, 2, minus N, which is, oh, I did it wrong. That's 2, -3. 1, 2, 1, 2, 3. I was wrong. I'm like, that doesn't make sense. There you go. Now you can see how it would be that opposite. All right, next two examples here is, again, same vectors. Now we're just doing, again, a little bit different. So in this case, I'm going to have L, which is -1, 1, plus 1/2 P, which is 4, 2. So that's -1, 1. And therefore, now this is going to be a 2, 1. So therefore, that gives me a final resultant vector of 1, 2. So let's go and graph that. So we have -1, 1. So -1, 1. And then we have 2, 1. So that's going to be up there. And again, that vector was originally 4, 2, right? So it got compressed by half its size. And therefore, that's going to be L. That's going to be 1/2 P. And now you can see that my resultant vector is going to be 1, 2. And you can see how that goes ahead and works. Last example here is -2n minus M. So again, this one, we have a lot of subtraction here. So I'm going to write this as a -2 times n, so 2, -3, plus a -m, which is 2, 0. Okay, I'm just going to go ahead and distribute here. So this would be a -4 plus 6. Why am I writing plus 6? -4, +6. And therefore, that's going to be a plus a -2, 0. So that's going to give us a -6, 6. And now, again, you can see that in this example, if I was going to graph both these vectors, I'd add -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. That's -2n. So not only is it reflected about the origin, which is another thing I actually didn't talk about, or I think I did, but when you reflect if you reflect the x and the y vector component, you can see it's also a reflection about the origin. So the negative is reflecting that across the origin as well as stretching it by 2. And then we have m, or -m, which is a -2, 0. Okay, And my final answer is going to be a negative 6, 6. So that vector, let's put that right there. So if you were to combine those two, you can see how that works right there. Whew. All right. The next one is what I talked about with students was how to find the scalar, determine the scalar that produces a magnitude of 1. So this was one of those kind of discussions that I just brought up with students. Like if we wanted to have a vector that had a magnitude of 1, like what would we need to do here? Well, what I told students is a lot of students, they, again, kind of going back to our initial answer is let's just graph it. So 1, 2, 3. So if I wanted to have this vector to only have a magnitude 1, instead of going over 3, I would just want to go over 1. Right? So the value k that makes the scalar equal to 1 would be 1/3. So I could rewrite this. So the magnitude of s is going to equal 1 when I multiply this by 1/3, 0, 3. Okay, same kind of thing here. A lot of students had a little bit more difficult understanding this one. So there's like, I don't know what I need to do, but hopefully you kind of recognize something that this looks very similar to maybe points that we've dealt with on the unit circle. That's just... and maybe if you see that if you took this as t equals 1/2 times 1 comma square root of 3, then this would give you 1/2 comma square root of 3 over 2. And obviously that means, that terminal point is on the unit circle. Well, again, remember the unit circle has a distance from the origin to the point in the circle is obviously 1. So therefore, again, here, the magnitude of t is equal to 1. So the point that I was trying to really kind of make to these students is, obviously, if we can take a vector and divide it by its magnitude, that's going to give us the same vector in the same direction, but it's just going to have a magnitude, or I'm just going to have a length of 1. And again, think about it. Like if I have something that's 5 meters long and I only want it to be 1 meter long, I'm just going to take that and that distance 5 and divide it by 5, right? 5 meters divided by 5 is just going to give us 1. I'm going to break it up into 5 different parts where they all have a magnitude of 1. So that's exactly what we're doing here because again, like here, I don't know why I keep on writing that. If you were to think about this, like what is the magnitude of t in this case? Like if I did the magnitude of t, then that would be 1 squared plus the square root of 3 quantity squared. Well, that's going to equal 2, right? Same thing here. The magnitude here is going to be 3. So all we're doing is we're just multiplying our vector by 1 over its magnitude and we'll get a vector with 1. So if I want to ask the same question here, all I'd simply do is find the magnitude of r, which is going to be the square root of 1 plus 1 squared plus 2 squared, which is going to equal 5. And therefore, my scalar, k, I should just write that, determine the scalar k. So therefore, k is equal to 1/3. K is equal to 1/2. In this case, k is going to equal 1 over the square root of 5. Okay. And again, the purpose of this is a lot of times it's going to be a little bit easier to deal with vectors to understand their angles. So like again, like for instance, if we know that a vector has a terminal point on the unit circle, it's very easy for us to understand the direction or the angle of those vectors. So that's a whole bunch of things which we call the unit vector. So a unit vector is basically just a vector that has a magnitude of 1. We can easily convert a vector to its unit vector by keeping the direction and the angle the same, just by taking that vector and dividing it by its magnitude. And that's really all we're doing. Again, it's just converting that, taking that vector. So let's just kind of let me do a little picture here real quick. So if we have that vector, let's say vector v, and then we have this like unit circle here, right? This is going to be our vector u, where u is again just taking that vector and dividing it by its magnitude. And again, what's that nice is if we know the unit vector, all we got to do is multiply it by a different scalar now to go ahead and get to different vectors of different magnitudes, right? We have the vector the unit vector. So we have the direction or the angle, and then all we got to do is multiply by different scalars to get different magnitudes. And more importantly, that also brings us into our standard unit vectors, which is going to be our I and our j. I does not represent the imaginary unit I, but I represents what we refer to as just our horizontal unit vector, and j represents our vertical unit vector. So any vector we can write in terms of i's and j's, which brings us what we call to another combination for vectors, which is the linear combination. So anytime you have a vector, v1, v2, you can also write them in terms of I and j just by putting the v1 in front of the I and the v2 in front of the j. Here is why that works. You can basically think of v1 and v2 as scalars of our unit vectors, like you're multiplying like them through. And that's basically how that works. The other way that I like to think about it, like if I have, for instance, like I gave an example in my class, I said, all right, let's say, here's my vector. Let's say that's 3, 4, 3, 4. Well, how many unit vectors did I have to travel, right? How many horizontal unit vectors did I have to travel there? Well, I had to go 1i, 2i, 3i's, right? 3i's is, 3 horizontal vectors is 3 units. And the same thing up, I had to do 1, 2, 3, 4. So I and j, they're kind of like they're the building blocks. These are the vector building blocks that allows us to understand vectors using our unit vectors. So again, we could just say 3i, right? You're doing 3 horizontal unit vectors plus 4 vertical unit vectors. But again, I tell students not to get hung up on the I and the j. If you don't like one, just easily go ahead and convert it to the other. All right, but I did want students to practice identifying the unit vector. And so therefore I just kind of covered these two. Basically what we're going to do is just determine the unit vector. So therefore we need to identify the magnitude, which I thought I wrote this in there. I can't believe I didn't do that. Oh, jeez, I can't believe I did that. All right, so let's call this R, and we'll call this one S. All right, so the magnitude of R is going to be the square root of -2 square root of 3 quantity squared plus 2 quantity squared. Now again, before you go ahead and whip out your calculator, -2 squared is 4. Square root of 3 squared is 3. So 4 times 3 is 12. And 2 squared is 4. And therefore you can say that's the square root of 16, which is 4. Now again, there's a lot of different ways we can write the unit vector. We could write it as 1/4 -2 square root of 3, comma 2. Right? And that'd be perfectly fine. Sometimes also we'll write it just as all divided by 4, which I think I'll get to. Yeah, I'll use that in some other variations. So that is one way that we could represent the unit vector. The next one, here we have in terms of I and j. So again, when we write the unit vector, we're going to want to write that in terms of I and j. If you don't like using I and j, you could go ahead and convert that to component form, just so you can go ahead and do the math. But again, guys, like the math is still the same. Like you're not doing anything differently. Here you're going to have 5 squared minus, 5 squared plus -6 quantity squared. Actually, I decided to change that. I'm going to change that to a 4. I thought I changed all these. I can't believe that. Yeah, let's change that to a 4j. Here. Yeah. That's a 4j. Okay, so now we're going to have 25 plus 16. So that's going to be a 41. All right. And so now, again, if you were to think about that, you'd have 1 over the square root of 41. And then that's going to be times here 5i minus 4j. Right? Now, again, I'm using parentheses here because this is not in component form with the slant in the parentheses. But now I can just distribute this just like we did with the scalar here. So now my unit vector, honestly, so I'll just call this u. My unit vector is now going to equal 5 over the square root of 41, I, minus 4 over the square root of 41, j. All right, So then I just had a couple other examples for my students to go ahead and work on. Hopefully you're kind of getting a little bit better at this as far as identifying the unit vector here. So let's see, I call this RS, let's call this T. So therefore the magnitude of T here, let's see, that's going to be, that's just going to equal 5. That's a good one. So again, another way you could write the unit vector is just like this, -3 over -4 over 5, right? You can, instead of multiplying by a fraction, you could also just write it like that. I and J, let's call this one W. So the magnitude of W is going to be, hopefully you recognize that's going to be the square root of 2. So we could just write this as 1 over the square root of 2 times I plus J. Right? Because again, that's 1 plus 1. So that'd be 1 squared plus 1 squared, which is 2, square root of 2. Now the next two are the ones that I really like to kind of look at. In this next one, you think about this like, well, should I go ahead and figure this out? And yeah, probably, right? So here we kind of have some math here. Now again, this isn't too bad because the cosine of 60 degrees, hopefully you recognize the cosine of 60 degrees is going to be 1/2. And then here the sine, that's going to be 5 square root of 3 over 2. Okay, so I'm going to go ahead and type this into my calculator. Let's call this W, let's call this Y, or let's call this Z. Yeah, we'll call this one V. Okay, so if I wanted to find the magnitude of Z, what I'm going to do is I'm just going to type this into my calculator. So that's going to be the square root of 5/2 squared plus 5 square root of 3 squared. So just go ahead and type this into my calculator. I have 5 divided by 2, quantity squared, plus 5 times the square root of 3 divided by 2, quantity squared. And then the square root of that, which I notice is, wait a second, that's 5. Okay, so 5 was right there. Now, is that always going to be the same? And I could obviously just rewrite this here as this unit vector would now just be, you know, if I just wrote this as like 1/5, 5 cosine of 60 degrees, sine 5, sine of 60 degrees. Well, my unit vector, if you guys notice here, is just going to be cosine of 60 degrees times the sine of 60 degrees. And again, that makes sense, right? Because the cosine of 60 degrees, sine of 60 degrees, that coordinate point, if you think about that, is 1/2 comma square root of 3, 2. Well, that's a point on the unit circle. So what this is looks like a vector is being represented by, if I have cosine and sine, whatever I'm multiplying it by, that's the magnitude. Whatever the angle is going to be the angle, which we're going to get into next. Obviously, you can see magnitude and angle. For the last vector, I think this one is kind of rather simple. Again, just kind of goes back to the idea of what we kind of covered first is -3. You can see, oh, that's a vector to the left, 3 units. So therefore, my unit vector is obviously going to be only in terms of i's and j's. So u is going to equal -I. Let's call our u here. But to build upon this last example, which we call our magnitude and our angle. So if we're given a vector v with an angle theta, that can be written as the magnitude. Vector v can be written as the magnitude times the cosine of angle, sine of the angle. And again, that's because the cosine of angle, sine of angle is your unit vector, and then you can just multiply it by its magnitude. Now again, that magnitude is like a scalar. So therefore, you're going to distribute that magnitude to both your cosine of theta as well as your sine of theta. All right. So the last thing I just wanted to do with my students was I just said, you know, let's just practice writing things in component form. So again, you can just write this as 2 cosine of 135 degrees. Actually, let's write this on the outside here. So 2 times the cosine of 135 degrees times the sine 135 degrees, right? And then you can distribute that. I'm just showing my work. You don't need to do all of this. And now, thankfully, we know that the cosine of 135 degrees is, again, cosine of 135 degrees is in the third quadrant. So cosine is going to be negative as well as sine will be negative. And if you recall, that angle is square root of 2 over 2. Oops, I'm sorry. Why am I making that negative? Let's put it inside the parentheses. Okay, so that's from the unit circle. And therefore you can see now my component form is negative square root of 2, comma, the square root of 2. Now, obviously, I'm going to choose two problems that we are aware of on the unit circle. But again, if you are, if you're using a calculator, then obviously we could also do these for rounded. So the exact same thing with this problem. Again, you could use negative angles. It doesn't really matter. You don't have to use positive. You could use the coterminal positive angle though. But in this case, I'm just going to take 1200 times the cosine of negative 30 degrees times 1200. Just make sure you distribute that to both terms times the sine of negative 30 degrees. Okay, so now I just need to make sure that I know sine of negative 30 degrees. That's going to be a positive square root of 3 over 2. And negative 30 degrees is going to be a negative 1/2. Okay, so that's going to be a 600 times the square root of 3, and this is going to be a negative 600. And again, you always just want to make sense of your component form. Like, should that take me into the fourth quadrant, right? Negative 30 degrees is going to be taking me to the fourth quadrant, at least for you guys. Well, if I go over 600 and then, or 600 times square root of 3 and then down 600, you can see again that takes you to the fourth quadrant. So you can always check your answer to make sure that your angles are going to be taking you back into component form. So there you go, ladies and gentlemen. That is the end of our lesson. I hope you enjoyed. I hope you learned a little bit about vectors, how we represent them, and as well as how all the different operations that you can apply when dealing with vectors. I look forward to seeing you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on applications of vectors. Now, this is actually our 5th lesson in our chapter for applications of trigonometry. And this is the exact same lesson that I gave to my students within the classroom. So what we're going to learn in this lesson is basically how to apply the dot product as well as determine the resultant vector from a word problem. And this is a fairly basic lesson. I know I can go in a lot more in depth, but because this is such a large chapter and a lot of the content is out of the scope of my class, we kind of keep things basic for this section. So I kind of start right in with the dot product. And again, I don't go into much detail for our class. We just kind of present them with the material and we just kind of practice it. So therefore, when they have to go out and apply the dot product later, it's something that they've seen. So the dot product is basically going to, it's not vector multiplication. It's basically going to be when you have two vectors, it's the product of the horizontal components. You can see U1 and V1, as well as a product of the vertical components, which would be U2 and V2. And you add those up and what you're getting is actually a scalar. And then some really cool videos that you can see like how that works with the vectors. But because I don't want to spend too much time as far as explaining and understanding dot product, I just want to make sure that students understand what it is we are trying to find and as well as how to find the dot product. Now, the important thing about the dot product is when the dot product is equal to 0, then that means that your two vectors are going to be orthogonal or parallel, which I'll get into in a second. When the dot product is positive, that means the two vectors face the same direction. And if they're negative, that means they're going to be facing in opposite directions. So those are just some things that you can see. And again, there's some great, kind of videos, tutorials where you can kind of understand a little bit more of the dot product, but it's just a little bit beyond the scope of our class. So I'll just say orthogonal. All right, so the next thing about the dot product, which helps us then, is it helps us determine the angle between the two vectors. So if we want to determine the angle between the two vectors, we can use this formula, cosine of theta equals the dot product of u times v divided by the magnitude of u times the magnitude of v. And again, just kind of going back through here, if I have two vectors, actually, let me just kind of do this actually up here. So remember, orthogonal is going to be if they're right? So if I have the u dot v is a positive, then we're going to have two vectors in the same direction. And if I have them in opposite directions, not necessarily in exact opposite directions, so that one would be negative. Oops, I'm going to say u dot v would be a negative. So let's just call this one u, and that's v. So again, you can kind of see this scalar. What the dot product does is it produces a scalar, and it tells us kind of how these two vectors are going to be related, at least that scalar multiplication of each other. And again, if it's positive, they're in the same direction. And then obviously if it's 0, then they're orthogonal or perpendicular. And then negative meaning they're going to be in opposite directions. So we can go a little bit further with the dot product to actually identify what that angle is between those two vectors. And that's just going to be using this formula right here. So again, it's a good problem, at least for my students. They get to practice applying the dot product, the magnitude, as well as using the cosine inverse. But we don't get into too much detail as well, with the formulas, or at least deriving the formulas. Just kind of one of those, I want them just to kind of be getting used to everything. So now we just kind of get into the general idea of that parallel and orthogonal vectors. So if two vectors, u and v, are orthogonal, that means the dot product, u dot v, and again, a lot of times I want to make sure this dot is going to be nice and thick for the students, u dot v is going to equal to 0. So that scalar product is going to be 0. Now, if the two vectors are parallel, then the dot product is either going to be or the angle between them is either going to be 0 or 180 degrees. So if the angle is 0, now again, these are just kind of vectors that are not in component form. Obviously, if they're in component form, they'd be right on top of each other. But you can see if they're two angles like u and v have 0 in between them, then it's obviously the exact same vector. They're pointing in the exact same direction. And then if the vectors have 180, you can see that they're going in opposite directions. But we're considering them parallel because at least the slopes are going to be the same. All right, so that's kind of how I started with the students. I said, all right, let's go ahead and just find the vectors or find the angle between the two vectors and then determine if they are orthogonal, parallel, or neither. Now, I did allow the students to first apply the dot product, and therefore, if they identified the dot product to be 0, like in the first example, then they could just justify that the angle between them is 90 degrees and that the two vectors were orthogonal. So in this first example, the first thing we did was find the dot product, and therefore you can see we got it to be 0. And again, if you look at this formula, like go back to the formula, you're going to have to identify, not that one, this one, you're going to have to identify the dot product anyways, and then the magnitude of u and v. So you might as well do the dot product first. If you get 0, then you're going to know that they're going to be orthogonal. Now, this next example, I do the dot product, right? So now I have w and t vectors written as a linear combination. And however, when I do the dot product, though, I get negative 51. So that doesn't tell me enough information at this moment to determine if they are parallel or orthogonal. Well, I'm sorry, they're not orthogonal. So I don't know if they're parallel or not. So then what I'm going to do is I'm going to continue with identifying the magnitude of w, which is going to be the first component squared plus the second component squared, so which is square root of 104. And then I do that again for t, which gives me the square root of 26. So now I plug them all into this formula for the cosine of theta equals there. And then when I go ahead and simplify this, I get negative 1. And again, like you could type this in your calculator if you want to, but again, really what we're looking for when we're doing these two vectors, if we're determining they're parallel or negative, 0 or 180 degrees, we're going to be looking for cosine of theta to equal negative 1 or for it to equal positive 1. And you can see in this case, since cosine of inverse cosine is equal to negative 1, we know that angle is going to be 180 degrees. So therefore, we can consider these two vectors to be parallel. And then what I did is I just gave the students some more examples. I said, all right, let's go ahead and practice some more and kind of see how you guys do. So I gave them these two as well as these two vectors as well. So let's just go ahead and work through these. Again, the first thing I like to do when doing these problems is just to apply the dot product. And again, if you kind of get stuck sometimes, you can always label them as their components. Okay, so this is U1, U2. This is going to be V1, V2. And again, a lot of students want to go ahead and write this as a vector. So just be careful. Use parentheses. When you're applying the dot product, you're looking for the scalar, not a vector. So this is going to be negative 2 times 6. So therefore, that's going to be positive 12 minus 12, and you can see 0. So again, right off the bat, we're getting 12 minus 12 is 0. So therefore, we can say that U and V are orthogonal. Or we'll just write orthogonal. So on to the next problem. Again, first thing we're going to want to do is identify the dot product. So I'm just going to do C dot D. And that's going to be, again, the first component, 6 times negative 3. Now, again, some people don't like using the I and J. So, again, if you want to write this in component form, go ahead. That's fine if that makes it easier for you. So I'm going to multiply 6 times negative 3, and then I'm going to add that to the product of 5 times a negative 5 halves. Okay, and when I go ahead and do this, let's see, I get this to be a negative 18, and this becomes a negative 25 halves. Now that doesn't look very nice to go ahead and complete. Now obviously I could go ahead and multiply. I could rewrite this as a fraction. But again, I know that at least it's not going to give me 0. So if I was just to go ahead and rewrite this, let's see, I could rewrite this as a negative 36 divided by 2 minus 25 over 2. And therefore you can see that, right, I can write negative 18 as negative 36 over 2. Sorry, I didn't mean to do that. And therefore, then I would have a negative 61 over 2. Okay, so that's going to be my dot product, which obviously is not going to be orthogonal. Now, the next thing we're going to want to do is identify the magnitude. So let's just go ahead and find the magnitude separately here. So I'm going to have the magnitude of C. So the magnitude of C here is going to be, let's see, it's going to be 6 squared plus 5 squared. So 6 squared is going to be 36 plus 5 squared is going to be 25. So therefore that's going to equal the square root of 61. And then for B squared, or I'm sorry, the magnitude of B, that is going to be the negative 3 squared plus, let's see, that's going to be a negative 5 halves squared. Okay, and that's going to be the square root of 9 plus 25 fourths. All right. Now, again, some students are like, all right, that looks kind of confusing here, 25 fourths. Like, but again, like we can type all this stuff into our calculator, right? Like when we're using a calculator, because that's what we're going to, my students will have access to this for a calculator. We can just go and type this all into a calculator. So I have cosine of theta is going to equal a negative 61 over 2, which you could easily divide, right, as 30.5, divided by the product of the square root of 61 times the square root, and again, that's not the dot product, but it's multiplication, 9 plus 25 fourths. And again, that's what I'm just going to be typing into my calculator because I just want to avoid, writing down any kind of or any kind of decimals into the calculator. So I'm going to take a negative 61 divided by 2. And we're going to divide that by the quantity. And again, you want to make sure when you're doing this, when you're typing this in your calculator, make sure you put the denominator in parentheses. So that's going to be the square root of 61 times the square root. And again, your calculator will follow order of operations here. 9 plus parentheses 25 divided by 20, or I'm sorry, divided by 4. Okay, so I'll close a parenthesis there, and then I will close the parenthesis of the denominator. Open, open, close. And I get negative 1. Interesting. Well, again, remember, if cosine of theta is equal to negative 1, that means those vectors go in opposite directions. So therefore, the angle between the two vectors, so therefore theta is going to equal 180 degrees, right? If you have your vector, sorry, let me just go and draw this real quick. If you have 180 degrees, you can see that these vectors are going in opposite directions, right? So therefore, we have a vector, there's going to be negative 1. So you can see they're going in opposite directions. So therefore, these are considered parallel. Okay, now let's go back into red. All right, next example. Again, we have another linear combination. So I'm going to go ahead and follow through on this. In this case, we have A and B. So I'll go ahead and do the dot product. What do I want to do? So the dot product, so that's going to be A dot B. So that's going to equal 7 times negative 2 plus 2 times negative 7. And therefore, we look like we have negative 14 minus 14. So it looks very promising, but this actually gives us a negative 28. So it's not going to work in this case. Then the next thing we want to do is go ahead and identify the magnitude of A. So the magnitude of A in this case is going to be the square root of 7 squared plus 2 squared. And hopefully you recognize that the magnitude of B is going to be exactly the same, because if you think about this, it's just negatives, right? And you're squaring the negatives. So that's going to be negative 2 squared plus negative 7 squared. So again, 7 squared is what? 49 plus 2 squared is 4. So therefore, that'll give us the square root of 53 and the square root of 53. Now, when I want to find this angle here, I'm going to have the cosine of theta is equal to negative 28 over square root of 53 times the square root of 53. Now, let's think about this for a second. The square root of 53 times square root of 53 is just going to be 53, right? So therefore, I can also rewrite this as the cosine of theta equals negative 28 over 53. Therefore, theta equals, and again, this is going to be something, theta is going to equal the cosine inverse of negative 28 over 53, which equals, I don't remember, so I'm going to type it in, negative 28 divided by 53, cosine inverse of that answer is going to equal 121.89 degrees. Okay, so you can see that's going to be the angle of those two vectors, which makes sense, right? They're pointing away from each other because our dot product is negative. And again, that works as well. In this case, you can see that these two vectors are pointing away. You can see the dot product is a -1. Now, the next one, again, I have some fractions. Now, in this case, I'm going to do a little bit of a trick that we can follow. And I'll show you 2 steps that you could do here to make this problem a little bit easier for you, depending on what the question is. Now, the first question I want to tackle is let's just identify the dot product. I think with the dot product, we want to be able to, again, the dot product is giving us a scalar. So we want to identify this dot product and just make sure we can do this even if we have fractions. That should not be changing our answers or as far as what we can do here. So in this case, we have 1/2 times 2, that's going to be 1. And therefore, this is going to be a negative 3/4 times negative 3. Let's see, that's going to give us a positive 9/4. Now, if I combine that, the 1, I could rewrite that as a 4 over 4 plus 9/4. And you can see my answer is 13/4. Okay, so without using a calculator, just knowing my fraction operations, I can identify this dot product. Now, when it comes into identifying the angle between the two vectors or determining if they are, orthogonal. I know they're not orthogonal, I'm sorry. Determine if they're parallel or not. I'm not going to, want to do calculations with these fractions. Even though I have a calculator, it's still a lot. Nor am I really going to want to plug them into my calculator or use decimals or anything. So there's one thing I just want you to think about. 2 kind of things we can do. First of all, if we're looking at 2 vectors, and if we're trying to identify like the angle between the 2 vectors, if I use scalars of these 2 vectors, you can see that the angles don't change, right? If I shorten a vector or lengthen a vector, it's still going to give us the same vector. So one thing we could do is instead of using the angle between u and v, why don't we use the angle between u and 4v? Because if I multiply this by 4, I'm going to have 2 minus 3. Now I'm not dealing with any fractions. It's a lot easier for me to be able to work with this, okay? The other thing you can see is, again, like when things are parallel, yes, you can see that they're pointing the same direction or pointing opposite direction, like the angle between them is 0 or 180 degrees. But that's a lot of work to identify if things are parallel or not. What I prefer to do is also just look at the slope, right? Remember, the slope is going to be the rise over run. So if I have negative 3 over 2, now obviously you see once I transfer this, what the slope is. But negative 3 over 2, that needs to be equal to negative 3/4 over 1/2. Well, again, this is just a fraction over fraction, right? So multiply by the reciprocal. Oops. So I have 2 over 1 over 2 over 1. And guess what? That's going to equal a negative 3/2. So without actually having to calculate the answer, and again, if you need to figure out the angle between them and you have fractions, I would use that scalar and use the calculations with that rather than dealing with the fractions. You can obviously do the fractions, but it just makes up for more opportunities to make mistakes. So that's what I'd recommend you do, is look for, when you only have one fraction like this last example, it's not the end of the world. It wasn't bad, but you could have done the exact same things I just explained here up here, and it probably would have been a lot easier now that you know. But I wanted to show you how you could work through that example, even if you have fractions, by using your calculator. But again, a lot of times just look at, using scalars of their vectors to avoid the fractions. Again, this works in this case for the angle because it's not going to impact it, as well as, just identifying if they're parallel or orthogonal. All right, so that was kind of our applications of the dot product. That's about as far as we went with that. And then we're going to get into some tips for doing word problems. Now, a lot of these problems are actually going to be from our last section when we were just kind of talking about vectors. But I just wanted to kind of explore them a little bit more in this section rather than the first section, because the first section was just like a lot of content. So when we want to identify like word problems using vectors, the first thing we want to do is draw a picture and label all its parts. Then what we want to do is identify the vectors provided and that are needed to solve. So, whatever we're kind of looking for, we want to make sure we understand them. And the last thing is we want to define our variables and set up any equations. And then last but not least, we want to solve and check our solution. Basically, checking your solution is not like checking your work, but checking to make sure your solution like makes sense. So the first word problem that I did for my students, or at least I went through step by step for them, was talking about an airplane is flying across country due east. So it's going due east at 323 miles per hour. So you can see here, I represented this as a vector going due east, 323 miles per hour. And there's an air current at a bearing of 60 miles per hour. So I represented this bearing here at 60 miles per hour, at a bearing of 60 degrees at 15 miles per hour. Now the question was saying, what is the actual speed and bearing of the airplane? So what we got to do is like kind of think like, I gave my students this understanding that, that they could relate to. Like when you're outside and you're running and you feel like wind at your back, you're going to start running faster and you actually are going to be going faster, right? And the contrary, like if you're running, you get this big gust of wind going against you, that's going to be slowing you down. You're going to have to work harder. So if we're trying to look at like, what is the final thing of the plane? Now, again, this is the plane that's not like correcting. And I know for the physics students, we're not taking in any kind of resistance or gravity or all those other things. We're keeping things very, very simple for this lesson. But if I have an airplane that, is heading out in this direction at this speed, and this wind is able to affect the airplane at 15 miles per hour at a bearing of 60 degrees, what is that going to do to the airplane? Assuming it's not like self-correcting or anything. Well, what we're looking for is really the airplane plus the wind, right? Because we need to take into account the airplane as well as we need to take into account the wind. Now, I didn't write this up here, but I should do this. So what we're going to do is we need to take into account the magnitude as well as the angle of each of those components. And that is a component that we worked on in our last class period, that at least we explained, as any vector can be represented by its magnitude as well as its angle. So what I did is I say, all right, so I'm going to have the airplane. I'm going to represent that as vector A. So you can see it written here. It's going 323 miles per hour at an angle, at a bearing of at an angle of 0 degrees, right? Even though that's a bearing, it's going due east. But remember, your calculator, which we're going to be using, your calculator only understands standard form. So even though the problem's in bearings, we have to make sure like, yes, that's 90 degrees bearing, but that's 0 degrees standard form. So it's going to be cosine of 0, sine of 0. Now, the nice thing about that is that gives us a unit vector, 1, 0, right? And you can easily distribute the 323, distribute there to give 323, 0, which makes sense, right? You're going to have, if you're representing the vector, it's going to be 323 horizontal and nothing up or down. Now, as far as the wind goes, I didn't plug in 60. Instead, I plugged in 30. And again, this is very important because the bearing is 60 degrees. That's from due north to here is 60 degrees. But again, our calculator is only going to understand this in standard form. So from here to here is 60. That means from here to here is going to be 30 degrees. So that's why we got to make sure we're using 30 degrees as our angle. Now, again, the wind is 15. So what I do is I calculate. Now, thankfully, 30 degrees is on the unit circle. So that's going to be square root of 3 or 2, comma 1/2. And then you're going to distribute the 15. And you get 15 square root of 3 divided by 2, comma 15 over 1/2. And again, you could convert those and store them and stuff like that. But I wanted you to see, what is it we're looking for? And again, we're looking for this magnitude. Here's this equation that I was talking about. We want to find, actually, I don't know why I wrote that like so far away. What we're looking for here is A plus W, right? So A plus W is going to be the airplane plus the wind. So when you add the airplane plus the wind, you're going to get this vector. Now, again, since we have the square root of 3, this gives us a irrational number. So therefore, I stored this as alpha A. And again, you don't need to store this. You can pretty much probably use the answer or at least write down the multiple digits and you'll probably be okay. But I wanted to store it just because, one, it's a lot faster to type this into my calculator once it's stored. So therefore, I found the magnitude of my A plus W. And again, you could give this another name like V if you wanted to, or R as resultant vector. But again, this is going to be square root of first component squared plus second component squared. And then that gave me 336.07 miles per hour. Now again, I want to stop. Does that make sense, right? If you're traveling 323 miles per hour and you have wind at your back pushing you forward, not 100%, not like directly behind you, but at an angle, then it makes sense you're going to go faster, right? But not all the way, you know, an extra 15 miles per hour faster because it's at an angle. So 336 miles per hour makes sense. And then in the same respect, we have the angle of the vector. And we ended up doing the angle. I do tangent inverse. Or sorry, I should probably write that in there. Just because some students still get this wrong. So theta equals tangent inverse of 7.5 over A. Okay, so theta equals tangent inverse of 7.5 divided by my stored answer A. And that gives me 1.27 degrees. Now, again, like that's not the bearing. So what I did to find the bearing is I subtracted that from 90. So I did 90 degrees minus 1.27. That's how I got my bearing. Right? Because again, the 1.27 is just giving you this angle down here. Very, very, very small. Now again, that's a really, really small angle, but it doesn't make sense. Like you're going 323 miles per hour. That's really, really fast. And there's only a wind at 15 miles per hour. So yeah, it's going to take you off course, but you have so much speed going horizontally, it's not going to take you that much off course. It's not going to take you that much off course from there. We're only at 15 miles per hour. So that's how we went ahead and solved the problems using vectors. Then we kind of went into, just so I wanted students, a lot of students have trouble with this, is writing the expression of an equation using a vector. So that's what I wanted to help students out with this. And I did ask them also to sometimes draw a picture, and I think I might have a little bit. I'll try to fit in some pictures here. So this one, a boat is traveling at a bearing of 263 degrees. So what we're going to do is we're going to have a boat 263. So that's going to be down there. Right? That's the bearing. Now again, that's going to be 30 miles per hour, but that's not the bearing that's not the angle in standard form. So an angle in standard form here is from there to there. So again, if this is 263, then that means this has to be what, 7 degrees? So therefore my angle is going to be, so that's going to be 180 degrees. So it's really, really important. Let me actually change that up. There you go. So you can see from here to here is 7 degrees. From here to here is 263 degrees, but that's the bearing, right? Well, again, when we're using our calculator, we can't use the bearing. We have to use our angle. So therefore, this is the standard form is going to be 187. Sorry, that's the angle. How far am I traveling? 35. So it's going to be 35 times the angle cosine of 187. Oops. 187 degrees, and then the sine of 187 degrees. And again, I didn't want students to actually solve this. I just wanted them to practice setting up the equation. And that you can see when I did the word problem, that's the first thing I did, right? I found the vector for the airplane, and then I found the vector for the wind. So it's a really, really important thing to be able to take from the word problem what your vectors are going to be. The next one says a plane is traveling 300 miles per hour as it begins to descend for landing at an angle of depression of 15 degrees. Now, again, we understand an angle of depression is going to be an angle below the horizontal, right? So we have a horizontal, and then we have an angle of depression. So that means the angle is going down. So again, if we wanted to think about this in terms of like standard form, we want to make sure that we're going to represent this as a negative, right? Because like, even though this is like if you're going down, you can see like my y, like that's going to be representing the plane in a downward direction. So we have 300 miles per hour. And then we're not wanting to use positive because positive would be giving us a, x and y that would be both positive. We want to represent that y coordinate to be negative. So therefore, I'm going to use cosine of negative 15 degrees and the sine of negative 15 degrees. All right, the next one is a cart full of children is being pulled up a ramp at an angle of elevation of 2.5 degrees. So again, now we have like a nice little ramp. And again, some people did really, really well with drawing a nice cart full of children. I'm not going to do anything special, but there we go. I have a children and they're being pulled. Okay. But this angle of elevation here is going to be 2.5 degrees. And then the force is going to be 4 pounds. So in this vector, again, since it's an angle of elevation, we want that to be positive. So therefore, that's going to be 4 times the cosine of 2.5 times the 2.5 degrees, and then the sine of 2.5 degrees. All right, and then lastly, we have a rope is being horizontally pulled by a truck due west of a car stuck in a ditch with a force of 1,500 pounds. So again, that due west is telling us, all right, there's this horizontal pull, right? And so here's a car, car stuck in a ditch, and it's being pulled by a truck, right? So, there's the truck going in, pulling the truck westerly, right? It's in a ditch. Now, again, we need to understand that that has a force of 1,500. And again, like, what is the angle? Like, how do we represent this horizontal, this west angle? Well, that's going to be used, if we were to think about this, like, what is this force on the car? That's going to be an angle of 180 degrees. So we can say 1,500, and that's going to be times the cosine of 180 degrees, comma, the sine of 180 degrees. All right, so then when students got a little practice with setting up the vectors, we ended it off with one last word problem. And again, it's another practice with the bearings. So in this example, a boat is traveling at a bearing of north 33 degrees west. And right there, I just kind of told my students, all right, let's just stop and let's draw that boat, right? So we have north 33 degrees west. So that's going to be somewhere right around there, okay? And there's the angle. That's going to be our 33 degrees. And then it's going at 42 miles per hour, right? So that's going to be the magnitude of the vector. Then there is a current against the boat at a bearing of south 17 degrees east. So now I have a new bearing. That's a bad bearing. Let's try that again. Okay. Now again, this new bearing is going to be south 17 degrees east. So I'll try to do my best here. Okay. So it's a nice little small angle. That's going to be 17 degrees. And that only has a magnitude of 12. So you can see how like my picture now is kind of getting a little difficult to understand, right? It's kind of like pretty small here. So what I'm going to do is I'm just going to kind of now represent these kind of offsite a little bit. So I'm going to say, all right, the boat here, let's just talk about this. The magnitude of the boat is going to be, is 42 degrees or 42 miles per hour, sorry. The bearing of the boat is 33. But again, we don't want to deal with the bearing of the boat. We want to deal with the angle of the boat. So the angle of the boat is going to be 90 plus 33. So that's going to be 123 degrees. All right. So from this picture, I can kind of see where that's going. Now let's talk about the current. So the magnitude of the current, that is going to be the speed of the current, and that's going to be 12 miles per hour. That kind of looks a little difficult to visualize, so let's space that out a little bit. Okay, and then the angle of the current is, again, you got to think that's going to be from standard form, right? So you could do the positive version, or you could do the negative version. Now, in this case, I'll do the positive version. I think in my class, I actually did the negative version, and some students kind of got confused with that. So I'm going to do the positive version. So all the way around, 3/4 of way around circle is 270. So if you just add 17 degrees, that's going to give you 287. It doesn't matter if you use 287 or if you go ahead and use a negative 83. Typically, it's a little bit easier to use the acute angle. But again, I don't know. But again, you could use the negative or you could use this obtuse angle. So now we have our components for the boat and we have the components for the vector or for the current. And now we can write a vector for each of them, right? So B, which is going to represent the boat, can now be represented as a vector in terms of its magnitude and its angle. And the current can be done in the exact same way. So the current can be written down as 12, the magnitude. Oops, I'm sorry, current. So it's going to be 12 times the cosine of 287 degrees times the sine of 287. Now, I will say that none of these are going to be some nice numbers. So I am going to be storing these all in my calculator now. So what I'll do is I'll show you how I stored them. Let me actually give myself a little bit of room here, because what I'm going to do now is go ahead and just figure out what I want to do now is just kind of figure out the magnitude of these two vectors. And therefore, then we can identify what is it we're looking for. So to identify the component form here, I'm just going to distribute that 42. So I'm going to do 42 times the cosine of 123. And that's going to be a negative 22.878. So I'm just going to call that alpha A. Oops, I'll store that as alpha A. Oh, come on. So store alpha A. There you go. So when I do the component form, that's negative 22.87. And again, I'm not going to use the rounded answers. That's why I'm storing that. And then if I do 42 times the sine of 123, and then I'll store that as alpha B. Now, again, you could type this a lot and a lot more of this stuff in your calculator, but I just want to kind of show my steps where I'm getting some of these numbers. So therefore, you can kind of check with me. And again, I'm storing this as alpha A. And I'm going to store this as alpha B. It's a lot faster and easier to write them as their stored answers than trying to explain to you, all these decimal points again. So again, now to get the next one, I'm going to do 12 times the cosine of 287. So I'll do 12 times the cosine of 287. And that should be a positive number, which it is. And that's going to be 3.51. Okay. And I will store that as alpha C. And then we have 12 times the sine of 287, which should be a negative number, which it is. And that is going to be, let's see, negative 3.1, negative 11.47. So just let me get that out. So that'd be 11.47. Okay. All right, and then I'm going to store that as alpha D. Okay, now it's not really necessary to store all these. Again, the only reason why I'm doing this is just so you can kind of follow along with me. I think when I did these in my class, I didn't store them. I just typed more of this in. I just kind of typed everything into my calculator, just kind of as they were. But I want you to understand, so there's the component form, because there's different operations we could be asking for this, for these. But in this case, it says determine the final speed and bearing of the boat. So again, what we want to do is identify what is the speed of going to be the boat plus the current, right? Now, again, in this case, the current is going against the boat. So we should expect here that this boat is going to be going slower, right? And also it's not going to be going as far west, right? It's kind of getting pushed back to the right a little bit, or a little bit more farther east. So if I want to identify A plus, what I'm going to do to identify A plus, if I want to identify the speed, what that's going to be is that's just going to be the magnitude of B, vector B plus vector C. Okay. So all I'm going to do in that case, as far as writing that out, is that's just going to look like this. So that's going to be the square root of, again, if I want to find these components, that's going to be of A plus C quantity squared plus B plus D quantity squared, right? You're basically combining these two vectors. So let me just kind of write this down here. B plus C is equal to the vector A plus C and B plus D. So that is my component form of that vector. And again, I'm not going to store that again. I just wanted you guys to kind of see what that was so we could kind of just take a break here and calculate those. So let's go and figure out what A plus C is. So I'll do alpha A plus alpha C, square that. And then I'm going to add that to alpha B plus alpha D and square that. Then I'm going to take the square root of that, and I get 30.64. Now, again, we want to make sure of this. Does this make sense? 30.64. Originally, it's going 42 miles per hour. But with the current against it at 12 miles per hour, you can see it's slowing down all the way to 30.64, which makes some sense, right? I mean, because it's almost, it's slowing it down a lot. It's coming basically almost, direct at it. So you can see like that makes some sense as far as how it's slowing down. Now, then I also need to figure out the bearing. Now, again, it's very important when we're figuring out this bearing, we need to look at this vector here. So when we figure out the bearing of this component form, it's going to give us this angle, okay? Because again, remember when we're doing the tangent here, tangent of theta, again, that's going to be B over D divided by A plus C. And that should be a negative angle. So I'm going to do alpha B, oops. So I'll do alpha B plus alpha D divided by alpha A, oops, parentheses, alpha A plus alpha C, close parentheses, and then tangent inverse of that answer, and I get negative 50.8, and that's correct. But again, that's only giving me, come on, almost done. So that's going to give me a negative 50.8 degrees. Now again, that's going to be from standard form to down there, right? So it's very important for me to understand though, that's not the bearing. The bearing is always again going to be from due north. Well, actually, sorry, I should take that back. If I have that as negative 50.8, again, my bearings, we're not dealing them from bearings, we're doing them from south. So if my bearing from here, from standard form, though, is negative 50 degrees, if I want to find the bearing, so again, we have negative 50 degrees, right? So there it is. That's negative 50.8 degrees. All I want to do is figure this out. So to figure out that angle, I'm just going to do 90. Again, I'm right on space. 90 minus 50.8 degrees. So when I do 90 minus that last answer, I get 39.19. So it has a bearing of 39.19 degrees. And again, that's what we're looking for right there. That's where the 39 degrees is. And again, sorry, it's going to be south 39 degrees east, 39.9 degrees east. And again, all I'm trying to do is match up the bearing with the same notation that the bearing was provided. You could also do the bearing from due north, but since our bearing was originally in terms of like the north, the cardinal system, the compass headings, therefore that's what I'm going to use first. I'm going to use south 39 degrees. So it's south 39 degrees, 39.19 degrees east. And therefore, again, you can see how I stored them. Again, you find the vector of the boat, the current, you add those components up to get your resultant vector. And that is going to be in terms of the boat, the speed of the boat plus the current. This time the current is working against us. So therefore, to find the speed, you just identify the magnitude of that resultant vector. And then to find the angle, you go ahead and use the tangent, but you just need to understand the context of where the tangent is given us. And therefore, we need to convert our answer to bearings, which we go ahead and do. And that was it, ladies and gentlemen. I hope you learned some things about vectors, as well as how to apply them for the dot product to identify the angle between two vectors, as well as some word problems. And if you do have any questions, feel free to leave them down below. I do my best to always answer them, or hopefully some other people in the community will be able to help you out as well. So I look forward to seeing you on the next lesson. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on parametric equations. Now, this is the 6th lesson in our chapter for applications of trigonometry, and this is the exact same notes that I gave to my students inside of the classroom. So what we're going to cover for this section is discuss what exactly are parametric equations, how to eliminate the parameter, as well as how to use parametric equations to solve word problems, more specifically dealing with particle motion problems. But the way that I kind of framed parametric equations is I started off with just a discussion as far as what the graph f of x equals sine of x produces. Like, how would we describe the input and the output of the function based on the graph? So I kind of had this discussion with the students. And, most students just kind of did like a little general, like, yeah, the sine of x graph, it gives you that wave function, right? But then again, I wanted to understand, like, this is a function. We have an input and output. What are we plugging in? And what we're plugging in is an angle, right? It's the sine of an angle. So we're plugging in an angle, and what are we getting out? Now, a lot of students replied with the, y coordinate. And again, we had to press that a little bit as far as what do you mean the y coordinate? Y coordinate of what? And then we kind of got to, well, it's the y coordinate of the unit circle. And again, the reason why it's that y coordinate, because it's really the y coordinate over the hypotenuse. But on the unit circle, the hypotenuse is 1, or the radius is 1, I'm sorry. So therefore, we just left it out as y. But yeah, sine represents that y coordinate, right? And that's basically what these values are. Like when we graph the sine of x function, the x-axis represented the angles, and the y values represented the y values of the function. So therefore, then I said, all right, well, if sine represents y, which most students kind of like feel familiar with, what does cosine represent? And again, we think about it, and then we say, oh, well, remember cosine represents the x coordinate. So a lot of students made this relationship of the graph, which you've already kind of did in my class, of making that relationship with the, whatever the x coordinate is, or I'm sorry, whatever the angle for the cosine of that angle is going to produce the x coordinate. So when I went ahead and drew the cosine graph on the same axis here, we had something like this. And again, not everything's going to be perfect here, but again, that would be the cosine of x. So that's cosine of x, and then remember the y coordinate, or the red, was going to be sine of x. So that is going to be our sine of x function. All right, and again, remember sine of x, so angle in, y value out. And then for cosine of x, that was angle in, and that was x value out. And again, that is from the x and y values on the unit circle, okay? Then I talked to them, I said, all right, well, what about a graph that you could represent the x and the y values of that function, given the angle theta? So basically, both of these functions are dependent on what the angle is, right? Whatever the angle is, that's going to tell me what the y value is for sine. And whatever the angle is for cosine is going to tell you what the x value is. But is there a way I can represent both x and y with given that angle theta? And, can we write a function? Can we write a function like this? Well, first of all, what we kind of brought into is if I said, really, here is, whatever my angle is, here's the x and the y. Can we write a function to represent this graph? And what this brought up to the students is, no, we can't, because these two functions, they don't pass the vertical line test. So we can't create a function to represent both of these at the same time for one angle theta. And again, it goes against the very definition of a function. You plug in an angle, you cannot get the x and the y values out, okay? So it's not going to work in terms of functions to represent both of these, at least as one function. So I say, all right, well then can we just create a graph, or a curve, I should probably say. Can we sketch a curve? I'm going to change that wording. That represents the x and the y values given any angle of theta. So if we did that, let's just go ahead and say, all right, well, if we're going to do a curve, let's do a curve on the xy axis. And so what I'm going to do is I'm going to say, all right, let's say at 30 degrees, what are my x and my y coordinates, right? So at 30 degrees, we have an x coordinate of square root of 3 over 2, comma 1/2. All right. What about at 45 degrees? Well, at 45 degrees, we're at square root of 2 over 2, comma square root of 2 over 2. All right. What about at 60 degrees? Well, at 60 degrees, we're dealing with a x coordinate of 1/2, comma square root of 3 over 2. And hopefully you kind of start to see what's going on here. At 0 degrees, I should have done this. That's going to be at 1, comma 0. At 90 degrees, we're dealing with 0, comma 1. And then you can start doing this a little bit quicker here, because I think you start to see the pattern. At 120 degrees, I'm going to be dealing with negative 1/2, comma square root of 3 over 2. Square root of 3 over 2. At 135 degrees, I'm dealing with negative square root of 2 over 2, comma square root of 2 over 2. And then at 150 degrees, I'm dealing with negative square root of 3 over 2, comma 1/2. And the point that I'm trying to make is, oh, I'm sorry, last one. At negative 180, or at 180 degrees, I'm dealing with negative 1, 0. So when I deal with these different angles, what's happening is, yeah, what is this curve that I am creating, right? When I have an angle and I have an x and a y coordinate, what is this curve I'm creating? Well, of course, it's a circle. Now, a lot of people say, oh, it's a unit circle. And yes, for this case, we know what that, those x and y's, like we did create the unit circle. These are all 1 unit away. But it doesn't have to be the unit circle. It's just creating a circle. Now, what is the equation that represents this graph? What is the equation that we have to represent a circle? And many students forgot this from the geometry class. But really, we have x squared plus y squared is equal to r squared. And again, where r, in this case for unit circle, is going to equal 1. Like in this case, our equation is x squared plus y squared is equal to 1. And that's true for all of them. And again, if you remember, that makes sense because when we looked at the unit circle, one thing if you want to remember that, this will come up later, cosine squared of theta plus sine squared of theta equals 1, right? Because again, remember, it doesn't matter my x squared and my y squared, that's going to be my x and my y coordinates, right? As far as in a triangle. So this leg plus that leg squared is always going to give you 1. So either way, the equation we're looking for is x squared plus y squared equals r squared. In this case, our r was 1. That's why we have 1 here. But again, it brought us into that equation of a circle. So the equation of a circle is when we have a center at hk, it's going to be x minus h squared plus y minus k squared. So the center is going to be your hk. And then if we have the center at the origin, we have x and y. And just remember that it's x squared plus y squared equals r squared, where r is going to be the radius. So one of the big common mistakes students will make is they'll see, whatever it's equal to, and they say that whatever r squared is, they say that's the radius. But again, you got to make sure you take the square root of that value. All right, so the problem though, and again, this makes sense. So here's a curve, but this isn't a function, right? This does not pass the vertical line test. So we created a curve based on the angle, all right, and the x and y distance. But again, we can't create a function, or at least one single function. So therefore, what can we do? And that is where our parametric equations come into play. So parametric equations are basically a way for us to take two different functions, continuous functions, on an interval, and for a given input, which we call the parameter. So basically, you can kind of think about these f of t as like the cosine of t or cosine of theta, and g of t representing the sine of theta. So in our case, t could also be theta. Those are kind of the two common parameters. Typically, theta can represent the angle. T, a lot of times for word problems, is going to represent time. But again, you can really use any variable to represent the parameter. But it's basically a way for us to use equations with 3 variables, because up to this point, if we had 3 variables, we needed to have 3 equations. But we can use parametric equations, allow us to use 2 equations in regards to our 1 parameter, our 1 variable. So you can see how they're both inputs of the same variable or parameter, which in this case is t. Just make sure for your x and your y, for those functions, you have a continuous function is going to your parametric equations, okay? So our 2 common cases that we're at least going to focus in for this class is understanding parametric equations for trigonometry. So again, when we're doing trigonometry, our parameter is going to be theta. That's going to be the angle, and that's going to produce us 2 different values for x and for y, which represents, those x and y coordinates, not just on the unit circle, but really for any circle or ellipse or any kind of shape. And then the second one that we're going to deal with, it'd be like will be for particle motion, where the parameter is going to be time. Because up to this point, a lot of times in, algebra 2, we'll deal with particle motion problems, but either it's going to be some distance in regard to time, or it's going to be distance with regard to distance, meaning like, how does the horizontal distance relate to the vertical distance? Or how does the vertical distance relate to time, right? But we never really talk about how are the horizontal and vertical distances with regard to the time. And that's kind of, you can see we kind of have 3 unknowns there. So parametric equations allows us to answer a lot of those questions or figure out a lot of the information based on the horizontal, vertical, and the time. Something that we were just unable to do before. So the first thing though, to understand with parametric equations is a lot of times we don't make sense of them, right? So the first, before I even solved this problem I gave to my students, I said, all right, well, here's a set of 2 parametric equations. What graph does this produce? And most students are like, no idea, right? They know now if they see x squared plus y squared equals 4, they know that's a circle with the radius 2. Or x squared plus y squared equals r squared, they know that's a circle with the radius r, but that's not in this form. So one of the main skills that we want to accomplish in this section is learning how to go from parametric equations to a rectangular equations. And to do that, basically what we want to do is eliminate the parameter, eliminate that third variable that the two parametric equations have in common. And again, that's typically going to be theta or t. So in this case, we have theta. And obviously, if we want to get rid of theta, what we need to do is we need to somehow represent how we can replace sine and cosine of theta. And to do that, we're going to use this lovely lovely identity that we've used multiple times, which is the Pythagorean identity. Cosine squared plus sine squared equals 1. Now, when we represent that, remember the trigonometric functions are squared, right? So it's just cosine squared of theta plus sine squared of theta. So we can think about them like this. Now, again, my goal is to eliminate the cosine of theta and the sine of theta. So to do that, what I'm going to do is I'm going to take both of these parametric equations and I'm going to solve for sine of theta, cosine of theta. Then, now that I know what sine of theta and cosine of theta are equal to, I can now plug them into my equation, and that's going to eliminate the theta, right? I can replace cosine of theta with x over 4. I can replace sine of theta with y over 4. And now what that allows me to do here, is to create this equation, x squared over 16 plus y squared over 16 equals 1. But again, that's not in the form I need it to be, right? So I want to get rid of those 16 as the denominator. So I multiply everything by 16. That gives me x squared plus y squared equals 16, which now I can represent as a circle with a center of 0, 0 and a radius of 4, right? Just remember you square root the 16 to give you a radius of 4. All right. So that was that first kind of one. So basically what we're going to do is just kind of practice doing the exact same thing, but then describe the shape of the equation. So in this next one, we're going to do the same thing. I'm just going to kind of set up here cosine squared of theta plus sine squared of theta equals 1. Okay, so for each of these problems, that's exactly what we're going to be doing. So what I'm going to do is just basically solve for y and x here to just kind of save myself some time. So y over 2 divided by 3 equals sine of theta. And x minus 3 divided by 3 equals cosine of theta. Okay, so now that I've solved for sine of theta as well as cosine of theta, right? You can just see I just subtracted the 2 divided by 3, subtracted the 3 divided by 3. I'm just going to plug them into the equation. So I have, y minus 2 quantity squared plus x quantity 3 quantity squared equals 1. All right. Now, in this case, remember when you have a rational expression squared, you're going to want to square the numerator as well as square the denominator. So in this case, I'll have y minus 2 quantity squared over 9 plus x minus 3 quantity squared over 9 equals 1. Now, some students went ahead and expanded this, but again, I wanted to remind them, like when you go back to the definition here, we don't want it to be expanded of a circle. We want to leave it in that binomial squared form because that tells us what the center is, h comma k. So, so I'll go back. No, where is this thing? There you are. Okay, so now I want to get rid of the 9 off the denominator. So I'm just going to multiply everything by 9 here. I should put it right there. Then when I multiply everything by 9, what that does, the 9 divides out, so I'm left with y minus 2 quantity squared plus x minus 3 quantity squared equals 9. So now you can see that, again, this is a circle with a center at, again, the center is going to be your h comma k, right? So h is with x, k is with y. So that's going to be a center at 3 comma 2. And a radius of r equals 3, right? Because again, the radius is that 9 is going to equal r squared. So just make sure you have that written in there. All right, so the next one is, again, basically going to be doing the same process. I'm just going to switch up the colors here just to kind of make this a little bit, not to confuse everything. So again, in this case, I'm going to divide by 2, right? So there's no adding or subtracting. So I have, I want to see the y here. So I have y divided by 2 equals the sine of theta, And in this case, I have x over 3 equals cosine of theta. Okay, well, again, I have my sine and my cosine, so I'm just going to plug them in here. So in this case, I have y over 2 quantity squared plus x over 3 quantity squared equals 1. And therefore, that's going to give me a y squared over 4 plus a x squared over 9 equals 1. Now, this one becomes kind of interesting because they don't have the same denominator. Now, again, if my goal is to kind of write this without any denominators, I can still figure out like what should I multiply them by. And the common denominator of 4 and 9 is going to be 36. So I'm going to multiply everything by 36. So 36 times y squared divided by 4 is going to leave me with a 9y squared plus a 4x squared equals 9. Now, one of the confusing things that students will do is they'll say, oh, it's a circle with the radius of 3. But again, we got to be careful. We got to understand or think about what is the 9 and the 4 actually doing to the graph? Well, they're stretching and compressing the graph, right? Because those are a dilation. That's how that's impacting the graph. It's not shifting it left or right, but that's going to be stretching or compressing it. So at least in this case, when we have the stretch and the, in this case, when we're multiplying by 1/9, it's happening to the y and the x value, right? And it's the exact same thing. Well, in this example, that's not happening. This one is being, multiplied by the y variable is being multiplied by 9. The x variable is being multiplied by 6. So what's happening is this circle is being distorted horizontally and vertically. So it's not a perfect circle anymore. And actually, what I forgot to do, I am not going to go through what took kind of this lesson a little bit longer is I had students in their graphing calculator change their function to parametric mode, and we actually plugged these equations into that, so therefore we could see. Now, again, you could just use the rectangular equation to understand what the shape of the curve is, and you'd see that this is a circle with a new center at 3, 2. But I also wanted students to kind of practice writing that in parametric mode. Well, in this case, we can see that this is going to be an ellipse. And we're going to study that more next chapter, so I just kind of left it at that. I did want students to understand the center, though, which in this case would be 0, 0. So we'll discuss a little bit more as far as the horizontal or vertical ellipse, how this is going to work, but that's more for next chapter. So for right now, I just wanted them to understand, though, it's not a circle. It's an ellipse. All right, for the next example, again, we're going to do the same thing. We're going to solve for y, or solve for sine of theta and cosine of theta. So I'll just add a 1. Then divide by 3. Let's go back to red. All right, so now going to my red. So I have a y plus 1 over 3 equals sine of theta. And a x minus 2 divided by 4 equals cosine of theta. Okay, so now again, plugging them in, I'll have a y plus 1 over 3 quantity squared plus x minus 2 over 4 quantity squared equals 1. You could square the numerator, square the denominator. So y plus 1 quantity squared over 9 plus x minus 2 quantity squared over 16 equals 1. All right, and what was I trying to do? Oh, I don't remember. Okay, now let's go ahead and figure out, I was like, what am I doing here? Now let's go and find the common denominator of 9 and 16. These numbers, we're going to kind of be using the same numbers over and over again. So you'll get kind of used to this. The product of 9 and 16 is 144. So if I multiply by 144, 9 goes into 144 16 times. And again, my students have a calculator for this chapter, so it's not anything I would not expect them that they could do without a calculator. And at least for right now, next chapter, they're not going to have a calculator. So hopefully they'll be a little bit more familiar with it. But now, again, we can see that this is the same kind of issue we had in the last example, that they are being multiplied by different factors. So therefore, it's not going to produce a perfect circle, but it is, again, going to produce an ellipse. And in this case, my center now is going to be at 2, negative 1. Oops. So an ellipse with a center at 2, negative 1. So that is how you eliminate the parameter as well as understand the curve of the parametric equation, at least for trig. So then what we did is we said, all right, well, what about all the other types of functions? Like, what about this graph? And I gave these to these students, like, what does that look? What does that look like? And most students had no idea. So one thing is we practice plugging them into a calculator and looking at what the graph looks like. And when doing that, you could see that, it produced a line. Now, really the process for eliminating the parameter for any function is, or at least for these two functions where it's not trig, is just to isolate t. Basically, you want to solve for t. And the next thing is when you want to describe the graph, though, we most commonly understand graphs when it's y equals, right? When it's, y equals x, that's a line. Y equals x squared, that's a cube, that's a parabola. When it's y equals square root, that's a square root, right? So we understand when it's something y equals, and we spent time in functions dealing with 12 trigonometric, or 12 different types of functions. So the important thing that we typically want to do most often is always solve for t in terms of the x equation. Therefore, once we solve for t in the x equation, we can plug what t is equal to into the y equation. So you can see I took both equations, I solved for t in the x equation, and I got this expression. Now, it doesn't matter if you use the fraction or you factor out the 1/2. It doesn't really matter. But when I plug this in for t is equal to this, right? So going back to like systems of equations, solving by substitution, same process. You're, plugging in your variable into the other equation, and then you're simplifying. And by simplifying, we get y equals negative 2x minus 3. And again, since that's equal to y equals, I know that is going to be a line. However, not everything is going to be as easy as that first example. So for instance, if I try to solve for t and for x here, I'm going to run into some problems, right? Because I have more than one t. They're quadratic. And so therefore that's going to be an issue to be able to solve for t. So rather than actually spending any amount of time trying to figure that out, I realized I could easily solve for y, which is t minus 1 or y plus 1. If I plug y plus 1 in for t here, now I get this equation x equals y squared plus 4y plus 3, which again is not something we're very familiar with at all, right? What is that equation? However, if you think about this, if you just swap these, right? If you just swap the variables x and y, you would get y equals x squared plus 4x plus 3. Now, most students know that is at least a parabola that opens up. And I would say as long as you understand that's a parabola that opens up, you're good to go. You do have a calculator that could help you graph it. I actually understood that it was factorable. So I said I factored it to find the zeros, and then I did a little bit more detailed sketch. However, that's not always going to be the case. So you don't want to rely on that method, but it should be something that you recognize and say, okay, I see what you're doing there. Now, this actually brings us back again to our functions unit. So here's this equation. I know what this graph looks like. That's a parabola that opens up. So if I swap the variables, the x and y, what is that doing? Well, that's like me finding the inverse, or that's like me finding the inverse of the function, right? That's reflecting it about the y equals x line. So if I swap the variables, right, now it's going to be a parabola that opens up to the right. So as far as describing the graph, it's just basically the same thing. It's this sideways parabola, it opens to the right. And again, we're going to investigate this further, but I just want to make students understand that what the curve is and typically what the opening is going to be. So those are two examples I went with my students, and then I gave them these problems to go ahead and work on and present on the board. So let's just go ahead and practice again, a couple more. Okay, so on to the first example. Again, I'm just going to do the same thing that I kind of did in the first example. I'm just going to solve for t in the x equation. So I'm just going to write that equation here. So 2t minus 4, and then I'll just solve for t. So I have x plus 4 equals 2t, divide by 2. And therefore you can say x plus 4 divided by 2 equals t. Now I'm going to keep the same expression here, and I'm just going to plug that in directly into my other equation for y. So therefore I have y equals 1/2 times x plus 4 divided by 2 plus 1. Now again, you can see here that's going to produce a 1/4 times x plus 4 plus 1. Now again, you could simplify this, right? If you distribute this, so it'd be y equals 1/4 x plus 1 plus 1. But again, you don't need to. I mean, I guess it really depends on the question. But either way, you can see that this is again going to produce a line, right? And where the y-intercept would be 2, the slope is 1/4. Just it kind of depends on what types of information you're asked. It has a positive slope, for instance. Now, the next one, a lot of students sometimes, again, get confused with the fractions. They say, I hate fractions. But again, we don't want to solve for y. So we're kind of forced to focus on solving for t in this equation. Well, again, if I want to get rid of what's happening here, again, this is the same thing as t divided by 3, right? You're trying to solve for t. So if t is being divided by 3, just multiply by 3. Undo division by multiplication. So I have 3x is equal to t. Or, you can think about just multiplying by 3 over 1. That's multiplying by the reciprocal on both sides. Either way, t is equal to 3x. Now I will just plug in y equals a 3x quantity squared plus 2 times 3x is go ahead and just simplify from here. So y is going to equal a 9x squared plus 6x. Hopefully you can see that this is going to be a parabola. And that's going to open up. I didn't just tell you needed to describe, but I think it's just important for you to know that the parabola is going to open up in that case. All right, the next couple examples here is now we have another one. I think solving for x here is rather simple. So we have x minus 1. So just add 1 to the other side. So we have x plus 1 equals t. And then we're just going to apply that into the other function. Now here we have 2 t's, right? So we need to make sure that we apply x plus 1 into both of them. And then just with a little bit of simplifying, this is x plus 1 over x plus 2. Okay. Now, again, this is just going to be just a rational function. I'm not really sure what the curve, how you'd actually express this. But, you should just understand that that is going to produce a rational equation or rational function. Really, the main thing, just kind of know that also you should remember that they have vertical asymptotes at -2, a horizontal asymptote at 1. Not like I'm going to ask you. It's just a good refresh to kind of know what the curve or what this graph is going to look like. All right. The next one is, again, it looks like it's going to be much more difficult to solve for x than it is for y. But in reality, all you have to do to get rid of the cube roots is just to cube both sides, right? If x equals the cube root of t, I'm going to want to just cube both sides. So x cubed equals t. So now when I plug that in, I get y equals 1 minus x cubed. Now, a lot of students are like, I have no idea what that is. And again, I just reminded them, just rearrange the terms. This is x cubed plus 1, right? Hopefully you should recognize that this is a cubic function, right? It's a cubic curve. It's a little S curve that we called it. And again, just remembering the transformations, that's a reflection about the x-axis with a vertical shift up 1. So you didn't have to go through the reflections, but I just kind of use this as a teaching tool to remind students of our transformations as well as asymptotes. All right, for the next 2 examples though, or at least for this next example, again, we realize that solving for x here is not really going to be ideal, right? And we haven't really talked about that in this class. So therefore, that was kind of my point for the students to understand is, oh, this is supposed to be a negative. The point that I was trying to bring to the students was that, yeah, this is something that we're not very familiar with as far as solving for the absolute value. Now, again, hopefully in Algebra 2, you remember how to solve for the absolute value. But again, we can, rather than even spending any ounce of energy trying to figure this out at this moment, since it's not something we discussed in the class, I'm going to go ahead and solve for y. So when I solve for y here, I get y equals 3t. I'll divide by 3, and I get t equals, 1/3, or y over 3, which t equals 1/3 y. Again, you can really use any representation you want to, but I'm going to represent it. I'm going to use the 1/3 y because I think that's a little bit easier to recognize. And then I have x equals a negative absolute value of 1 minus 1/3 y. Okay. Now again, what is that graph going to produce? Well, let's again step back here and say, all right, what would y equals negative absolute value of 1 minus 1/3 x produce? And again, you know what? Forget about all the stuff in the inside. That's a lot that looks very, very confusing as far as the transformations. It is pretty confusing, but what would just y equals negative absolute value of x look like? What would that graph look like? And because all what's happening on the inside, remember, that's just going to be shifting the graph left or right, right? So if we just think of y equals negative x, and that's kind of confusing, that would take a little bit more work, a little bit more explanation. But if we just kind of focus on y equals negative x, we know the graph is going to open down, right? And it's going to be what we call that V-shaped graph. So if I have the x and the y flipped again, basically what's happening now is if my graph is going to be reflected about the y equals x line, what's going to happen is we're going to have this graph is now going to be open to the left. So I'm just going to call this a V-shaped shaped graph or the absolute value. And that's going to open to the left. Okay. And again, you could do that with the same thing with the parabola. When the parabola opens down, if you're reflecting that about the y equals x line, instead of it opening down, it's now going to reflect to it's going to open to the left. So when it's positive, it opens to the right. When it's negative, it opens up to the left. And the next example is another one where it looks a lot easier to solve for y and then for x. But the problem is when we solve for y, if you were to plug in this y into this equation, you're only going to get the square root, right? So therefore, you're going to think like that's only going to give you x equals the square root curve. But remember, that's when x is equal to. So if you reflect, it's only going to give you part of the graph. So in this one, it's going to be really important for us to be able to solve for y, and you'll see in a second. So this one, I know it takes a little bit more work, right? And that's fine, but we're just going to go ahead and solve here. So I have x minus 2 equals the square root of 3t. Then I'm going to get rid of the square root by squaring both sides. Then I'll divide by 3, right? So I have this big equation here, x minus 2 quantity squared over 3, right? That equals t. Now, once I plug that into my y equation, I have y equals negative 3 times x minus 2 quantity squared over 3. Well, the negative 3 and the 3 divide out to give me a negative x minus 2 quantity squared. And again, now I can see that this is a parabola that opens down. Okay, and hopefully you recognize also has a shift 2 units to the right, and the graph should look something like that. If you were to plug y into x, you would not get a parabola. You would get the square root curve. And if you reflected the square root curve about the y equals x line, kind of like doing that same thinking we've done before, you would only get half of the parabola. So that's why it's very important to try to always solve for x. Think about the 2 times, at least in this class, where we're going to avoid solving for x would be the absolute value curve and when it's a quadratic. You know, if this, like for instance, the 2 examples that I did not solve for x, where I solved for y, was the absolute value and the quadratic. And obviously there's more examples, but for this class, that's what I'd say you could focus on. Or at least understanding. Otherwise, to understand the graph perfect best would be to solve for t in the x equation. And the other thing too, I just reminded students and remind you as well that, you know, you can use your calculator to understand what the graph is going to look like. All right, last example, guys, is just the particle motion. So therefore, I just kind of went over with students the understanding the path of an object modeled in feet per second using parametric equations. X equals v sub 0 times cosine of theta t, and y equals negative 16t is 0 plus v sub 0 sine of theta t plus y sub 0. Where basically v sub 0 represents our initial velocity and y sub 0 represents our initial height. So these are going to be very famous problems, like if you throw a ball, right, from ground level, or maybe sometimes you're going to be like on top of a cliff and you throw a ball, okay? So when we want to represent the vertical height as well as the horizontal height in terms of time, we're going to want to use these parametric equations. And again, basically what will be given is usually like an angle that something is shot or thrown from, as well as its velocity. So the first example that I did with my students was we just kind of covered, you know, an arrow is shot from the ground at an angle of 76 degrees with an initial velocity of 300 feet per second. Write the parametric equations that model the path of the arrow. So basically we have 300 feet per second. That's going to be my initial velocity. Since it's being shot from the ground, my y sub 0 is equal to 0. Okay, so my initial velocity is 300 feet per second, and my initial height is going to be 0. And then my theta is going to be 76 degrees. So having those 2 equations, I just plug in the information and I get my 2 parametric equations right here. Now the next one was, how do you find the height and the horizontal distance when the arrow is at 3 seconds? And the nice thing is that's what these 2 parametric equations represent. This parametric equation, or this equation here, function, really represents the horizontal distance based on the time. This represents the vertical distance based on the time. So all I had to do was just plug in 3. And again, I had to use my calculator to go ahead and plug that in. And therefore you can see I got 217 feet. And then when I plugged in 3 in for the y equation, I got 729 feet. So just by setting up the equations and then plugging them in, you can see how we arrived at the feet. Now, the one thing I tried to keep this a little bit easier with the students is because I don't require my students to have a graphing calculator for the test. So some of the problems that are a little bit more advanced, that would be a little bit multi-step, I didn't kind of cover just because, or I kind of covered in class as just like an extension of this lesson, but I didn't want to focus this lesson on there because therefore it's not going to show up on the test because not all my students have graphing calculators or at least access to them. So the next example is one where I actually gave you the parametric equation. So rather than giving you the information, I gave you the parametric equations. And this one says a ball is shot out of a cannon and represented using the following parametric equations where t is in seconds and distance in feet. So what is the maximum height of the ball? Now, again, you got to understand here that when we're looking into this parametric equation, I forgot to type this in. When we're looking in this parametric equation, I can't believe I forgot to do that. So let's see if I can remember everything. So go back to function mode. So when we want to find the maximum height for the ball, we're looking for the x value. Now we could find the x value in terms of time, right? But one of the things since we're not dealing with time, we're only dealing with like the height, right? So a lot of times what's going to be best to do is eliminate the parameter in this case. Now I did a problem that was fairly simple to eliminate the parameter with because t is equal to x. But what I'm going to want to type in my equation here, or at least in my calculator, is -1/16 x squared plus 30x plus 100. Okay, so what that equation is, since t is equal to x, that's going to be the horizontal distance or the vertical distance in terms of the horizontal distance. So otherwise, sometimes what I'll do is I will just eliminate the parameter and go ahead and plug it in that way. You know, sometimes you have to do a little bit more math to eliminate the parameter and then plug them in. But again, since I'm not none of these questions are referring to time, it's not really going to be necessary for me to use the parametric equations like I did in the last example. So now the one thing I wanted to do with the students is a lot of students are not familiar, at least my students are not familiar with using graphing technology. So we spent a lot of time in class helping students get these graphs out, kind of talking about the window that we used. In this case, I use y min is 0. I think the y max I used 4,000. No, y max was 500, I believe. And then the y min was 0, because again, it didn't make sense for my x and my y to be negative. So I just used 0. And then the y max, I think, was 5,000. And you can change your scale and all that kind of stuff. But the main point that I wanted students to do is when they go ahead and graph this, they should get the path of a ball looking something like this. Now, so the first thing we want to do is find the maximum height of the ball. Well, that's going to be the y coordinates of this graph. And the reason why, again, I put this in terms of y and x, because the question is saying, you know, what is the height, right? And what is the distance that the ball travels, or how far does the ball travel before it hits the ground? So that is going to be the x value, like how far it travels to this x value. So in this case, I want to find the y value. In this case, I want to find the x value. So to find the y value, what I'm going to do is find the max. And again, so to do that, I'm not going to spend too much time because I'm not taking this as a technology lesson, but you just go ahead and use second calculus, at least for a TI calculator. And to find the maximum, you do the left bound and the right bounds. You could also use the formula for the vertex of a parabola. It'd be a little bit more difficult with these numbers, but you could definitely do it. And I get a maximum height of y equals 3,700. Okay, and that's again just by using graphing technology. Now, if I wanted to find where the ball hits, well, then what I'm looking for is, again, I'm going to be looking for the x value. So now I'm going to be looking for the 0 of the graph. So I'm looking for basically when does the graph cross the x-axis. So I'm just going to again do left bounds. Then I'll do a right bounds, and x equals 483.31. And again, these are in feet. Okay. And the last one says, is there, you know, if there is a wall 200 feet away that is 3,000 feet high, will the ball clear that wall? So again, like you got to think that's 200 feet. So, 400 halfway around would be, roughly 200, right? Or a little bit more. So let's pretend, here's what they're basically asking. So here's the graph. We have something that's 200 feet, right, away. And basically what we want to know is this y value going to clear 3,000 feet, right? So basically we want to know what is the y value at 200. So I'm just going to take this equation. So I'm just going to have my equation here. And nope. And now I'm just going to evaluate it in for 200. So by taking the graph, I can basically just go ahead and type in 200. And I forgot. There you go, value. There you go, x value of 200. So when I type in second calculate, again, I go to value and I type in 200 and I get 3,600. So I can say at 200 feet, the ball will be 3,600 feet high. So therefore, it will clear the fence. So another problem that we like to typically do is use time in this case, like at a certain time, will it clear the fence? But therefore, you'd have to do a little bit more math for there. But I just wanted to kind of keep things simple, introducing students to, again, another word problem, as well as solving. But there you go, ladies and gentlemen. That is basically our lesson for parametric equations. I hope you understood some things from this lesson as far as, what are parametric equations, how to eliminate the parameter, as well as how to use them for word problems. But if you did have any questions or anything that was kind of hard to understand, please feel free to comment down below, and I look forward to seeing you on the next video. Cheers. Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on polar equations. Now, this is going to be our last lesson in our chapter for applications of trigonometry, the 7th lesson of them all. And what I'm going to do is I'm going to work through the exact same notes that I worked with my own students inside of the classroom. Now, for polar equations, I kind of keep things fairly simple, but what we're going to do in this lesson is we're going to talk about what are polar points or polar coordinates, how to plot them, as well as how to determine the different representations. And then we're also going to focus on the converting between the polar and rectangular coordinates as well as equations. We're not going to get into the graphing of polar coordinates in this lesson. So we're just going to kind of focus on those three main topics, because I know obviously we could get a lot more advanced with the polar equations, but we're just going to keep it simple for this lesson. So the first thing I did to kind of start off the lesson is I gave students 2 points and I said, all right, why don't you guys plot these points? And, just plot them. I put them in quotation because I didn't want students to try to be exact. I just wanted them to pretty much say, where are these points on a coordinate grid? And most students, didn't take them long. They kind of plotted the points. And then what I wanted to do was talk to them like, well, how did you arrive at those points? For instance, on these points here, did you evaluate the square root of 3 divided by 2 to be 0.86 and 1/2 to be 0.5 and then plot it that way? And most students said, no, I didn't do that. I basically recognized this was on the unit circle. So therefore I kind of plotted the point. And I think, that's very, very interesting here what you did. Rather than thinking of what the x coordinate is and what the y coordinate is, what you thought about was what is the distance away from the origin, which in this case is 1, and the angle, which was 30 degrees, right? And then this next case, again, did I say, did you take out your calculator and evaluate for the square root of 2? And no, a lot of them estimated, which is good because that's one thing I taught them in class, that the square root of 2 is roughly somewhere in between 1 and 2. Hopefully we recognize that the x coordinate is negative, so that's why it's going to be in the second quadrant. The x coordinate is negative and the y value is positive, so it's in the second quadrant. But again, if we look at this, we can recognize, we can actually label this point as yes, we have the x coordinates, and yes, the y coordinates. But we can also say, what is the angle here? Now again, if we recognize the two legs of a triangle are exactly the same, we know it's going to come from a 45, 45, 90 triangle, right? Like when you have coordinates, when you have legs that are the same, then this was going to be x square root of 2. Now the students also could use the Pythagorean theorem to figure out the magnitude, which ends up would equal to 2. But again, you can see that the distance, or I'm sorry, the hypotenuse using the Pythagorean theorem, kind of speaking a little bit ahead. But you can see here that distance is going to be 2. And if that's 45 degrees, this angle here, even though that's 45 degrees, we could say this angle would be 135 degrees, right? Because from here to here, oops, I'm sorry. Yeah. From there to there is 135 degrees, right? But inside of there would just be 45 degrees. So what I'm doing is, rather than representing these points as X and Y coordinates, I'm representing the points as how far are they away from the center of the coordinate grid, the origin, and then what are their angle, right? And you can do this for both these examples. You could say this is going to be 135 degrees. All right. And I think by looking at it this way, you can see it's a little bit easier to kind of understand where these points are, like they have a distance and then the angle. Well, to represent these both these ways is what we call our polar coordinates. And our polar coordinate system is basically a way for us to, it's kind of the same thing on our X and Y axis. All right. And we're going to call the origin what's going to be the pole. And a ray from there is going to be our polar axis. So every point can be written as r comma theta, where r is going to represent that directed distance away from the pole. And theta is going to represent the angle, or the directed angle. Now, again, we're going to be using this in standard form. So one of the things I just kind of like, it's not really the radius, but a lot of times I will use the radius to kind of like make sense or make some connections for students. You know, so we can think about this smaller circle here. We can say the radius is 1. So that's like the unit circle. So it's really just like expanding different, you know, circles of a different radius. But again, I don't want you to be confused and thinking them as a radius, because they're not. They're a directed distance. And when I talk about directed distance, the reason why I underline them is because direction matters. You can go in a positive or a negative direction. And that doesn't make sense if you're thinking about them as a radius. So what we'll do is, when we get into some more of these points, we'll start to see why that is the case. All right, but the first thing I want to do is just have students practice plotting coordinate points. And again, remember, this is not an XY graph, but what we're going to do is we're going to focus on now dealing with the directed distance and the angle. So the first thing I tell students to kind of do is find the angle in standard form, right? So the angle of 150 degrees, we can say that we can assume these are going by 30-degree increments. So 150 degrees would be over here. And then we have a directed distance of 3. So it's kind of like counting 3 rings here. 1, 2, 3, out. And we can do the same thing for B here. Now that's going to be negative pi over 3. So that's going to be down this way. And again, you can think about this in terms of thirds, right? So, you know, 1/3, 2/3, 3/3, right? Just break it up into thirds. And then that's going to be a distance of 5. So 1, 2, 3, 4, 5 along that polar axis. And therefore, now you can see that is where your coordinate point is, okay? And that's basically plotting the points. And then I gave the students some examples. And I said, all right, let's just go and practice them. A lot of students, you know, really didn't have issues with this, except when we got to the radians, they kind of forgot how to work through that. But let's just go and plot these. I'll label these as A, B, and C. So the first one's going to be 30 degrees, and we'll do 3. 1, 2, 3. I'll label this as A. For B, that's going to be at 90 degrees, 1. So again, I go into 90 degrees, and then I'm going a distance of 1. For C, we're going to do 135. Now again, that's going to be between 30 and 60, and it's going to be a distance of 5. So 1, 2, 3, 4, 5. Then we have D, which is 2, negative 120. So negative 120, again, we need to think about that. That's going to be 60 degrees away from the x-axis. Again, we're going in the negative direction, right? So remember, in standard form, we have the positive direction and the negative direction. So we're going in negative direction. And again, if these are 30 degree increments, then 60 would be down here, and that's going to be at A2. So we'll do, that's going to be D. And then negative 7 pi over 4 is an interesting one, because again, you got to remember, you're going in the negative direction again, right? So remember, halfway around a circle is pi, just in the negative direction. Well, in terms of force, that's going to be 4 pi over 4. All the way around the circle is 2 pi. In terms of force, that would be 8 pi over 4. So if I'm going in the negative direction, this is going to be negative 4 pi over 4. This would be negative 8 pi over 4. But I only need to travel to negative 7 pi over 4, right? So you could do negative 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So you can see it's going to be, the polar axis is going to be right here. And therefore, then it's going to be at 2. So 1, 2. So that's going to be my E. And then for F, same kind of idea here. We're at 11 pi over 6. So now that's going to be in the positive direction. Well, again, halfway around the circle is pi. In terms of 6, that's 6 pi over 6. All the way around the circle is 2 pi. In terms of 6, that's going to be 12 pi over 6. So again, I'm not going 2 pi, 12 pi over 6. I'm only going to go a pi over 6 short. Which again, if you can see, actually, this circle is broken up into 6 parts. So 1, 2, 3, 4, 5, 6, right? 7, 8, 9. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 11 pi over 6 is going to be all the way to here. And then again, we're going out to 4. So 1, 2, 3, 4. And there you go. So that's how you basically plot these points from there. And again, you want to typically find the angle first, radians or degrees, and then go ahead and plot with the directed distance. Now, the one thing that kind of brings up then is, are these again the same thing as the coordinate points? And that's what I wanted to bring up over here. Like, you can see this coordinate point didn't change. Like, I could write this in this rectangle form or the polar form, but you can see how they create the exact same coordinate points. So if I give you a coordinate point, in terms of like x, y, I can represent that as a polar point as well. So there are some equations, and a lot of people get confused. They're like, I'm not going to remember these, like how, because I don't give them to them on the test. So, what should we do? How can we remember these? So what I went over with my students, I said, this is all the same information you already know. Let's say we have a random XY point on a coordinate grid. All right. We know that that point has a distance. Actually, let me do it this way. Let's use blue. So we know that point is going to have a distance away from the origin, which is R. Okay. And we also know that that XY point is really representing a X distance and a Y distance away, right? So this coordinate point is an X and a Y distance, which creates a right triangle. So therefore, that's how we get the X squared plus the Y squared equals R squared. The other thing is, since we have a triangle, we could say that that is going to represent theta, right? So if we have this right triangle, that represents theta. Well, then again, the tangent of theta is equal to Y over X. So you can see just by like sketching the graph, and again, that's what I did with the students at the beginning of class. I just said, let's just plot the point. Forget about everything else. Plot the point. And just from plotting the point, what we already learned is, or what we already knew, is the Pythagorean identity and the trigonometric function. We could create those. Now, and that was what we did at kind of like at the beginning of our unit on trigonometry. Then we started getting into trying to get prepared for the unit circle. And when we got prepared for the unit circle, what we did is we said, all right, let R equal 1. Now when R equals 1, so typically we have sine of theta is equal to Y over 1. Well, we didn't really need to write, well, remember, actually, hold on. Sine of theta is Y over R, right? And most students were like familiar with sine of theta is opposite over a hypotenuse, right? Cosine is adjacent over hypotenuse. So then we said cosine of theta is X over R, right? Now, again, we simplified this a little bit in the point that we said, well, when R is equal to 1, so when we said when R is equal to 1, then we could just say sine of theta is equal to Y and cosine of theta is equal to X, right? And therefore we had, this was cosine of theta, and this represented the sine of theta. And that was important because that's what we refer to as the unit circle, cosine of theta, sine of theta. But now we're going back to, well, if you look back at your polar coordinates, R is not always 1, right? R can be these multiple different, these different values, these different distances. So how is that going to impact our points? So again, like let's pretend R was 2 in this case. Like let's pretend R is out here. So what would that give us in terms of our X coordinates, right? So if R is equal to 2 out here, well, all that's going to do is you're just going to multiply 2 times cosine of theta to sine of theta. Okay, so you can think of that R as like a scalar. It's multiplying by the horizontal as well as this vertical component of the points, right? Because it's double the horizontal distance and double the vertical distance. So in reality, all we're going to do is whatever, we know that x is cosine, y is sine, right? But that was when r is 1. So when r is any number, we're just going to multiply it by our sine and our theta and our cosine. And again, you can see in our original problem why this kind of makes sense. We can see that when you multiply by r on both sides, you get r times sine of theta equals y. And if you go back to cosine of theta is x over r, you multiply by r on both sides, you get r cosine of theta is equal to x. So hopefully you can see, how we got these green equations as well as how we got the blue equations just by sketching the graph and using what we already know from trigonometry. Now, that was typically the easy part of the beginning of the lesson. Then we get into the multiple representations, and this is where students usually get pretty confused because they have a hard time visualizing these multiple representations. So one of the common questions that comes up is determine 3 representations of a following point. And typically there's going to be a restriction because again, when you recognize when we have angles, we could always use coterminal angles, right? We could always add and subtract 360. We can always add and subtract 2n. That's always going to produce infinite many angles. So typically there's going to be a restriction of what the angles can be. And in this case, the angles have to be between negative 360 and positive 360. So what I'm going to do is I'm going to try to do my best here. And actually, I'm going to go back to using green to kind of represent this. So the first one is, let's say we have 4 180, right? And that makes sense, right? We have 180 degrees. Okay, so there's our angle, 180. And then we have 4, 1, 2, 3, 4, directed distance, done. Now, we can't add 360. Well, we can, but if you add 360, then that's going to give you, let me do this. So that'd give you 180 degrees plus 360, right? Because typically, if you want to find coterminal angles, you just add and subtract 360. But the problem is we get 540 degrees, and that does not satisfy the restriction, right? So that's why we're not going to include that answer, because it doesn't satisfy the restriction. Okay, so therefore we look to, well, what about subtracting 360? Well, if I subtract 360, that's going to give me negative 180, right? And that works. And you can see that produces the exact same angle. If I did negative 180 and then go over 4, you can see how that produces that point. Now I can't subtract 180 again because that would give me negative 540, which again would not satisfy the restriction. So what else can I do? So here's where I actually want to go back and utilize like the idea of vectors just to kind of make a point. So when we are dealing with vectors, one of the things we talked about with vectors was the scalar. So if I had like, here's vector v, and vector v has an x and a y component, right? Well, if I looked at negative v, right, just that same vector multiplied by negative, all that's doing is that's reflecting it about the origin to give me, let's actually call this, let me call this t. So that's going to give me negative x comma negative y. Now, t is equal to the opposite to v, right? Or the negative v. And what's important about that then, negative t is equal to v, right? So like here's vector v, here's vector t. If vector v represents xy and vector t represents negative x, negative y, well, you can see that this is just the negative scalar. T is just the negative scalar of v. And if you did the opposite then of t, that would take you back to your original vector. So what I'm trying to propose to, or I'm trying to understand is these vectors, if you're trying to think about that scalar, when you multiply by a scalar, what you're doing is you're reflecting it about the origin. So when you have that scalar, you're multiplying by the x and the y components. And what that does is and when it's negative, that is going to reflection about the origin. So if we kind of go back to our understanding here, what is this r doing? Well, you're multiplying the r not by just the cosine, not just by the sine, but by the x and the y. So therefore, you can think of this r as also like a scalar. It's going to have that same kind of impact on your polar point like it would a vector. Now, again, these are not vectors. That's why I did this in blue, because I don't want you to get confused. But my point that I'm trying to make here is that if you were to take the following vector, 0 degrees, 1, 2, 3, 4, right? If I was going to do 4, 0 degrees, that's going to take you over here. But again, my point is Those are not the same vectors, right? Obviously. But if I make this a negative, what that's going to do is that's going to reflect it about the origin. So it's over here. So actually that point, -4 0 degrees, is this point being reflected about the origin, which is going to produce that point. So therefore, those two angles work. And again, you could do 0 degrees or you could do 360 because it could be equal to 0 or it could also be equal to 360. Now, so people have a really, really difficult time understanding this. Actually, I don't want to make this negative. There you go. So then I'll do this is a -4, 0 degrees. So people have a hard time, seeing this or like visualizing this. So a lot of times I said, well, we can always go back to these equations, right? Don't forget x equals r times cosine of theta, right? So maybe let's go ahead and check our work. So x equals 4 times the cosine of 180 degrees. And therefore, x also has to equal -4 cosine of 0 degrees. Okay, so let's go and play around with this. Cosine of 180 degrees, right, based on this unit circle here, is going to be -1. So I have 4 times -1, which equals x equals -4. Got it. I'm familiar with that. I agree. That's fine. So if I do x equals -4 0 degrees, I'm going to have a -4 times cosine of 0, which is over here, right? Which is 1, 0. So therefore, that's going to give me x equals -4. And the same thing is going to work because, again, when you're multiplying this -4, because that's the r, you're multiplying that by cosine of theta and by sine. The cosine and the sine are both going to be positive, but when you multiply by a -4, you can see why that's reflecting about the origin. So it's a confusing section, or it's just a confusing point to make. The one thing I kind of tell students to do is, one, always add and subtract 360 or 2 pi. That always will give you a different representation. Make sure you find the restriction. And then the second thing I want students to look at is understand that when you're multiplying by the negative, that is reflecting about the origin. Okay, so it is something though that we want to practice, and that's why I kind of gave the students, a little bit more time to kind of practice and say, all right, let's go and find some different representations. So the first one is I have a negative angle. So therefore I know that the only thing I can really do here to find an easier one is I can take -4/2. I'm going to add 2 pi, which would be 8 pi over 4. So that's the easiest thing I can do. And that's going to give me 7 pi over 4. Okay, so let's go and plot the graph. Actually, I should probably have done that first. First thing you want to do is plot the point. So I have -pi over 4, so that's going to be somewhere here, and then 5. So 1, 2, 3, 4, 5. Okay. So there's my point here, right? And again, this is not a line, this polar axis, but I want to kind of see this here. So again, that is going to be -pi over 4, right? But here's the point. Okay. Now again, all I did was I added 2 pi to get this angle. Now again, I can't subtract 2 pi because that would be larger than our restriction. And again, our restriction is between -2 pi and 2 pi, or -360 and +360. I'm using the same restrictions as my other problem. So I can only add. But now there's really nothing else I can do except for finding the reflection. So again, I got to understand, all right, well, what is that reflection point, right? So remember, the reflection is going to be, or I'm sorry, the negative is going to be, when I deal with -5, that is going to be a reflection about the origin, right? So basically it's going to be this exact same point, 1, 2, 3, 4, 5, right here. So that's going to give me the -5 radius. And now what I need to do is understand, well, what is that angle here, right? So I could do this angle 2 different ways. I could do this angle, or I could do that angle. But again, my point is I want to take that angle to get me to here, which again would be like, you can think about it as +5, but once I make that a negative, it's going to reflect it back over to here. So again, what is this angle? Well, if this is pi over 4, -pi over 4, that means this angle right here is going to be a pi over 4. So I'm going to be pi over 4 short to pi, which would be 3 pi over 4. And if you did the negative version, you could do I could do pi over 4 over pi, which would be a -5 pi over 4. So that would be -5 pi over 4. This one would be 3 pi over 4. And again, you can think of the 5 going this way, and then the reflection making it negative takes you out that way. All right, so now let's do a negative angle. Now again, graphing the negative angles gets confusing. So what I like to do is I like to say, forget about the negative angle. Just graph 120 degrees. So we're going to go 120 degrees. That's going to be 60 degrees away from the x-axis. And then I'm going to go to 3. 1, 2, 3. Okay, so that is my 320 degrees. But now what I'm going to do is I'm going to say, all right. Oh, and let's go and find a different, whatever. Now let's go and figure out the negative 120 degrees. Well, negative 120 degrees is going to be basically this point reflected about the origin. So 1, 2, 3. And you can see that here, this polar axis is on the same line here, right? So that's going to be my negative 120 degrees. All right. So negative 120. So what I like to do is graph the angle first with the positive and then flip it over. All right. Now I do want to think about, so here is negative 120. What is another way that I could represent that? Well, if this is going to be a negative 120, I could also do the negative version of that, right? So I could do negative 3 and say, how far is that going to be from 180, or just subtract? And that'd be negative 240 degrees, right? So if you did negative 240 and then negative 3, that would take you over to here. Or we could think about just doing the positive angle, right? So let's kind of do our calculations. From here to here is 120 degrees. That means from here to here is going to be 60 degrees. And again, using your math here, that means that is going to be 60 degrees as well. So I could use the positive 3, and I could also say positive 3, negative 60 degrees, or I could use positive 3, positive 300 degrees. Okay, because again, if that's positive 3, I could do negative 60 degrees, or I could do positive 3, 300 degrees. And again, it's a confusing thing. I think it's one of those points that, you just need to kind of work through a couple different examples to really kind of refine your understanding of plotting these points and especially dealing with the negative. But the best thing I can just recall with you is, again, one, you can always check your work by using x, r cosine of theta, r sine of theta. But then also really just kind of think about them as their reflection. So when you see that negative, just remember that is representing a reflection about the origin. So it's not, this is positive 120, right? That red dot is positive 120. So when I make it negative, I'm reflecting it about the origin. So I like to do the positive version first and then apply the reflection after that. All right, so again, kind of like to check our points here, like we did in this last example, we can always convert them between each other. So the conversion between polar to rectangular is simply just r times cosine of theta, r times sine of theta. Now, I caution my students not to use a calculator in this case, because typically for a free response, we're not going to be dealing with decimals. I'm going to ask for the exact answer. And then when you're dealing with a multiple choice problem, your answers are not going to be typically in decimals anyway. So you're going to have to find this exact answer. And again, you should be able to evaluate these hopefully without using a calculator anyways, because we have the unit circle. Now, the nice thing about this though too, is we can also verify what our answer is going to be. So in this case, we have the polar coordinate 4, 300 degrees. If I was to go ahead and plot this, all right, I have 300 degrees is going to be down in the 4th quadrant, and we're going to have a distance of 4, right? Sorry. What was I trying to do? I don't know. Well, 300 degrees. 300 degrees is going to be a point on the unit circle, which is 1/2 common negative square root of 3 over 2. But again, so I know that angle is producing something in the 4th quadrant. It doesn't matter if it's a distance of 1 or a different distance of 4 along this polar axis here. It's still going to be in the 4th quadrant. Now, as I convert them, 4 times 1/2 is 2, and then 4 times negative square root of 3 over 2, you can see that I have a positive x and a negative y, which again produces a rectangular point that we know would be in the 4th quadrant as well, right? So that's a good way to kind of check your work, understanding the theta to make sure you're in the right quadrant, and then as well as comparing that to your x and the y coordinates for your rectangular equation. So that's the problem I did with for my students. Now let's just go ahead and practice again, just another example. So again, here I'm going to have x equals 2, cosine of 225 degrees, and y is going to equal 2 times the sine of 225 degrees. Okay, so again, it's going to be helpful to kind of know where 225 degrees is? Well, again, that's going to be in the third quadrant. And again, hopefully you know that coordinate point is negative square root of 2 over 2, comma negative square root of 2 over 2. Okay, so I have 2 times negative square root of 2 over 2. And the y is going to equal 2 times negative square root of 2 over 2. And therefore, the 2's will divide out, and you'll get x equals negative square root of 2, and a y equals negative square root of 2. So therefore, we have negative square root of 2 times, or comma, negative square root of 2. All right, for the next example, you could be, oh, it's a negative. I hate negatives. I'm confused. But again, like, you don't really need to worry about that, right? Because all we're going to do is follow the formulas. X equals negative 3 times the cosine of 5 pi over 6. And y equals negative 3 times the sine of 5 pi over 6. Now, I'll put these in parentheses. You could know that 5 pi over 6 is hopefully in the second quadrant, right? So therefore, the coordinate point here on the unit circle would be negative square root of 3 over 2, comma, 1/2, right? X is negative, y is positive. However, hopefully you recognize that since this is a negative 3, my true point is actually going to be in the fourth quadrant, right? Because it's going to be a reflection about the origin. So my answer should be a positive x and a negative y. So as long as I do this correctly, I should have a point that's actually in the fourth quadrant, not the second quadrant. So let's go ahead and work it out. So I have a negative 3 times the cosine of 5 pi over 6, which is a negative square root of 3 over 2. And therefore, that will leave me with a positive 3 square root of 3 over 2. And then over here, I'm going to be left with a 5 over 6. So that'd be a negative 3 times 1/2, which is going to equal to a negative 3/2. So again, my x is positive, my y is negative. You can see how that is going to produce something in the fourth quadrant. And then my polar point, it's not going to look very nice, but I'll just leave it in its exact form, and we're good to go. Now, the next one is going from the rectangular to polar. And again, a lot of students, they're like, I don't remember the formulas and blah, 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 blah. But the way that I think about this is just go back to our warm-up. Like if you have a coordinate point, right, an xy, then just plot the xy. Like you don't need to memorize anything. Plot the xy. You know that the distance xy to there from the origin is going to be r, which is technically the hypotenuse of a right triangle that you can create, right? Because negative 2 represents the horizontal distance away from the origin, and negative 2 square root of 3 represents the vertical distance. And even though negative 2 square root of 3 might not be a nice number, you know, as far as one that you can like visualize how long it is, what you can do is, you can still use the Pythagorean theorem here. So all I did was I just plugged them in. This squared plus this squared equals r squared, or that distance. And again, not whipping out my calculator and getting to calculations, I get negative 2 squared is 4. Negative 2 times square root of 3 times negative 2 square root of 3 is going to give me 12 r squared. And this gives me 16 equals r squared, and r is going to equal 4. So that is going to be my r equals 4. Now, the next thing is where it gets a little confusing is figuring out my angle. So I'm not sure why I didn't show my work. Oh, I did my work over here. I was like, where did I do my work? So the next thing is understanding, all right, there's my angle theta. Like I need to be able to figure out theta too. So I go ahead and find tangent of theta. That's negative 2 square root of 3 divided by negative 2. Therefore, I do tangent inverse of square root of 3. Hopefully by the unit circle, you recognize that's going to be this point over here, which is going to be 1/2 comma square root of 3 over 2. So when I take the y over the x, I get a square root of 3, which is 60 degrees. Now again, you could also use your calculator. Just make sure it's in degree mode. Oh, that's plus 180. But the thing is, I get 60 degrees. This coordinate point is not 60 degrees, right? This is 60 degrees. So if I want to get the point from here to here, like what do I do? And so what you need to understand is, well, from here to here is 180, and then you add 60 degrees, right? Because again, we're trying to find the angle in standard form from here to here. So 60 degrees is actually just relating the reference angle. And again, you need to understand when we're dealing with the tangent inverse, that's only going to give you, the tangent inverse is only going to give you an angle in the first and the fourth quadrant. So it's being applied, it's going to have that domain restriction on it from tangent. So Therefore, our angle is only going to be in the first and second quadrant, so therefore we just have to use a little bit of math and understanding to recognize we need to add 180 to give us an angle of 4, 240. So I just have a couple more points that I gave my students, and what I'm going to do is I'm just going to do, again, a rough sketch just so I can visualize this to make sure things are working. So I'll have a -9, +3, because I just want to make sure I have this in the right quadrant. Okay, so at least I know it's in the second quadrant. And therefore, when I find my angle, it's going to be a little bit easier for me to make sure that I'm finding the correct angle. So now what I'm going to do is just do -9 quantity squared plus 3 squared of 3 quantity squared equals r squared. So this is 81 plus, let's see, it's going to be 9 times 3. It's going to be 27 equals r squared. Now in this case, when I add them up, I'm getting 108. So again, 3 times 3 is 9. Square root of 3 times square root of 3 is 3. 3 times 9 is 27. So r squared equals 108. And you can just say r equals the square root of 108. Okay, and we'll just leave that. That's fine. There's nothing wrong with that. So our r is going to be the square root of 108. You could simplify that, but we typically just kind of focus on or look into simplifying it. That for this chapter, we're not going to be simplifying our radicals. We'll just leave them as they are. The next thing then, I want to be able to figure out the tangent. So I'm going to do the tangent of theta is going to be 3 square root of 3 over -9, which is going to leave me with a negative square root of 3 over 3. Okay, so hopefully you recognize that is going to be for 30 degrees. So when I do tangent inverse of negative square root of 3 over 3, that is going to give me in my calculator a negative 30 degrees. But again, that doesn't make any sense, right? Negative 30 degrees is over here. My point is over here, right? So we need to understand that negative 30 degrees, what that's doing is that's giving you the reference angle, right? That's giving you this angle right here. But again, we're not trying to find that angle. We're trying to find the angle in standard form from here to here. So hopefully you can recognize that this is just going to be this angle. My calculator, because tangent inverse gives me negative 30 degrees, that's going to represent the reference angle. So therefore, it's going to be equal 150 degrees. All right, again, same kind of thing. This one's a little bit easier to go ahead and plot, but we're going to have a +5, -5. It's going to be down here. So again, if I wanted to find the distance, how far is this away? You can think of that's 5, that's -5. So I'm just going to do 5 squared. So r squared equals 5 squared plus -5 quantity squared. R squared is going to be going to equal to 50. And again, r then is going to be the square root of 50, but we'll just leave that in the radical form there of square root of 50. We'll just leave it as that. So therefore, r is going to be square root of 50. Now we need to figure out the angle. So we'll have tangent of theta is going to equal -5 over 5. So theta equals -5 over 5 is just -1. So that'd be a tangent inverse of -1. And hopefully you recognize that -1, that's going to be a -45 degrees. Or if you were to plug in your calculator, that would give you -45 degrees. Now in this case, we can use the angle to be -45 degrees. That's perfectly fine. Or we could use the positive version. It doesn't really matter. That's a multiple representation here. So again, my r is going to be 50, and this would be -45 degrees. Again, or you could do square root of 50, comma, let's see, that'd be 315 degrees, right? So it doesn't really matter if you want to use the negative or the positive. Obviously, it would kind of depend on the question from you. And then again, just remember, you could also do different representations for all of these, which I kind of forgot to do over here. That was one thing I mentioned with my students. You could do 4, 240. You could also do a couple other variations here. You could do the negative version, right? Which would be, let's see, 60 away from 180. So you could also do 4, negative 120. You could do, what about the negative? If you made this a -4, so this is going to be our answer. But if you did a -4, that's a reflection about the origin. So you could do 60 degrees. Or you could do a -4, -300 degrees. So you can see how these are both kind of variations to produce or to give us this exact same point. But obviously, if I just want to convert this to polar form, that's going to be my answer. But again, if we were looking for maybe a different types of question as far as looking for different variations, you can see how we can arrive at that. Okay, so now let's go ahead and think about working on equations. So how are we going to convert from polar to rectangular equations? So polar equations are basically equations that are in terms of r and theta, whereas rectangular equations are going to be angles that are in terms of x's and y's. So our goal in this case is going to to eliminate our r and our theta. So two things we know. We know that r squared is equal to x squared plus y squared. So if I have an r squared, or if I create an r squared, I can replace it with x squared plus y squared. And then we also know if I have r times cosine of theta, we can replace that with x. And if I have r times sine of theta, we can replace that with a y. All right. So in this first example, you can see that I didn't have either of those, right? So I can't replace r with anything. It needs to be either multiplied by cosine and sine or be r squared. So the easiest way to create an r squared would just be to square both sides, right? And this is something we don't use as much because, you know, when solving equations, that produces an extraneous solution, and we wanted to avoid that. But in this case, it's going to be perfectly fine for us to do it. We're just, you know, converting from one equation to the next. So I go ahead and square both sides. And then that gives me r squared equals 9. And then I convert r squared to x squared plus y squared equals 9. And then I can describe the graph to be a circle with a center at 0, 0 and a radius of 3. And this is, again, going back to our representation that we talked about last class period. The other thing is it kind of makes sense. Like if you think of r is equal to 3, that's the only thing you know about the equation, right? The distance away from the origin is 3. Well, that's just going to create a perfect circle, right? All right, the next one is theta is equal to 60 degrees. And again, the only way I can use theta if it's like r times cosine of theta or r times sine of theta, or, and I forgot to mention this, or if it's tangent of theta equals y over x. So multiplying by r, taking the cosine of both sides and multiplying by r doesn't seem like it's really going to simplify this much. However, taking the tangent of both sides is definitely something that works, and I can easily do. So when I take the tangent of both sides, I now have tangent of theta equals tangent of 60 degrees. Tangent of theta is y over x. Tangent of 60 degrees is the square root of 3. Now, to solve for y, I just multiply by x on both sides, and you can see that I get a line. That's an equation, y equals mx, right? Plus b, where b is 0. But you can see the slope is square root of 3, which is kind of weird, but it works, right? That's going to produce a line. And again, like that kind of makes sense again. If we go back to that polar equation, if you have something that's always 60 degrees, right? Even when you have a negative direction, it's still going to be a 60-degree angle. You can see that's producing a line. All right, and then the last example I covered with my students was when you have r equals 4 times sine of theta. And again, in this case, we need to we have a sine, so basically we want that to be multiplied by r, and that's going to give us y. Well, we just can't multiply one side and not the other side. And also, we recognize there's an r on the left side anyways. So when I multiply by r on both sides, I get an r squared equals 4r sine of theta. I can convert the r squared to x squared plus y squared equals 4y. Now, technically, that's done. However, in preparation for next chapter, what I did is I helped students go ahead and rewrite this into what we call our standard form, which is basically going to be representing, well, this is not fully in standard form, but at least representing the circle or representing our equation into being able to identify the center and by creating the binomial squared. And the way that we're going to do that is by completing the square. So what we want to do is get all the x's and the y's to the same side. You can see I can group the y squared minus 4y together. And then what I want to do is create a perfect square trinomial. And again, I'm not going to get in depth with the completing the square because we're going to spend more time more in depth on that in next chapter. But again, if you recall, that's the b divided by 2 squared equals 4. You can plug that value in. Then that produces a perfect square trinomial, which can be factored down to a binomial squared. And then you have it in this form where it's a little bit easier to identify the circle with a center of 0, 2 and a radius of 2. And again, this is a little bit extra explanation that I went through with my students just to make sure they felt comfortable with the material. And then we went ahead and practiced doing some other equations. So in this next one, I'm not used to secant. Like, what should I do here? Well, again, like if I have an r, I want the r to be multiplied by cosine of theta, right? It's either I square both sides, multiply by r on both sides, or multiply by cosine of theta. So when I multiply by r cosine of theta, I get r cosine of theta equals 2. Because secant of theta times cosine of theta, those are reciprocal functions of each other, so it's equal to 1. And again, r cosine of theta is equal to x. So that equals 2. And voila, we're done. Next example is just like I did in the last one. I'm going to multiply everything by r. So that gives me r squared equals a negative 4r cosine of theta. Again, now this is going to represent x. So I can say x squared plus y squared equals a negative 4x. Now I'm going to do the same process over here. I'm going to have, let's see, that's going to be becoming x squared plus 4x plus y squared equals 0. And then again, basically I'm saying if I wanted to create this as a perfect square trinomial, like x squared plus 4x plus what number here is going to make this a perfect square trinomial? Meaning, what number where the exact same number add to give me 4x, what would they multiply by? Well, what is the one number that's exactly the same that adds to be 4? That's 2, right? 2 plus 2 is 4. Well, then 2 times 2 is 4. But again, you just can't randomly, did I forget to do that? No, okay. You just can't randomly add a 4 to the left side without adding it to the other side. So that's why I'm going to add a 4 here on the other side. Then this can now be factored down into x plus 2 quantity squared plus y squared equals 4. And now you can see that that is an equation. So again, that's perfectly fine. But from here, a little bit extra, you can see that the center, that it is a circle, but with the center at negative 2, 0, and a radius equal to 2. So very, very similar to our last example. All right, so for the next one, we're going to want to do the same thing. Like if I have a cosine of theta, sine of theta, I want those to be multiplied by r. So I'm just going to multiply everything times r. So I'm multiplying everything times r. I get an r squared equals 6r cosine of theta minus 2r sine of theta. Now that produces a x squared plus y squared equals a 6x minus 2y. And again, like technically we're done right there, right? I have now written the equation from r's and thetas to x's and y's. So that is the rectangular equation. However, just in case your problem is not in this form, like for instance on a multiple choice, we want to make sure that we can write this in our standard form, or at least identifying the center and the radius. So what I'm going to do is I'm going to get all the x's and y's to the same side. And actually, I'm just going to rewrite this for the sake of space. Plus y squared plus 2y is equal to 0. Now you can see I'm going to group my x's and I'm going to group my y's. And basically what I want to do is say, all right, what number should I add inside these parentheses to create a perfect square trinomial? Again, what number is exactly the same that adds to give me negative 6? And again, that's going to be a negative 3. Negative 3 plus negative 3 is negative 6. Negative 3 times negative 3 is going to be a positive 9. And if you forget, you can always do opposite of b divide, well, it doesn't matter. Opposite of b. I was thinking the line of symmetry. B divided by 2 squared, right? That's the same thing. If you take negative 6 divided by 2, that's negative 3. Negative 3 squared is going to give you 9. So this always works in that case. But again, our goal here is to create this perfect square trinomial. You can see here, if I add a 4, that produces that, a perfect square trinomial. Or just do the b divided by 2. 2 divided by 2 is 1. 1 squared is 1. So you can see I didn't do that great in my head. So that's going to be 1 equals 0. But again, I have now produced two perfect square trinomials, which now can be factored down into x minus 3 squared plus y plus 1 quantity squared equals 0. Therefore, again, it is a circle with a radius. It doesn't make any sense, guys, for it to equal 0. That means the radius would equal 0, right? I'm kind of working myself way too fast, so I'm going to slow down for a second. Remember, if you add a 9 to the left side, you can't just randomly add a 9 and an equation to the left side without adding it to the right side. Otherwise, the equation's not balanced, right? Back to like 101 of equations. Same thing over here. You can't just add a 1 to the left side without adding a 1 to the right side. So therefore, that's going to equal 10. So this is important because now r, my radius, is the square root of 10. And we can say that the center is going to be the opposite of my h and my k, which is going to be a 3, -1. All right? Okay. For the next example, kind of looks a little interesting here. Well, I figure if I'm going to want to convert this, I'm going to want to get this off the denominator. So what I'm going to do is I'm going to multiply both sides by 2 cosine of theta minus 3 sine of theta. Okay, so I'm just going to multiply the whole equation there. So then what I'll have is r times 2 cosine of theta minus 3 sine of theta on the left-hand side. And on the right-hand side, those will now divide out, right? So therefore, I'll just be left with 6. Well, I can now distribute this r to give me 2r cosine of theta minus 3r sine of theta equals 6. And again, now you can see I have r cosine of theta, r sine of theta. So this could be 2x minus 3y equals 6. Okay, so now you can see that's in rectangular form. Obviously, guys, again, you could write this as slope-intercept form if you needed to. Let's see, that could be negative 3y equals negative 2x plus 6, and then divide by negative 3. So y equals a positive 2/3 x minus 2, right? So you could subtract the 2x, divide by negative 3, and you could also do a slope-intercept form as well. Okay, so to convert from rectangular to polar, I think it's actually a little bit easier because the problem with these is you didn't, every single, except for these two problems, everything else was kind of different, right? Here we had to multiply by cosine. Here we had, these two we had to multiply by r. Here we had to multiply by the denominator on both sides. Like, it's different for each one of these. But for rectangular, it's usually kind of like the same process. You're just going to want to replace your x and y's with r cosine of theta, r sine of theta. So it's kind of like straightforward. So in this first example, if I just replace my x with r cosine of theta and my y with r sine of theta, like, I'm done. Like, basically that is now a polar equation. It's in terms of r's and thetas, right? Because again, our whole goal is to replace x and y's with r's and thetas. However, typically when we're solving for an equation in polar form, we want to have it solve for r. So what I'm going to do is factor out an r because I can't combine them because they're not like terms, right? So I'm going to have to factor out an r, then divide by 3 cosine of theta plus 2 sine of theta to give r equals 4 divided by 3 cosine of theta plus 2 sine of theta. In the next example, again, kind of the same idea. I don't want to replace, well, first of all, before I get to the same idea, I don't want to replace x with r cosine of theta and y with r sine of theta right here, because then I'm still going to have to square them, right? And it's going to kind of, I mean, I guess you could just replace them and then you're done. But if you have an equation that's solved for r, it's going to be a lot more difficult to square things and then try to simplify. So the way that I looked at this, because then you have a sine squared plus a cosine squared, and I think it'd kind of get a little confusing from there. But actually it's still, yeah, it's still, maybe I'd have to, I don't know. I didn't work it out, but either way, the way I looked at it is it's much easier to expand these with variables. And when I expand this with the variables, then I just group my x squared, my y squared together, and my 6x and my 6y together. So therefore I knew x squared plus y squared, that gives me r squared. I can rewrite this in terms of, I don't know why I'm using x. Let's use thetas. I like converted x's to thetas, but I don't want you to confuse, I want you to confuse all these thetas with the actual variable x because they're not. So then I converted the 6r cosine of theta to just cosine of theta, sine of theta. Oh, r times cosine of theta, yeah. Sorry, I converted the x to r cosine of theta, the y to r sine of theta. Okay, and then we come into another situation. This is where it's similar to this one. We have multiple r's. If we need to solve for r and we have multiple of them, typically our goal is going to either combine them or to look into factoring out a common element or factor out the r. Well, in this case, we can't combine them, so I'm going to factor out the r. Now, when I factor out the r, I'm still left with, I have a factored form of r times r plus 6 cosine of theta plus 6 sine of theta. So again, since I have the product equal to 0, I can apply the zero product property. That's good. So therefore, I'm going to set both products equal to 0. So r is equal to 0, and then r plus 6 cosine of theta plus 6 sine of theta is equal to 0. But again, r equals 0, that doesn't make any sense, right? That's like the distance away from the origin. It's like a dot. So it's not even actually a graph at all. So the equation is, we're just not going to represent that. That's not going to represent this equation. So therefore, then I just have this equation. I'll set this equal to 0, and that is the equation I'm going to use because that's not going to represent that, right? That's like a dot at the origin. All right, and then I just gave my students 4 more problems to do, and you can kind of see we'll just kind of work through them in this case. So again, from here, I can just replace y with r sine of theta, -2. When I divide by sine of theta on both sides, that's the same thing as like rewriting this as cosecant. So you'll most commonly see this as cosecant of -2 cosecant of theta. For b, again, first thing we want to do is really just expand this out. So, again, remember x minus 2 quantity squared is x minus 2 times x minus 2. It does not equal x squared minus 2 squared. Okay, that's one of the more common things that I didn't mention in my previous example, but it's one of the more common mistakes students will make. So you actually have to multiply this out. So this is going to be an x squared minus 4x plus 4. Always happens like that. Plus y squared equals 4. Now again, here we have an x squared plus a y squared. So therefore, that's going to equal r squared minus 4 times r cosine of theta equals 0. Right? So you can see what I did is I grouped, actually, let's just show my work here. Let's just group everything. So I have x squared plus y squared minus 4x plus 4 equals 4. Okay, so we can subtract a 4 on both sides. This gives us r squared. And then we have 4r cosine of theta. And again, we can't combine them, but we can factor out our r. And that'd be r minus 4 cosine of theta equals 0. And therefore, that is going to not produce that equation. So therefore, we can just focus on r equals 4 cosine of theta. For next example, we have an x and a y. So I'm just going to replace the y with r sine of theta and the x with a r cosine of theta. Okay. And now to solve for r, I basically want to get the x and y to the same side. So I will subtract a 2r cosine of theta. Okay, and again, we can't combine them, but I can factor out an r in this case. That would give me a sine of theta minus 2 cosine of theta equals 4. So r is going to equal a 4 all over sine of theta minus 2 cosine of theta. All right. And then the last one is going to be just like the one I did up here. So I will kind of skip over a little bit of steps, or at least just not show everything. But again, hopefully we can expand this out. So when I expand this out, that's going to give me an x squared minus 4x plus 4 plus a y squared plus 2y plus 1 equals 5. I'll group these together. So x squared plus y squared minus 4x plus 2y plus 5 equals 0. Then I can rewrite this as an r squared minus 4 cosine of x plus 2 sine, why am I doing x? I don't want to confuse you. Let's use theta plus 2 sine of theta. That's equal to 5, forgetting some things, equals 0, right? You can just subtract the 5s. And then I forgot my r's. Dang it. Going too fast. So let's subtract these 5s here. Okay, so 4x becomes r cosine of theta. Y becomes r sine of theta. Very good. Now we factor out the r, and again, we're going to be left with a r minus 4 cosine of theta plus a 2 sine of theta equal to 0. Again, this r is going to go to 0 or set equal to 0, and it's fine. Therefore, we have r equals 4 cosine of theta. So if you set this equal to 0 minus a 2 sine of theta equal to 0. Oh, I'm sorry. There you go. Slow down. So there you go, ladies and gentlemen. That is our lesson on polar equations. Hopefully that it was helpful for you. What we covered is, again, converting between rectangular and polar points, finding different representations, as well as converting between rectangular and polar equations. Hopefully you understood some of that. And if not, please feel free to put your comments down below, and either myself or hopefully somebody will be able to answer your questions in the comments below. And otherwise, I look forward to seeing you on the next video. Cheers.